Space calls to us with countless mysteries that both challenge what we know and fuel our curiosity. From the shadowy depths of black holes where gravity warps time and space itself to the strange and unpredictable movements of faraway galaxies, the universe is filled with phenomena that are hard to explain. Join us as we embark on a journey to uncover these cosmic secrets, solving one celestial puzzle after another. And beneath the thick, toxic clouds of Venus lies a world so harsh it seems almost alien to life as we understand it. The atmosphere there is mostly carbon dioxide, blanketed by dense clouds of sulfuric acid that hang heavy over the planet like a veil. This deadly combination traps heat in what is known as an extreme greenhouse effect, pushing surface temperatures to around 800 degrees Fahrenheit. This makes Venus hotter than Mercury, even though it orbits farther from the Sun. But temperature is only part of the story. The crushing pressure at Venus's surface is nearly 90 times that found on Earth. Imagine being submerged almost a mile beneath the ocean. This immense force would destroy any spacecraft we send, making exploration a monumental challenge. The mix of blistering heat and overwhelming pressure creates an environment so extreme that no known Earth organism could survive there. Venus's landscape tells a tale of violent geological activity. Its surface is dotted with volcanoes, some of which may still be active, releasing gases that thicken the already dense atmosphere. Vast volcanic plains and towering highlands reveal a planet shaped by powerful natural forces over billions of years. In recent years, scientists have even entertained the possibility that microbial life might exist in the upper layers of Venus's atmosphere. Here, conditions are less severe, temperatures and pressures are more moderate, sparking hope that tiny, hardy organisms could survive, hidden high above the inferno below. The mysteries of Venus remind us that the universe is full of surprises waiting to be discovered. However, the surface of Venus is a realm of extremes. Its harsh environment, marked by crushing atmospheric pressure and temperatures hot enough to melt lead, combines with thick clouds of sulfuric acid to create conditions that are nearly impossible for complex life to survive. Yet beneath these relentless clouds lies a world shrouded in mystery that continues to captivate scientists. Despite the hostile surface, the secrets hidden beneath Venus's veils of acid continue to drive intense scientific curiosity and ongoing missions aimed at uncovering its many enigmas. Meanwhile, far beyond the familiar planets of our solar system, a tantalizing possibility has emerged in recent years. Astronomers have observed peculiar behaviors in distant icy objects orbiting in a region known as the Kuiper Belt, a vast collection of small celestial bodies beyond Neptune. These objects move in unusual patterns that hint at the gravitational pull of a massive, unseen planet lurking in the shadows. This mysterious world, often called Planet 9 or sometimes Planet X, has yet to be seen directly, but its existence is inferred from the gravitational effects it seems to exert. Planet 9 is theorized to be much larger than Earth, possibly several times its mass, with an orbit that is extremely elongated, taking it far beyond the known planets in our solar system. Its distance from the Sun could range from about 20 to 800 astronomical units, where 1 astronomical unit equals the average distance between Earth and the Sun. Because of this staggering distance, the planet is incredibly difficult to detect. It may appear faint and distant against the backdrop of space. Still, its powerful gravitational influence disturbs the paths of Kuiper Belt objects, offering clues to its possible whereabouts. The hunt for Planet 9 has become a focal point of modern astronomy, blending observations from advanced telescopes with sophisticated computer simulations. Each new piece of data brings scientists closer to potentially locating this elusive giant and capturing its first image. Discovering Planet 9 could revolutionize our understanding of the solar system's history and formation, shedding light on how planets evolve and migrate over billions of years. Furthermore, uncovering this world could open the door to the existence of other undiscovered planets hidden in the remote edges of our cosmic neighborhood. The movements of distant celestial bodies suggest that the outer solar system is a dynamic and intricate realm filled with mysteries waiting to be unraveled. As telescopes peer deeper and technology advances, the quest to find Planet 9 continues to inspire astronomers and space enthusiasts around the globe. Shifting focus closer to home, Saturn hosts one of the solar system's most captivating weather phenomena, its hexagonal storm at the North Pole. This striking, six-sided vortex stretches about 14,000 miles across, a shape so precise and massive that it has intrigued scientists since the Voyager spacecraft first discovered it in the 1980s. Unlike any other storm seen in our solar system, Saturn's hexagon challenges our understanding of atmospheric science and fluid dynamics. The hexagon is not simply a giant storm, but a complex, stable structure formed by the interaction of high-speed winds in Saturn's atmosphere. These winds, reaching speeds greater than 150 miles per hour, create a standing wave pattern that takes the shape of a perfect hexagon. Saturn's rapid rotation, combined with the cold polar winds, generates this remarkable geometric figure, a phenomenon that scientists have recreated in laboratory experiments using rotating fluids. By introducing obstacles in fluid flows under controlled conditions, researchers have observed hexagonal patterns emerge, mirroring the storm on Saturn. Seasonal shifts on Saturn also affect this fascinating feature. Changes in sunlight and temperature alter wind patterns, causing variations in the hexagon's appearance and intensity. The hexagonal storm is not static. It evolves over time, with smaller storms forming and drifting along its edges. Its persistence over decades reveals a robust and complex atmospheric system that continues to mystify scientists. Studying this storm offers more than just insights into Saturn's weather. It enhances our broader understanding of planetary atmospheres and the physics of fluid dynamics on a massive scale. Turning to Uranus, this distant ice giant stands out with an extraordinary characteristic. It spins almost completely on its side. While most planets tilt their axes less than 30 degrees relative to their orbits, Uranus has a dramatic tilt of about 98 degrees, making it unique among its planetary siblings. This extreme tilt results in unusual seasonal changes and atmospheric behavior that differ greatly from those of other planets. The leading explanation for Uranus's sideways spin is a colossal collision early in its history. Scientists believe that during its formation, Uranus was struck by one or more massive celestial bodies, knocking it over and causing the extreme tilt we observe today. This event has had profound effects on the planet's climate and magnetic field, setting Uranus apart as a fascinating case study in planetary evolution. Its sideways rotation influences how sunlight is distributed across the planet during its long seasons, creating conditions unlike anywhere else in the solar system. Together, these worlds, Venus with its veiled secrets, the potential hidden giant planet 9, Saturn's mesmerizing hexagonal storm, and Uranus's dramatic tilt, paint a vivid picture of the complexity and wonder of our solar system. Each discovery pushes the boundaries of our knowledge and invites us to continue exploring the vast cosmic frontier that surrounds us. This theory aligns closely with the idea that the early solar system was a chaotic place, filled with colossal collisions that shaped the planets as we know them today. During this tumultuous period, massive impacts were not only common, but powerful enough to drastically alter the rotational axes of planets, as well as influence their axial tilts. Uranus, in particular, stands out as a striking example of this cosmic turbulence. Its unique rotation is both slow and unusual, taking approximately 17 hours to complete a single spin on its axis. This slow rotation, combined with its extreme axial tilt, causes each of Uranus's poles to endure prolonged periods of sunlight followed by equally long stretches of darkness. As a result, the planet experiences dramatic seasonal changes, unlike those seen anywhere else in our solar system. The way Uranus is oriented relative to its orbit means that one hemisphere basks in continuous sunlight for an extended duration, while the opposite hemisphere remains shrouded in darkness. This extraordinary tilt not only affects the planet's day-night cycle, but also plays a critical role in shaping its atmospheric behavior. Uranus's weather is marked by fierce, high-speed winds and ever-shifting cloud formations that provide scientists with a fascinating window into the complex dynamics governing its atmosphere. As astronomers and planetary scientists continue to probe the mysteries of Uranus's rotation and tilt, they uncover valuable clues about planetary formation and the violent history of our solar system's earliest days. Turning our gaze to Mars, the origins of its two small moons, Phobos and Deimos, have long intrigued researchers. These moons are tiny compared to Earth's moon, with Phobos measuring roughly 14 miles across and Deimos about 8 miles in diameter. Their irregular shapes and modest sizes have led astronomers to propose that they may not have formed alongside Mars, but instead were captured from the nearby asteroid belt. The most widely accepted explanation is that Phobos and Deimos are remnants of a larger group of rocky bodies that once floated in the asteroid belt between Mars and Jupiter. Over time, gravitational forces could have nudged these objects out of their orbits and pulled them into Mars's gravitational embrace. Supporting this theory is the close match between the composition of Phobos and certain types of asteroids, especially carbonaceous chondrites, primitive, carbon-rich space rocks. Both moons have surprisingly low densities, suggesting a makeup rich in carbonaceous material and possibly ice. This aligns with the characteristics of many asteroids, reinforcing the idea that these moons originated elsewhere before becoming Mars's companions. Their heavily cratered surfaces and irregular shapes also point to a long history of impacts, common among small bodies drifting through the solar system. However, alternative theories exist. Some scientists suggest Phobos and Deimos may have formed directly in orbit around Mars, created from debris thrown into space by large impacts on the planet itself. Despite the ongoing debate, the true nature and history of these moons remain an open question, inspiring future missions aimed at uncovering more about Mars's unique satellites and the red planet's own evolutionary story. Beneath the thick icy shell of Europa, one of Jupiter's most captivating moons, lies a hidden world that may harbor one of the best chances for finding extraterrestrial life within our solar system. Scientists believe Europa hides a vast subsurface ocean beneath miles of ice, containing potentially more than twice the amount of water found on Earth. This discovery places Europa at the forefront of astrobiological research, as liquid water is widely considered a key ingredient for life as we understand it. Water acts as a universal solvent, facilitating essential chemical reactions that drive biological processes. What makes Europa especially fascinating is the potential interaction between its subsurface ocean and the rocky mantle below. On Earth, hydrothermal vents deep in the ocean floor create mineral-rich environments that support diverse ecosystems without sunlight. Scientists speculate that similar processes might occur on Europa, where minerals from the moon's rocky interior could mix with its hidden ocean, creating conditions suitable for microbial life. Data from past missions, such as NASA's Galileo spacecraft and observations by the Hubble Space Telescope, have detected plumes of water vapor erupting from Europa's icy surface. These plumes offer tantalizing hints about the ocean's composition and even suggest the presence of organic molecules. Future missions, including NASA's highly anticipated Europa Clipper, aim to study Europa's icy crust and its subsurface ocean in greater detail. By examining these mysterious plumes and the moon's surface, scientists hope to unlock the secrets of this alien ocean and determine if life could indeed thrive in such an extreme environment. The possibility of life beneath Europa's ice has captured the imagination of scientists and the public alike, posing profound questions about the nature of life in the universe and our own place within it. Mercury, the smallest and innermost planet in our solar system, presents a unique and puzzling composition that sets it apart from other rocky worlds. Most strikingly, Mercury possesses an exceptionally large iron core, which makes up about 70% of its entire mass. This massive core has baffled scientists for decades, prompting extensive research into how Mercury formed and evolved during the early days of the solar system. One leading explanation proposes that Mercury's oversized iron core resulted from a massive collision early in its history. During the formation of the planets, countless collisions occurred between protoplanetary bodies. A particularly violent impact may have stripped away much of Mercury's original outer silicate mantle, leaving behind a disproportionately large iron core. This process explains why Mercury's mantle is significantly thinner than those of Earth, Venus, or Mars, emphasizing the dominance of its dense core. Additionally, Mercury's close proximity to the Sun subjected it to intense heat during its formation. This extreme temperature may have caused lighter elements and compounds to evaporate or be pushed outward, while heavier elements, including iron, sank inward to form the planet's core. This process of material differentiation, driven by heat and collisions, appears to have been more intense for Mercury than for any other terrestrial planet. Understanding Mercury's unique structure sheds light not only on its own history, but also on the broader processes that shaped all the rocky planets in our solar system, offering a deeper glimpse into the violent origins of our cosmic neighborhood. Furthermore, Mercury's evolution is deeply shaped by its rich geological history. This small planet has provided compelling evidence of volcanic activity, which scientists believe occurred after its iron core had already formed. Studying the present-day structure of Mercury, especially its massive core and overlying mantle, offers crucial clues about how planets form and the unusual processes that can create such distinctive features in celestial bodies. As space missions continue to explore Mercury, each new discovery sheds more light on its vast iron heart, helping us piece together the early history of our solar system and revealing the secrets of planetary development in ways never before imagined. The mysterious spokes of Saturn's rings have fascinated astronomers ever since they were first spotted by the Voyager spacecraft in the 1980s. These spokes appear as radial streaks stretching thousands of kilometers across the rings, their shapes and brightness shifting in a captivating dance over time. Their fleeting nature and remarkable appearance make them one of the most mesmerizing puzzles connected to Saturn's spectacular rings. Scientists currently believe that these spokes form when tiny dust particles within the rings become electrically charged by sunlight and interact with Saturn's powerful magnetic field. This process suspends the particles above the ring plane, creating the visible spokes that change as magnetic and gravitational forces fluctuate. Interestingly, these spokes tend to become most prominent around Saturn's equinox, when sunlight strikes the rings at a low angle, casting long shadows and enhancing the spokes' visibility. This seasonal lighting effect suggests that the interplay between solar illumination and Saturn's magnetosphere is vital in shaping these delicate features. Despite extensive research, many questions about the spokes remain unanswered. Some experts propose that the dynamic behavior of the ring particles themselves or gravitational pulls from nearby moons might also play a role. With each new mission and increasingly sophisticated instruments, scientists hope to unravel the mysteries of these striking patterns, further enriching our understanding of one of the solar system's most breathtaking ringed giants. The story of Pluto and its largest moon, Charon, is equally captivating and has intrigued researchers for decades. Both bodies are part of the Kuiper Belt, a distant region beyond Neptune filled with numerous small icy worlds. The dominant theory explains that Pluto and Charon formed from the same primordial material that composed many other Kuiper Belt objects in the early solar system. According to this model, they emerged through a slow process known as accretion, where tiny dust and ice particles collided and stuck together in the cold outer reaches of the solar system. Over time, these particles combined to create larger objects called planetesimals, which continued to merge under gravity's influence, eventually forming Pluto. Charon, however, stands out as unusually large relative to Pluto, about half its diameter, making their relationship unique among moons and planets in our solar neighborhood. This size ratio has led many scientists to suggest that Charon was created by a colossal impact event. In this scenario, a massive collision knocked loose a substantial amount of material from Pluto, which then gathered together to form Charon. This dramatic origin story explains why Pluto and Charon share such a tightly synchronized orbit, locked in a cosmic dance that hints at the violent past of these distant worlds. As new data arrives from ongoing missions, our understanding of Pluto and Charon's formation continues to evolve, deepening our appreciation for the complex and dynamic history of the outer solar system. The Pluto-Charon system, a fascinating cosmic partnership, presents an intriguing example of celestial mechanics. Both bodies in this binary system are tidally locked to one another, perpetually showing the same face. This gravitational relationship, known as tidal locking, creates a unique dynamic between the two. Further studies of this system, including key data obtained from NASA's New Horizons mission in 2015, have yielded significant insights into the composition and geology of these distant worlds. The findings have unveiled a complex and storied history, allowing scientists to piece together the origins of Pluto and Charon. Understanding their formation not only enhances our knowledge of the intricate dynamics of the Kuiper Belt, but also provides valuable clues about the broader processes that have shaped the entire solar system. As research on these two worlds continues, we find ourselves continually uncovering new details that shed light on their mysterious pasts. These discoveries are not just about Pluto and Charon. They open windows into the history of the solar system, revealing the cosmic events that formed the icy outer reaches of our planetary neighborhood. The continuing exploration of the Pluto-Charon system exemplifies how even the most distant and seemingly remote celestial bodies can provide key insights into the workings of the universe. Meanwhile, the dwarf planet Ceres, located in the asteroid belt between Mars and Jupiter, presents another extraordinary puzzle. In particular, the bright spots found on its surface have captivated scientists since NASA's Dawn spacecraft arrived at Ceres in 2015. The most notable of these bright spots are situated within a large crater called a crater. These spots have sparked intense curiosity regarding their composition and origin. Spectroscopic analysis suggests that the spots are primarily made of sodium carbonate, a type of salt, along with other reflective materials. The brilliance of these spots likely stems from the way sunlight interacts with the surface, illuminating how the bright areas reflect light in contrast to the surrounding terrain. The discovery of these bright spots has profound implications for understanding Ceres's geological history. It is now believed that the spots may have formed as a result of briny water rising from beneath the surface and evaporating, leaving behind the reflective salt deposits we observe today. This suggests that Ceres may have experienced a form of cryovolcanism, or cold volcanism, in the past, a process where icy materials, rather than molten rock, erupt from beneath the planet's crust. Scientists hypothesize that warm, salty water may have once made its way through cracks in Ceres's surface, leading to the deposition of these bright, reflective residues. The discovery of these features, such as domes and mounds in the crater, further reinforces the idea of past geological activity on Ceres. Understanding the origin and composition of these bright spots is critical not only for understanding Ceres's history, but also for broader questions about icy bodies in our solar system. The presence of water, albeit in its frozen or briny state, raises important questions about the potential for past habitability or even the existence of life in such extreme, frigid environments. As researchers continue to investigate these bright spots, the findings promise to unlock even deeper mysteries of this enigmatic dwarf planet. In a completely different corner of the cosmos, and inside the event horizon of a black hole, lies one of the most mysterious and extreme environments in the universe. The event horizon marks the boundary beyond which not even light can escape the gravitational pull of the black hole. Once anything crosses this threshold, it is drawn inevitably toward the singularity, the very heart of the black hole, where density becomes infinite and the known laws of physics break down. Within this boundary, space and time lose their conventional meanings as the immense gravitational forces warp the very fabric of the universe. Current theories suggest that all paths, regardless of their direction, eventually lead to the singularity, making it a one-way journey for anything that ventures too close. This irreversible journey defines the event horizon as the ultimate point of no return. As objects approach the event horizon, they are subjected to extreme tidal forces. The gravitational pull varies dramatically depending on the proximity to the black hole's singularity, which can cause objects to undergo a phenomenon known as spaghettification. This process stretches objects vertically and compresses them horizontally, much like strands of spaghetti, due to the warping of space-time. Despite our growing understanding of black holes, much of what happens within the event horizon remains speculative. Scientists continue to explore how general relativity and quantum mechanics interact in these extreme environments, grappling with questions regarding the nature of space, time, and the conservation of information. The study of black holes and the nature of the event horizon represents a profound journey into the very fabric of the universe. As scientists probe the depths of these enigmatic objects, they not only seek to understand the black holes themselves, but also aim to unravel some of the most fundamental mysteries of the cosmos. The formation of supermassive black holes at the centers of galaxies is another captivating aspect of astrophysical research. These giants can reach masses that are millions or even billions of times greater than the mass of our Sun. Their presence significantly impacts the dynamics and evolution of the galaxies they inhabit. The process by which these supermassive black holes form is still not fully understood, and it remains a focal point for researchers studying the intricacies of galactic evolution. Several interconnected theories have been proposed, each aiming to explain the birth of these immense cosmic objects. As our understanding of supermassive black holes deepens, so too does our understanding of the forces that shape entire galaxies. Each discovery takes us one step closer to uncovering the mysteries of these colossal unseen structures and their profound impact on the universe's larger scale dynamics. The exploration of both black holes and the celestial bodies they interact with continues to be a frontier of scientific inquiry, where the boundaries of knowledge are constantly being tested and expanded. One of the leading hypotheses about the formation of supermassive black holes suggests that these colossal cosmic entities arise from the merging of smaller black holes and dense stellar clusters in the early universe. The process begins with the rapid collapse of massive clouds of gas and dust, which could lead to the formation of many smaller black holes. As these black holes drift through their surrounding environments, they continue to accrete gas, slowly building up mass. Over time, gravitational interactions between these black holes could cause them to coalesce into larger black holes, eventually growing to the supermassive sizes we observe today. However, this process doesn't occur in isolation. The environment in which galaxies evolve plays a crucial role in shaping the formation of supermassive black holes. In the dense centers of galaxies, interactions between stars, gas clouds, and other matter are frequent and intense. These interactions can cause the black holes at the center of galaxies to efficiently accrete material, increasing their mass at a rapid pace. As these black holes grow, they may emit extraordinary amounts of energy, often observed as quasars, ultra-bright and highly energetic centers of active galaxies. The intense radiation observed from quasars occurs when gas spirals into the black hole, reaching temperatures so high that it generates intense X-rays and other forms of radiation. Another significant factor in the growth of supermassive black holes is the mergers between galaxies, which have been a common occurrence throughout cosmic history. These galaxy mergers can funnel enormous amounts of gas and stars into the central regions of the galaxies, providing the perfect environment for black holes to grow even further. These interactions not only contribute to the increase in mass, but also reshape the structure and dynamics of the galaxies involved, often triggering a profound transformation in the galactic environment. The relationship between black hole growth and the surrounding galactic environment plays a critical role in the overall evolution of both entities. However, despite several compelling theories, many details about the formation of supermassive black holes remain unresolved. One of the most intriguing questions scientists are trying to answer is how these massive objects managed to form so quickly after the Big Bang. Additionally, researchers are keen to understand how supermassive black holes interact with their host galaxies over vast cosmic timescales. Ongoing research, driven by advanced telescopes and other observational technologies, is key to unlocking more about the nature and formation of supermassive black holes. As astronomers continue to observe these enigmatic entities, they will hopefully provide new insights into the interactions between black holes and the galaxies they inhabit, offering us a deeper understanding of the processes that shape the universe. In recent years, another mystery has caught the attention of astrophysicists: fast radio bursts, or FRBs. These highly energetic and extremely brief flashes of radio waves were first discovered in 2007, and since then, they have become a subject of intense study. FRBs last only a few milliseconds, yet they release an amount of energy comparable to what the sun emits over a period of 10,000 years. This extreme energy release has baffled scientists, and understanding the origins and mechanisms of these bursts has become a significant area of research in astrophysics. The exact cause of FRBs remains a mystery, giving rise to numerous theories. One prominent hypothesis posits that these bursts could be produced by extraordinary cosmic events, such as the collapse of a neutron star or the merger of neutron stars. In these violent events, extreme gravitational and magnetic forces generate intense bursts of energy that may manifest as FRBs. Another possibility is that the bursts are linked to magnetars, neutron stars with incredibly powerful magnetic fields. The interaction between a magnetar and its surrounding environment could produce powerful radiation bursts that might be observed as FRBs. Some of the more speculative theories propose that FRBs could have origins in the early universe, possibly linked to the formation of black holes or even signals from advanced extraterrestrial civilizations. While the idea of alien communication is tantalizing, the scientific community generally favors natural astrophysical explanations for these bursts. Fortunately, recent advancements in observational technology have enabled astronomers to pinpoint some FRBs to specific galaxies, providing important clues about their origins. Notably, some of these bursts have been observed to repeat, suggesting that they are associated with localized, energetic astrophysical sources. As researchers continue their work on FRBs, each new discovery brings us one step closer to understanding these elusive and puzzling cosmic phenomena. The study of FRBs is not only advancing our knowledge of the universe's most energetic processes, but is also shedding light on the dynamic forces that govern the cosmos. Magnetars, a fascinating subclass of neutron stars, are another area of growing interest for astrophysicists. These stars are renowned for their incredibly powerful magnetic fields, which can exceed 1 trillion Gauss, making them the most magnetically powerful objects in the known universe. The origin of these immense magnetic fields is closely tied to the processes that occur during the formation of neutron stars, as well as the extreme properties of their dense and compact matter. When a massive star reaches the end of its life, it exhausts its nuclear fuel and undergoes a catastrophic supernova explosion, collapsing under its own gravity. The core of the star then shrinks into a neutron star, an incredibly dense remnant where neutrons are packed together so tightly that the matter forms a nearly incomprehensible state. This collapse is a crucial stage in the creation of magnetars, as the intense gravitational forces involved play a role in generating the star's incredibly strong magnetic field. One leading theory about the formation of these magnetic fields suggests that the rapid rotation of the collapsing star amplifies the pre-existing magnetic field. As the neutron star continues to spin, the angular momentum causes the magnetic field to increase in strength. This dynamo effect is a key process in the formation of the magnetar's powerful magnetic field, which can be further magnified by the extreme density of the matter within the neutron star. These enigmatic objects, magnetars, represent one of the most extreme forms of stellar remnants in the universe, and their study offers valuable insights into the laws of physics under some of the most extreme conditions imaginable. As astrophysicists continue to probe the nature of magnetars, FRBs, and supermassive black holes, the mysteries of the cosmos continue to unfold, inviting deeper exploration and understanding of the vast and dynamic universe we inhabit. Within the heart of a neutron star, conditions are unlike anything encountered on Earth. These environments are so extreme that the behavior of matter deviates dramatically from what we observe in everyday conditions. Under such immense pressure and density, matter undergoes profound changes that give rise to a variety of fascinating and complex phenomena. The interactions within this environment play a key role in generating the magnetic fields that characterize these stellar remnants. At the core of a neutron star, an intriguing process occurs: the presence of superfluid neutrons, a state of matter where neutrons move without resistance, creates a dynamic that influences the structure of the star's magnetic field. In some cases, these magnetic fields can emerge so rapidly that they result in an extraordinarily powerful magnetic structure, capable of maintaining its strength over time. The result of this is the magnetar, an extremely magnetized neutron star that harbors one of the strongest magnetic fields in the universe. However, these powerful magnetic fields do not remain constant. As magnetars age, their magnetic fields can undergo significant changes. These changes occur as a result of the immense energy present within the star, which can gradually lead to the rearrangement or decay of the magnetic field. This process often results in the release of energy in the form of sudden bursts or flares. These bursts can release staggering amounts of energy and emit radiation across a wide spectrum of wavelengths, ranging from X-rays to gamma rays. This dynamic behavior not only showcases the immense power contained within magnetars, but also provides a window into their complex evolution and the interactions between these stellar remnants and the surrounding space. The magnetic fields of magnetars, their bursts of energy, and their fluctuating magnetic structures reflect a constant state of change, revealing just how intricate and unpredictable these objects truly are. Ongoing research continues to deepen our understanding of these enigmatic stars, shedding light on the underlying physics behind their intense magnetic fields and how they evolve over time. As we study magnetars, we uncover new layers of knowledge that could have far-reaching implications for our understanding of the universe. In a completely different corner of the cosmos, dark energy presents a far more mysterious challenge to scientists. Dark energy is an enigmatic force that seems to permeate the entire universe, and it is responsible for one of the most puzzling discoveries of modern cosmology: the accelerated expansion of the universe. This phenomenon was first observed in the late 20th century when astronomers studying distant supernovae found that the rate at which the universe was expanding was not slowing down, as had been previously thought, but was in fact speeding up. This discovery ignited a wave of curiosity and investigation as scientists scrambled to understand the true nature of dark energy. Current estimates suggest that around 70% of the universe is composed of this elusive substance. Yet despite its overwhelming presence, its precise nature remains one of the greatest unsolved mysteries in cosmology. The leading explanation proposes that dark energy is an inherent property of space itself, a kind of energy of the vacuum that emerges as space expands. In this model, as the universe grows, more dark energy is created, which further accelerates the expansion in a feedback loop. This concept is deeply rooted in Albert Einstein's theory of general relativity, which includes a cosmological constant that could account for the energy density of empty space. Other theories offer alternative explanations. One hypothesis is that dark energy might not be a constant property of space, but rather a dynamic field that changes over time, influencing the rate of expansion at different epochs in the history of the universe. Another theory suggests that dark energy could be linked to modifications in our understanding of gravity on a cosmic scale, offering a new way to reconcile gravitational forces with the observed acceleration. Despite these compelling theories, no single explanation has yet been proven definitively. The study of dark energy has become one of the central challenges in modern cosmology. What was once a surprising discovery has now evolved into one of the most profound areas of scientific inquiry. As researchers continue to explore this cosmic force, they are developing new techniques for observing its effects and testing theories that could one day provide clarity. Unlocking the secrets of dark energy is not just a quest to understand an enigmatic force. It could fundamentally reshape our understanding of the universe's past, present, and ultimate fate. By delving deeper into dark energy, scientists hope to uncover new insights that will help us comprehend the fundamental forces that govern the cosmos and perhaps even redefine the very laws of physics as we know them. In the search for answers, dark energy remains a key focal point for both theoretical and observational research. Its discovery has opened up as many new questions as it has answered, and the journey to understand this mysterious force continues to push the boundaries of what we know about the universe, its expansion, and the intricate workings of the cosmos at large. Quasars stand as some of the most extraordinary and luminous phenomena in the cosmos, often outshining entire galaxies. Their brilliance and immense energy output derive from the powerful activity surrounding supermassive black holes located at the centers of far-off galaxies. These black holes, whose mass can be billions of times that of our Sun, act as the engines that fuel quasars. As matter spirals toward one of these supermassive black holes, it forms a rapidly rotating accretion disk, a swirling disk of gas, dust, and other cosmic materials. This matter becomes intensely heated due to the immense gravitational forces and friction as it spirals inward at mind-boggling speeds. The temperature in the accretion disk can soar to millions of degrees, causing the material to emit an extraordinary amount of electromagnetic radiation across a vast spectrum, from visible light to ultraviolet and X-rays. As this transformation of potential energy into thermal energy takes place, it produces light and radiation on a scale so immense that the energy output of a quasar can be up to 1,000 times greater than that of all the stars in a typical galaxy combined. This overwhelming brightness is what makes quasars detectable across unfathomably vast distances. In fact, quasars are visible from billions of light years away, making them among the most distant objects we can observe in the universe. Their luminosity provides valuable clues to astronomers about the conditions of distant galaxies and the processes occurring at the hearts of those galaxies. Quasars also emit powerful jets of relativistic particles traveling at speeds close to the speed of light along the rotational axis of the supermassive black hole. These jets, which extend across vast distances, sometimes stretching thousands of light years into space, radiate additional energy in the form of high-energy particles and radiation. The interaction of these relativistic jets with surrounding matter can have profound effects on their host galaxies. They can deliver energy and momentum to the intergalactic medium, shaping the environment and influencing the evolution of the galaxy itself. Through studying quasars, astronomers gain vital insights into the workings of the universe on a grand scale, helping us unravel the mysteries of black hole formation, the growth of galaxies, and the evolution of the cosmos itself. Quasars serve as cosmic beacons, illuminating the depths of galactic history and providing a glimpse into the immense forces that drive the universe forward. In parallel, another of the universe's most awe-inspiring phenomena are gamma-ray bursts, the most powerful explosions observed in the cosmos. These bursts release staggering amounts of energy in the form of gamma rays, the most energetic form of electromagnetic radiation. Gamma-ray bursts are thought to occur either during the deaths of massive stars or through the cataclysmic merging of compact objects, such as neutron stars or black holes. When a massive star exhausts its nuclear fuel, it collapses under its own gravity, resulting in an implosive core collapse followed by a supernova explosion. If this collapse is accompanied by the emission of powerful jets of material, those jets can produce the gamma rays that characterize a gamma-ray burst. Likewise, when two neutron stars collide, or when a neutron star merges with a black hole, the result can be just as explosive. The immense gravitational energy released in these collisions causes a black hole to form rapidly, surrounded by an accretion disk. As material is drawn into the black hole, it generates powerful jets of radiation, and if these jets are aligned with Earth, we observe them as a gamma-ray burst. Gamma-ray bursts are classified into two main categories: long-duration bursts and short-duration bursts. Long-duration bursts, lasting anywhere from a few seconds to several minutes, are typically associated with the collapse of massive stars. On the other hand, short-duration bursts, which last less than 2 seconds, are generally linked to the merging of compact objects like neutron stars or black holes. This distinction is crucial because it provides scientists with insights into the different environments and conditions that give rise to these catastrophic events. The energy released by a gamma-ray burst is so immense that it can outshine the total energy emitted by our sun over its entire 10 billion year lifetime, all in just a matter of seconds. These bursts are so bright that they can be detected across the vast reaches of the universe, from billions of light years away, offering astronomers an unparalleled opportunity to study the extreme processes that govern the universe. The study of gamma-ray bursts not only sheds light on the final stages of stellar evolution and the behavior of black holes, but also provides a unique window into the fundamental nature of physics under the most extreme conditions. Understanding these cosmic explosions challenges our comprehension of the universe and pushes the boundaries of what we know about the fundamental forces shaping the cosmos. Binary star systems, fascinating celestial entities composed of two stars bound together by gravity, often emerge from the dense regions of gas and dust within molecular clouds. These molecular clouds, vast and cold, serve as the stellar nurseries where stars are born. As portions of the cloud collapse under their own gravitational pull, they fragment into smaller clumps, each one becoming the cradle of a new star. When two such clumps find themselves in close proximity, they initiate a gravitational dance, eventually coalescing into a binary system, two stars orbiting each other in an eternal celestial embrace. The formation of these binary systems is not a random event, but a delicate process that hinges on the conditions present in the molecular cloud at the time of star formation. The distribution of mass, temperature, and the specific dynamics of the gas cloud all play a critical role in determining whether two stars will form together and how their system will evolve over time. These early stages of formation influence the future trajectory of the binary system, shaping its characteristics and determining the paths each star will take on their life journey. Once a binary system is established, its evolution is far from uniform. The stars within it may evolve in tandem, particularly if they are similar in mass. When this happens, the two stars will undergo comparable stages of stellar evolution, from their birth in the dense molecular cloud to their eventual expansion into red giants. The interaction between the stars can become increasingly complex as they grow older. If they are close enough, their outer layers may begin to transfer mass, leading to phenomena such as mass exchange. In some instances, this can result in the formation of additional structures, like accretion disks, around one of the stars. These disks form when matter is drawn towards a companion star, often giving rise to intense radiation and powerful jets of particles. However, not all binary stars evolve similarly. When one star is significantly more massive than its companion, the disparity in their evolutionary paths can be dramatic. The more massive star may end its life in a spectacular explosion, known as a supernova, an event so powerful that it can briefly outshine an entire galaxy. This explosion leaves behind either a neutron star or, in the case of even more massive stars, a black hole. The less massive companion star, though, will continue to evolve independently, its journey marked by a very different set of stellar processes. The dynamics of the binary system can shift dramatically at this point. The remnants of the supernova, either a neutron star or black hole, can interact with the companion star gravitationally, sometimes leading to an entirely new set of phenomena. For instance, a binary system consisting of two neutron stars can form, or perhaps a neutron star paired with a black hole. These systems, in particular, are of immense interest to astronomers because of the gravitational waves they emit. These waves are ripples in the fabric of space-time itself, generated as the stars spiral closer together, often with such intensity that they can be detected by observatories millions of light years away. The study of binary star systems is not merely a curiosity. It provides critical insights into the larger processes of stellar evolution, offering a window into the life cycle of stars. By observing these systems, astronomers can measure various stellar properties, such as mass, luminosity, and age, thereby refining models of how stars form and evolve. Furthermore, binary systems are essential for understanding the broader dynamics of galaxies and how stars influence their galactic environments. As stars interact with one another, they can trigger supernovae, form black holes, and send shockwaves through their surroundings, fundamentally altering the structure and composition of the galaxies they inhabit. But stars are not the only cosmic objects that captivate scientists. Cosmic rays, high-energy particles originating from outer space, pose another profound mystery. Among these particles, those with ultra-high energies stand out, intriguing researchers with their mind-boggling power. These cosmic rays can carry energies exceeding 1 quintillion electron volts, a staggering number that dwarfs the energy levels reached by human-made particle accelerators, such as the Large Hadron Collider. To put this into perspective, these cosmic rays are millions of times more energetic than the most powerful particles ever created by the most advanced experiments on Earth. The origin of these ultra-high-energy cosmic rays is one of the greatest puzzles in astrophysics. Scientists are still working to unravel their source, with several competing theories under investigation. One leading hypothesis suggests that these high-energy particles are accelerated by supermassive black holes at the centers of active galaxies. These black holes, which can contain millions or even billions of times the mass of our Sun, are surrounded by regions of intense energy. As matter falls toward the black hole, it is heated to extreme temperatures and accelerated to nearly the speed of light by powerful shock waves and magnetic fields. This process allows protons and even heavier nuclei to gain enormous velocities, sending them racing through intergalactic space. As these charged particles travel through the vast expanses of space, they interact with the cosmic microwave background, the faint afterglow of the Big Bang. This interaction can give the particles an additional boost, enabling them to achieve energy levels far beyond what is possible in laboratory conditions. This means that the cosmic rays we observe may have traveled vast distances, gaining energy from the environments of distant black holes or other energetic cosmic phenomena before reaching us. Another proposed source of these ultra-high energy cosmic rays is gamma ray bursts, some of the most energetic explosions in the universe. These bursts, which are thought to be caused by the collapse of massive stars or the merging of compact objects like neutron stars, release an immense amount of energy in a very short period of time. During these explosive events, particles can be accelerated to ultra-high energies, creating cosmic rays with far more energy than we typically observe from other sources. The study of both binary star systems and ultra-high energy cosmic rays is a journey into the heart of the universe. These phenomena offer us clues about the fundamental workings of the cosmos, from the birth and death of stars to the mysteries of the most energetic events in the universe. By continuing to explore these cosmic wonders, scientists hope to gain a deeper understanding of the forces that govern the universe and our place within it. Ultra-high energy cosmic rays, UHECRs, the most energetic particles ever detected, hold the key to unlocking the most profound mysteries of the universe. These particles, which carry energies far beyond anything achievable by human-made accelerators, are scattered throughout the cosmos, entering our atmosphere from distant corners of space. But despite their existence, the exact origins of UHECRs remain elusive, making their study one of the greatest challenges in modern astrophysics. Certain cosmic phenomena have long been proposed as potential sources of UHECRs. Supernova remnants, particularly those associated with Type II supernovae, and the cataclysmic mergers of neutron stars stand out as primary candidates. These events, which result in the violent explosion or collision of massive stellar bodies, are believed to create the conditions necessary for accelerating particles to the extreme energies observed in UHECRs. However, pinpointing the true origin of these particles is incredibly difficult. Their trajectory through space is profoundly influenced by magnetic fields present not only within our galaxy, but also between galaxies in the vast expanse of intergalactic space. As UHCRs travel through these magnetic fields, their paths become twisted and distorted, making it nearly impossible to trace them back to their original source. This complexity is compounded by the fact that the particles are not directly observable through traditional means. They interact with Earth's atmosphere and produce secondary particles, such as air showers, which are easier to detect. Advanced observational techniques, including extensive arrays of air shower detectors and neutrino detectors, have been developed in a concerted effort to study these cosmic rays. Through these groundbreaking technologies, scientists hope to uncover more information about the extreme astrophysical processes at play in the universe, processes that may hold the key to understanding the fundamental laws of physics. The answers to these questions could have far-reaching implications, not only shedding light on the violent and energetic events shaping the universe, but also refining our understanding of the very nature of space, time, and matter. As we delve deeper into these mysteries, the potential for discovering new physics at the highest energies grows exponentially, offering a glimpse into the most enigmatic forces of the cosmos. In this quest to understand the origins of ultra-high energy cosmic rays, one cannot overlook the role of Type Ia supernovae, which are among the most spectacular and predictable explosions in the universe. These events serve as invaluable cosmic yardsticks, allowing astronomers to measure vast distances across space with remarkable accuracy. The origins of Type Ia supernova lie in the remnants of stars that have exhausted their nuclear fuel, white dwarfs. These compact, stellar remnants are primarily composed of carbon and oxygen, and are supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents the white dwarf from collapsing further under its own gravity. For a white dwarf to trigger a Type 1a supernova, it must undergo a process called accretion, in which it gains mass from a companion star in a binary system. This companion could be another ordinary star, or in some cases, another white dwarf. As the white dwarf accumulates material, primarily hydrogen and helium, from its companion, its mass slowly increases. When the mass of the white dwarf approaches approximately 1.4 times the mass of the Sun, a critical threshold known as the Chandrasekhar limit, the core temperature and pressure rise to the point where nuclear fusion is ignited. Once fusion begins, it escalates rapidly in a runaway reaction. Unlike the typical stellar detonation, which occurs through the slow and steady fusion of elements over time, a Type 1a supernova is characterized by a thermonuclear runaway. This process leads to the rapid fusion of carbon and oxygen into heavier elements, releasing an enormous amount of energy. The explosion is so powerful that it completely disintegrates the white dwarf, scattering heavy elements such as iron and nickel into space. These elements are then incorporated into the interstellar medium, enriching the material from which new stars, planets, and even life will eventually emerge. The consistent luminosity of Type 1a supernovae, driven by the uniform mass of the exploding white dwarfs, allows astronomers to use them as standard candles for measuring cosmic distances. By studying these explosions, scientists have been able to chart the expansion of the universe, leading to groundbreaking discoveries about the nature of dark energy and the ultimate fate of the cosmos. The study of Type 1a supernovae, therefore, not only enhances our understanding of stellar evolution, but also serves as a crucial tool for mapping the large-scale structure of the universe. It offers a window into the life cycle of matter, from the birth of stars to the formation of planets and the development of life itself. Turning our gaze to the Milky Way galaxy, our home in the cosmos, we see a barred spiral galaxy, a classification that refers to its central bar-shaped structure, composed primarily of stars, with spiral arms radiating outward. However, the true shape of the Milky Way is far more intricate than this simple description. While scientists often visualize the galaxy as a flattened disk with a central bulge known as the galactic bulge, the complete structure is more complex, with a vast halo of stars, gas, and dark matter extending far beyond the visible galaxy. The disk of the Milky Way, where most of its stars, including our Sun, reside, has a thickness of about 1,000 to 2,000 light-years and spans approximately 100,000 light-years in diameter. Within this disk lie the spiral arms, regions of the galaxy where stars are born in great clusters, their formation triggered by density waves that compress gas and dust. These spiral arms give the galaxy its distinctive appearance, but they are not fixed features. Rather, they represent areas of higher stellar density, where the gravitational pull of stars and gas creates a wave-like motion that propagates through the galaxy. Beyond the disk lies the galactic halo, a roughly spherical region of the galaxy, where older stars, globular clusters, and dark matter reside. The exact extent of the halo is still uncertain, with some estimates suggesting it may stretch far beyond the visible parts of the galaxy, influencing the motion of stars and shaping the dynamics of the entire Milky Way. This diffuse, unseen component of the galaxy plays a crucial role in its overall structure, contributing to a more rounded shape when observed from a distance. In this way, the Milky Way, like other galaxies, is not a simple, static structure, but a dynamic, complex entity shaped by the interplay of gravity, dark matter, and the life cycles of its stars. As we continue to explore the cosmos, the study of our galaxy's structure will provide crucial insights into the nature of galaxies as a whole and the forces that govern their formation, evolution, and ultimate fate. Observations using cutting-edge technology, including infrared and radio waves, have profoundly reshaped our understanding of the Milky Way galaxy. These tools have enabled astronomers to map the intricate distribution of stars and gas across the vast expanse of our home galaxy. However, a unique challenge remains. Our position within the Milky Way limits the precision of certain observations. As a result, astronomers continue to refine their models and research methods, slowly but surely, uncovering more details about the true shape and structure of our galaxy. While these discoveries enhance our knowledge of the Milky Way, they also provide crucial context in the broader study of galaxy formation and evolution throughout the universe. One such intriguing discovery lies within the Andromeda Galaxy, also known as M31, which exhibits an unusual and complex feature, a double nucleus. This dual structure results from intricate gravitational interactions and dynamic processes within the galaxy. The primary nucleus of Andromeda is a bright, dense region at its center, which houses a supermassive black hole. The secondary nucleus, however, is thought to be the remnants of a smaller galaxy that was absorbed into Andromeda over millions of years. As galaxies evolve, they often interact with their neighboring galaxies, either through gravitational attraction, tidal captures, or mergers. Andromeda is currently in the process of merging with several of its satellite galaxies, including M32 and NGC 205. During these interactions, smaller galaxies can be torn apart, leaving behind stellar remnants and debris that contribute to the formation of a secondary nucleus. This secondary structure, though less luminous, forms a distinct concentration of stars and other materials separate from the primary nucleus. The dynamics of Andromeda's double nucleus are influenced by several factors, including the rotation of the galaxy and the distribution of dark matter in its halo. The intense gravitational forces exerted by the galaxy's mass, combined with the remnants of absorbed star clusters, give rise to complex orbital patterns that stabilize and maintain the double nucleus feature. By analyzing the velocities and movements of stars in these regions, astronomers can unravel the ongoing processes that shape the galaxy. Studying Andromeda's double nucleus not only provides valuable insights into the evolution of this specific galaxy, but also contributes to a deeper understanding of galactic formation and interaction at large. The presence of multiple nuclei in a galaxy typically indicates a rich history of mergers and gravitational interactions. As Andromeda continues to evolve, it remains a critical subject of research for astronomers eager to understand the dynamic forces that shape galaxies over time. In our own Milky Way, another fascinating feature, the Fermi bubbles, offers a striking glimpse into the energetic processes at the galaxy's center. These two enormous symmetrical structures extend above and below the central region of the Milky Way, creating a dynamic feature of immense scale. One leading theory posits that the Fermi bubbles are the result of high-energy outflows from Sagittarius A star, the supermassive black hole at the heart of the Milky Way. When matter falls into this black hole, it emits powerful jets of particles and energy. These jets can interact with the surrounding gas and dust, producing shock waves that push material outward, forming the massive Fermi bubbles. This activity could be linked to a more active phase of the black hole's life, during which it consumed more mass and expelled energy at a higher rate than it does today. Another hypothesis suggests that the bubbles are the remnants of cosmic rays released during periods of intense star formation or supernova explosions in the galaxy's central region. In the final stages of their existence, massive stars explode in supernovae, releasing vast quantities of energy and cosmic rays into the surrounding space. Over time, these powerful explosions could accumulate, contributing to the formation of large-scale structures like the Fermi bubbles. These bubbles provide critical insights into the dynamics of our galaxy's core and the energetic processes surrounding its supermassive black hole. As research into the Fermi bubbles continues, astronomers are eager to better understand their formation as well as the energy sources that sustain them. These findings not only enhance our understanding of the Milky Way, but also contribute to the broader study of galaxy evolution, particularly the role of supermassive black holes and stellar populations in shaping galactic structures. Meanwhile, the formation of spiral arms, another captivating feature of galaxies, including our own, remains a complex and dynamic process. Spiral arms are not static features. Rather, they emerge as a result of the interplay between stars, gas, and gravitational forces within a galaxy's disk. The process is driven in part by what's known as the density wave theory, which posits that the spiral arms are created by waves of increased density that travel through the galaxy's disk. These waves cause stars and gas to cluster together in certain regions, creating the characteristic spiral patterns observed in many galaxies. As stars orbit the galaxy's center, they move in and out of these density waves, producing the spiral shapes we recognize. Think of these density waves like traffic jams on a highway. As vehicles, or stars and gas in this case, move through, they slow down and group together in areas of higher density. This clustering results in the formation of brighter and more densely packed regions that form the visible spiral arms. Understanding the mechanics behind these spiral structures offers astronomers a window into the underlying dynamics of galaxy formation. Not only do spiral arms play a significant role in the distribution of stars and gas, but they also reveal key insights into the gravitational interactions that shape a galaxy's overall structure and evolution. In summary, the ongoing exploration of our galaxy's structure, whether through the study of Andromeda's double nucleus, the Fermi bubbles, or the formation of spiral arms, deepens our understanding of the forces at work in the universe. These observations do not just improve our knowledge of the Milky Way itself, but also provide invaluable context for the study of galaxy formation and the complex dynamic processes that govern the evolution of galaxies across the cosmos. Each discovery, no matter how small, contributes to our broader understanding of the universe, making the study of galaxies a field of endless intrigue and excitement. Star formation plays an essential and transformative role in the intricate dance that shapes the spiral arms of galaxies. These arms, visible from Earth as luminous ribbons of stars, gas, and dust, are regions where gravitational forces, stellar winds, and radiation all collide in a cosmic symphony. Often, these arms correspond to regions of heightened density, areas where new stars are being born at a frenetic pace, particularly within the dense molecular clouds that populate galactic disks. The birth of hot, young stars releases an incredible amount of energy, radiating intense light and generating powerful stellar winds. This outpouring of energy from these newborn stars interacts with the surrounding gas and dust, further influencing the structure of the galaxy, helping to amplify the spiral arms themselves. As these new stars mature and eventually reach the end of their lives, they leave their mark on the galaxy's spiral structure, continuing the cycle of evolution. Supernova, stellar remnants, and the release of heavy elements into the surrounding interstellar medium ensure that the galaxy's spiral arms are not static features. Instead, they undergo continuous transformation, evolving over cosmic timescales. The feedback loops between the birth, evolution, and death of stars ensure that the spiral arms remain dynamic, constantly reshaping the appearance and behavior of galaxies. Additionally, interactions between galaxies introduce another layer of complexity to the formation and evolution of spiral arms. The gravitational tug-of-war between neighboring galaxies can induce tidal forces, causing distortion within the spiral structure of a galaxy. These gravitational interactions might enhance existing spiral arms or even reshape them entirely, creating a more pronounced or altered structure. Such cosmic interactions highlight that the formation and evolution of spiral arms are not solely driven by the life cycle of stars, but are heavily influenced by the gravitational ballet between galaxies. In a universe where gravitational forces govern the motion and interaction of cosmic bodies, understanding how spiral arms are shaped reveals much more about the larger processes that dictate galaxy formation and evolution. These arms are not isolated features, but are deeply intertwined with the life cycles of stars and the gravitational interactions of galaxies. By studying them, scientists can uncover valuable insights into the broader mechanics of galaxy evolution, shedding light on how galaxies like our Milky Way came to be. One of the most intriguing and mysterious cosmic phenomena that further illustrates the vast scale and complexity of galactic dynamics is the Great Attractor. Located in the direction of the Centaurus constellation, approximately 100 million light-years from Earth, the Great Attractor is a massive gravitational anomaly that exerts an immense pull on galaxies within our local supercluster, the Laniakea supercluster. This gravitational force is so strong that it causes galaxies, including our own Milky Way, to move toward this enigmatic center at staggering speeds. The Great Attractor remains a subject of intense investigation in cosmology due to its complex and largely hidden nature. At the heart of the Great Attractor lies a dense concentration of mass, primarily composed of galaxies, gas, and dark matter. Estimates suggest that the mass within this region is several 100,000 times that of our Milky Way, producing a gravitational influence that is profound enough to warp the motion of galaxies across vast stretches of space. This gravitational pull is what drives the motion of galaxies in the region, causing them to converge toward the Great Attractor, as they are affected by the combined gravitational effects of the surrounding mass. However, studying the Great Attractor presents significant challenges for astronomers. The anomaly is located behind the dense plane of our own Milky Way galaxy, which blocks direct observation of many of the galaxies and structures that could help explain what lies at its core. Despite these challenges, astronomers have developed innovative techniques, such as X-ray surveys and redshift measurements, to probe the distribution of galaxies and the associated mass within the region. These techniques offer glimpses into the structure of the Great Attractor, helping to map its gravitational influence across the cosmos. The Great Attractor is part of a much larger cosmic web, a vast, interconnected structure that links galaxy clusters and superclusters throughout the universe. This cosmic web provides further evidence that the universe is not evenly distributed, but rather organized into intricate patterns and structures that are strongly influenced by gravitational forces. As research into the Great Attractor progresses, it may reveal more about the role it plays in shaping the large-scale structure of the universe, including offering new insights into the elusive nature of dark matter and the dynamics of galactic motion. The question of dark matter remains one of the most profound mysteries in astrophysics, yet it is clear that dark matter plays a crucial role in the structure and dynamics of galaxies. Dark matter, which makes up roughly 27% of the universe's total mass, is invisible and undetectable through conventional means. Its presence, however, can be inferred by observing the gravitational effects it exerts on visible matter, such as stars and gas. However, not all galaxies seem to conform to this model. Some galaxies exhibit remarkably low amounts of dark matter, challenging the conventional understanding of how galaxies form and evolve. These galaxies, often referred to as dark matter deficient or dark matter free systems, provide critical insights into the nature of dark matter and its role in galaxy formation. A particular class of dark matter deficient galaxies are dwarf galaxies. These are smaller and less luminous than their larger counterparts, and in some cases they seem to contain only a small fraction of their mass in dark matter. Instead, much of their mass appears to be in the form of visible stars and gas. Researchers speculate that interactions between dwarf galaxies and larger galaxies, particularly through gravitational tidal forces, could explain the absence of dark matter in these systems. For example, if a dwarf galaxy were to merge with a more massive galaxy, the gravitational forces at play could strip the dwarf galaxy of its dark matter content. This process, known as tidal stripping, could alter the distribution of dark matter in the dwarf galaxy, leading to a noticeable deficiency. Alternatively, the formation conditions of these dwarf galaxies may play a role in their lack of dark matter. Cosmological simulations suggest that smaller galaxies, particularly those that formed in less dense regions of the universe, may have experienced weaker gravitational wells during their formative years. As a result, they may not have been able to capture and retain the dark matter that typically surrounds larger galaxies. This offers a fascinating glimpse into how the varied conditions of galaxy formation across the universe can lead to galaxies with unexpected properties, challenging our understanding of dark matter and its role in the evolution of galaxies. These dark matter deficient galaxies remind us that the universe is full of surprises. The mechanisms governing galaxy formation are far more complex than previously thought, and the interactions between matter, gravity, and dark energy continue to unfold in ways that are only beginning to be understood. As astronomers continue to probe the nature of these galaxies and the forces that shape them, they move ever closer to unraveling the deepest mysteries of the cosmos. The role of bionic matter, which includes stars, gas, and dust, is crucial to our understanding of the cosmos. In some galaxies, the observable matter, particularly stars, gas, and cosmic dust, can exert a significant gravitational influence, which may dominate the dynamics of the galaxy. This gravitational pull can obscure the typical signs of dark matter that we usually observe in more familiar galaxies. As a result, in these galaxies, the movement of stars may suggest a lower presence of dark matter than is commonly seen in most spiral or elliptical galaxies. The study of these dark matter deficient galaxies is pivotal, as it deepens our understanding of the universe's structure and sheds light on the role dark matter plays in galaxy formation and evolution. By investigating these unusual galaxies, scientists gain valuable insights into the complex relationship between bionic matter and dark matter, which helps refine our models of galaxy formation and their interaction over cosmic time. One particularly fascinating aspect of this investigation lies in the study of voids, which are vast expanses of space almost entirely devoid of matter. One such void, the Boots void, stands out as one of the largest known voids in the universe. This enormous region stretches across a staggering 100 million light years and is a notable feature of the cosmic landscape. Inside this void, the number of galaxies is dramatically lower than the average density found throughout the universe. This extreme emptiness challenges our conventional understanding of cosmic structure, as galaxies are typically expected to be far more numerous in such large volumes of space. The unusual behavior of galaxies near the edges of the Boots void sparks significant interest. These galaxies exhibit dynamics and distributions that are heavily influenced by the void's unique environment. The absence of a concentrated mass within the void means that the gravitational pull from neighboring cosmic structures is weaker than in more densely packed regions of space. As a result, galaxies on the borders of the void may experience motions that differ significantly from those found in denser clusters. These galaxies are less likely to interact with one another, leading to more independent trajectories and slower merger rates compared to galaxies in denser regions. This intriguing effect is further compounded by the process of cosmic expansion. As the universe continues to expand, regions like the Boots void, with their low density, are subjected to a less intense gravitational pull from the surrounding matter. This weaker gravitational influence can create a phenomenon known as gravitational repulsion, which pushes galaxies outward. Over time, this can lead to an anisotropic distribution of galaxies in the void, where the galaxies on the outer edges are more evenly spaced and less clustered than those found in the denser, more typical regions of space. This uniform spacing is in stark contrast to the dense groupings of galaxies that we observe in other parts of the universe. Another fascinating characteristic of the Boots void is the presence of numerous small, low-mass galaxies. These galaxies are in stark contrast to the massive, luminous galaxy clusters found in denser areas of the universe. The void's emptiness creates an environment where high-density interactions that typically drive star formation and galaxy mergers are rare or non-existent. As a result, star formation within these galaxies is often hindered, and the lack of significant mergers means these galaxies evolve in ways that are distinctly different from their counterparts in more populated regions. The absence of high-density environments within the Boots void shapes the way galaxies within it evolve. This lack of external gravitational forces and the corresponding absence of interactions with other galaxies results in a population of galaxies that may follow a completely different evolutionary path. These galaxies may evolve more slowly, with distinct characteristics that set them apart from galaxies in denser, more interactive environments. Over time, this dynamic could give rise to a population of galaxies with unique properties and behaviors. Exploring the Boots void not only helps to expand our understanding of cosmic structure, but also offers a deeper insight into how galaxies behave in a variety of environments. By studying galaxies that exist in such extreme and unusual conditions, scientists are able to refine our understanding of the forces shaping galaxy formation, evolution, and interaction across the vastness of space. These investigations continue to reveal new complexities in the way galaxies form, develop, and influence the cosmic landscape, offering a glimpse into the future of cosmology and the mysteries of the universe. Exploring the influence of the cosmic void on galactic dynamics provides valuable insights into the formation and evolution of galaxies, offering a deeper understanding of how local conditions can profoundly affect the life cycles of galaxies across the universe. A particularly intriguing class of galaxies that highlight these dynamics are ultra-diffuse galaxies, which defy many of the conventional characteristics that typically define galactic structures. Ultra-diffuse galaxies are remarkably distinct, marked by their extremely low surface brightness and an enormous amount of empty space between the stars. These galaxies are difficult to detect with traditional methods due to their sparse stellar populations spread across vast volumes of space. The result is a faint, diffuse appearance that makes them seem almost invisible against the backdrop of the cosmos. Despite their elusive nature, the processes that govern their formation and survival are crucial for refining our models of galactic evolution. A primary pathway for the creation of ultra-diffuse galaxies involves the interaction and merging of galaxies within the dense environments of galaxy clusters. When galaxies collide, the gravitational forces between them can trigger dramatic changes in their structure. These interactions can strip away gas and stars from the galaxies, and in some cases, this leads to the dispersion of stars into a much larger, more diffuse formation. This process often transforms previously compact galaxies into ultra-diffuse ones, especially as star formation slows down or ceases altogether. As a result, these galaxies lose their once bright features, becoming faint and spread out over vast areas of space. One of the most striking characteristics of ultra-diffuse galaxies is their low mass and small amounts of dark matter. Dark matter, which constitutes a significant portion of a galaxy's mass and is crucial for its gravitational stability, is typically sparse in these galaxies. This lack of dark matter means that ultra-diffuse galaxies do not possess the intense gravitational forces needed to hold their structures together tightly. As a consequence, their stars remain dispersed, and these galaxies do not collapse or fragment as quickly as more conventional galaxies. This weak gravitational cohesion allows them to persist for much longer periods, even while interacting with other galaxies within a cluster, where gravitational tides might otherwise disrupt their stability. Interestingly, ultra-diffuse galaxies can also thrive in low-density environments, where they are less likely to engage in interactions with other galaxies. In such regions, their sparse nature can be maintained without the risk of disruption. This observation suggests that ultra-diffuse galaxies can adopt a variety of forms depending on their environment and interactions, revealing that galaxies are not static entities, but instead evolve in response to the gravitational landscapes they inhabit. The study of ultra-diffuse galaxies is essential for understanding the broader spectrum of galactic types and their evolutionary pathways. These galaxies provide valuable clues about the conditions under which galaxies can continue to exist and even thrive despite their low density. They also raise important questions about the processes that govern star formation in galaxies that are so diffuse. By studying these enigmatic galaxies, scientists can enhance their understanding of galactic diversity and the wide range of evolutionary outcomes that can arise in different cosmic settings. In addition to ultra-diffuse galaxies, another intriguing phenomenon in galactic studies are the high-velocity clouds, HVCs, found near the Milky Way. These clouds, composed primarily of neutral hydrogen, are characterized by their unusual velocities that do not conform to the expected motions of stars and gas within the galactic disk. Their peculiar velocities present an exciting opportunity for astronomers to explore the complex interactions and processes occurring within the Milky Way and its surrounding environment. One prominent theory regarding the origin of high-velocity clouds posits that they are remnants of material that was ejected from the Milky Way as a result of various dynamic processes. Supernovae, which occur at the end of a massive star's life cycle, are one such process. The explosion of a supernova releases an immense amount of energy, which can expel gas and dust into space at high velocities. This material, moving at great speeds, can form clouds that are observed far from their original locations within the galaxy. Another possibility is that these high-velocity clouds are primordial structures, remnants from the early universe that were captured by the Milky Way's gravitational pull after the galaxy itself had formed. These primordial clouds might consist of gas that contributed to the formation of stars, but never fully integrated into the galactic disk or stellar population. Instead, they remain as clouds within the galactic halo, exhibiting high velocities as they orbit the center of the Milky Way. Whether ejected by dynamic events or remnants of the early universe, high-velocity clouds offer a fascinating glimpse into the diverse processes at work in and around galaxies. The study of high-velocity clouds, much like the investigation of ultra-diffuse galaxies, enhances our understanding of galactic dynamics and evolution. Both phenomena push the boundaries of our knowledge about the complex processes that shape galaxies and their environments. By investigating these structures, we gain a clearer picture of how galaxies form, interact, and evolve, unveiling the many forces that govern the cosmos on both large and small scales. High-velocity clouds, HVCs, cannot be fully isolated from their interactions with neighboring galaxies and their larger cosmic environment. The Milky Way, as part of an expansive cosmic web, is far from an isolated system. Instead, it is deeply connected to its surrounding universe through a complex network of gravitational forces that influence its structure, movement, and evolution. The interactions between galaxies are multifaceted. Galaxies can collide, merge, and exert tidal forces on one another. Smaller galaxies or intergalactic gas clouds also play a significant role in shaping the behavior and dynamics of these high-velocity clouds. These interactions are not merely passive. They actively contribute to the formation and movement of HVCs, making them crucial for our understanding of galaxy evolution. As astronomers study these clouds, they uncover vital information about the Milky Way's history. By exploring the movement of gas and the formation of stars, they are able to reconstruct the dynamic processes that govern the galaxy. These studies offer a glimpse into the complex relationships between galaxies and their environments, revealing the interconnected nature of the universe. Each new discovery about high-velocity clouds adds another layer to our understanding of how galaxies evolve and interact over cosmic time. These clouds act as cosmic time capsules, carrying the history of the Milky Way's evolution and interactions with its neighboring galaxies. By studying them, astronomers gain crucial insights into the forces that shape galaxies and their continuous transformation over billions of years. One of the most captivating phenomena in galactic dynamics is the formation of ring-like structures within galaxies. These rings are often the result of intense gravitational interactions typically caused when two galaxies collide or pass closely by each other. The immense gravitational forces involved in such interactions can significantly distort the shapes of the galaxies. As a result, gas and stars can be stripped from the galaxies, and the remaining matter may be twisted into a ring shape, giving rise to these stunning formations. A striking example of this phenomenon is the Cartwheel Galaxy, a well-known spiral galaxy that showcases a brilliant, prominent ring structure formed by a collision with a smaller galaxy. This collision has left behind a visually stunning, perfectly symmetrical ring of stars and gas, offering a vivid reminder of the powerful forces at work in the universe. But gravitational interactions aren't the only mechanism responsible for the formation of ring-like structures. Another key theory is the density wave theory, which explains how these rings can form as a natural consequence of a galaxy's rotation. As a galaxy spins, certain areas within it may experience higher densities of stars and gas. These regions, known as density waves, are often concentrated in rings that orbit the galaxy's center. This process creates a resonant pattern, much like the ripples of a pebble in a pond, where the distribution of stars and gas within the spiral arms of the galaxy becomes more concentrated, forming a ring of stars that becomes clearly visible when observed from afar. Additionally, ring structures can evolve over time as galaxies age. Internal processes, such as stellar formation and the movement of gas, continually reshape the galaxy. Over billions of years, these changes can lead to the formation of distinctive features like rings, which are composed of young, hot stars formed from accumulated gas. These stellar populations are often short-lived, but they reveal important information about a galaxy's ongoing evolution and the stages of its life cycle. By studying these rings, astronomers can piece together the history of galaxies, learning how they interact with their surroundings and how they evolve through time. Each ring structure is a snapshot, capturing a unique moment in the life of a galaxy and offering crucial clues about its past, present, and future. These cosmic features not only highlight the diversity of shapes found in galaxies, but also underscore the dynamic, ever-changing nature of the universe itself. In a different corner of the night sky, a curious phenomenon has caught the attention of both amateur stargazers and professional astronomers alike: the dimming of Betelgeuse, a red supergiant star located in the constellation Orion. Over recent years, Betelgeuse has exhibited a dramatic dimming, sparking widespread speculation about the star's future. What is behind this sudden drop in brightness? The dimming of Betelgeuse is the result of several interconnected factors, one of the most prominent being the star's natural variability. Betelgeuse is classified as a semi-regular variable star, which means its brightness fluctuates over a period of several months or even years. This variability is a natural part of its life cycle, stemming from pulsations in the star's outer layers. These pulsations cause the star to expand and contract, altering the amount of light it emits. Consequently, these changes in size lead to fluctuations in the star's observed brightness from Earth. However, recent observations suggest that there may be an additional cause behind the star's dimming. As Betelgeuse undergoes changes in its outer layers, it produces and expels vast amounts of gas. This gas can cool and condense into dust particles, which, when dispersed, partially obscure the star's light. As these dust clouds accumulate around the star, they can significantly reduce the amount of visible light we receive from Betelgeuse, giving it a dimmer appearance. This dust formation is a normal aspect of a star's evolution. It is an indication that Betelgeuse is in the later stages of its life cycle, preparing to undergo the dramatic transformation that will eventually lead to a supernova explosion. While Betelgeuse is indeed nearing the end of its life, the idea that it will go supernova in the near future is more complicated. Although the star has exhausted much of its nuclear fuel and is entering the final phases of stellar evolution, it is likely still hundreds of thousands, if not millions, of years away from its explosive demise. In the grand cosmic scheme, the fate of Betelgeuse is just one piece of a much larger narrative, one that we can only begin to comprehend as we continue to study the stars and the processes that govern their birth, life, and death. The dimming of Betelgeuse offers a poignant reminder of the transitory nature of stars and the cosmic cycles that shape the universe. High-velocity clouds, HVCs, are not isolated entities. They cannot be fully understood without considering their interactions with other galaxies in the wider cosmos. The Milky Way, as part of an immense and interconnected cosmic web, is constantly affected by gravitational forces from its neighboring galaxies. These forces are not just distant, passive influences. They actively shape the structure and behavior of the Milky Way. Galaxy collisions, tidal interactions, and mergers with smaller galaxies or even intergalactic gas play crucial roles in the formation and dynamics of high-velocity clouds. The study of these clouds has revealed important insights into the Milky Way's intricate behavior, shedding light on the larger mechanisms of galaxy evolution. By analyzing these clouds, astronomers are not just exploring the present state of our galaxy, but also peering into its past. They can trace the flow of gas, track the formation of stars, and even understand how the Milky Way has interacted with its surrounding environment over billions of years. These interactions, both with nearby galaxies and with the diffuse gas of the intergalactic medium, help define the processes that govern the evolution of galaxies in the universe. One of the most fascinating aspects of galaxy evolution is the phenomenon of ring-like structures. These circular formations are often the direct result of gravitational interactions between galaxies. When two galaxies collide or pass by each other, their enormous gravitational fields can distort their shapes. This can cause stars and gas to be stripped away, while the remaining matter gets twisted and pulled into a ring shape. A prime example of this cosmic ballet is the Cartwheel Galaxy, which boasts a stunning ring structure formed by a collision with a smaller galaxy. However, not all ring-like structures in galaxies are the result of collisions. Another explanation comes from the density wave theory, which posits that as a galaxy rotates, certain regions of higher density emerge. These areas, where stars and gas are concentrated, can form rings as they orbit the galaxy's center, creating a resonant pattern within the spiral arms. These dense regions, rich in young, hot stars, can be vividly observed as rings, offering astronomers a snapshot of the galaxy's dynamic and ever-changing nature. Some ring structures are the product of a galaxy's own internal evolution. Over time, as a galaxy ages, internal processes like stellar formation and gas movement can lead to distinctive patterns, including the formation of rings. These rings are often composed of young, hot stars born from the accumulation of gas. By studying these evolving ring structures, astronomers gain valuable insights into the life cycle of galaxies, uncovering the ways in which galaxies evolve and change over vast cosmic timescales. Each of these ring-like structures is more than just an aesthetic feature. It's a crucial piece of the puzzle that helps scientists understand the broader narrative of galaxy formation and evolution. Every ring is like a page in the history book of the cosmos, telling a story of galactic interactions, stellar birth, and the ever-changing forces that shape our universe. Meanwhile, another captivating phenomenon has been unfolding in the constellation Orion. Betelgeuse, a red supergiant star, has recently been dimming, capturing the attention of both amateur stargazers and professional astronomers alike. This dimming, while noticeable, is not entirely out of the ordinary. Betelgeuse, known to be a semi-regular variable star, exhibits changes in brightness that occur over months and even years. These fluctuations are often caused by pulsations in the star's outer layers, which cause it to expand and contract, altering its luminosity in the process. In addition to these natural variations, another factor contributing to the star's recent dimming is the formation of dust. As Betelgeuse undergoes changes in its outer layers, it ejects large amounts of gas. When this gas cools, it can condense into dust particles that obscure the star's light, making it appear dimmer from Earth. This dust formation is part of the natural life cycle of massive stars and signals the ongoing changes taking place in Betelgeuse's outer atmosphere. But the big question on everyone's mind is whether Betelgeuse is on the verge of exploding as a supernova. While the star is indeed nearing the end of its life, scientists estimate it could still be hundreds of thousands, if not millions of years before that happens. Betelgeuse has already exhausted much of its nuclear fuel and is in the late stages of stellar evolution, but predicting the exact timing of a supernova remains an incredibly difficult task. When it does eventually explode, however, it will likely be a spectacular event. The explosion could be brighter than the full moon, visible even during the day, offering an unforgettable spectacle for anyone lucky enough to witness it. Despite the uncertainty surrounding the timing of Betelgeuse's supernova, its current behavior is a rich subject of study. By understanding the processes that are influencing the star's dimming and evolution, astronomers gain a deeper understanding of the life cycles of similar stars and the violent ends they eventually meet. The study of Betelgeuse provides crucial insights into the dynamics of massive stars, helping scientists piece together the complex processes that govern their birth, life, and explosive deaths. On a different note, there's another star that has caught the imagination of astronomers: Tabby's star, or 846852. This star has been the subject of much fascination due to its highly irregular and mysterious dimming patterns. Unlike typical variable stars, which exhibit predictable and rhythmic changes in brightness, the dimming of Tabby's star occurs in an erratic and unpredictable fashion. This irregular behavior has sparked numerous theories about its cause. One of the most widely discussed theories is that a swarm of comets could be responsible. The idea is that a group of comets is passing in front of the star, temporarily blocking its light and creating the observed dimming. As the comets approach the star, their icy bodies release dust, which forms a cloud that obscures the star's light. This would explain the star's erratic dimming and brightening. Another more speculative theory suggests the possibility of an alien megastructure orbiting the star. According to this idea, advanced civilizations might have constructed enormous structures to harness the energy of the star, which could account for the unusual dimming patterns. While this theory has captured the public's imagination, it remains highly speculative, and astrophysicists consider it far less likely than natural explanations. Other hypotheses focus on the star itself. It's possible that changes in the star's atmospheric conditions, such as sunspot-like activity, could cause variations in its brightness. Alternatively, the star might be undergoing intrinsic changes in luminosity as part of its natural evolution. Regardless of the cause, the mystery surrounding Tabby's star serves as a powerful reminder of how much we still have to learn about the life cycles of stars and the complex processes occurring in the universe. Finally, we come to the theoretical concept of Thorne-Zetko objects, TZOs, named after the physicists Kip Thorne and Anna Zetko. These hypothetical stellar structures represent a fascinating challenge to our understanding of stellar evolution. A Thorne-Zetko object is theorized to form when a neutron star becomes embedded within the outer layers of a red supergiant star. This unusual scenario arises when a massive star exhausts its nuclear fuel and expands into a red supergiant. If the star undergoes a supernova explosion, leaving behind a neutron star, the neutron star could potentially be captured by the gravitational field of the supergiant, becoming immersed in its outer layers. This interaction creates a dynamic and unique relationship between two very different stellar objects. The neutron star's gravitational influence would continue to shape the material surrounding it, creating an intriguing and complex system within the supergiant's outer envelope. While no Thorne-Zetko objects have yet been observed, their theoretical existence pushes the boundaries of our understanding of stellar evolution and the diverse phenomena that can occur in the life cycles of the most massive stars. In all of these cases, whether it's high-velocity clouds, ring-like galaxy structures, the dimming of Betelgeuse, the mystery of Tabby's star, or the theoretical Thorne-Zetko objects, we are constantly reminded of the vastness and complexity of the universe. Each new discovery, each puzzle unraveled, brings us one step closer to understanding the forces that shape the cosmos, yet it also reveals how much we still have to learn. The universe, in all its beauty and mystery, remains an endless source of wonder and curiosity. One of the most captivating aspects of astronomical phenomena is the potential for unusual nuclear processes occurring in exotic objects like the Thorne-Zetko. The presence of a neutron star within such an object can trigger an environment where nuclear reactions occur at an accelerated rate. These reactions, in turn, can lead to the production of a wide range of elements and may even cause alterations in the star's luminosity and temperature. These changes challenge conventional understandings of stellar behavior, providing a theoretical foundation for how these objects could appear fundamentally different from typical stars in their surroundings. As of now, no confirmed Thorne-Zetko object has been detected, but astronomers continue to search the cosmos in the hope of finding these elusive entities. Detecting such objects would not only revolutionize our understanding of stellar formation and death, but also deepen our knowledge of the intricate relationships between different celestial bodies. The very idea of stars within stars stretches the boundaries of what we consider stellar phenomena, offering a glimpse into the profound diversity of the universe. One intriguing class of objects that have captured the attention of astronomers is the blue straggler stars, which are often found in globular clusters. These stars stand out as younger, bluer stars in an environment that is typically filled with older, cooler stars. Their apparent youthfulness has puzzled astronomers for decades, prompting several theories to explain how they maintain their vibrant characteristics in the face of the aging stellar population around them. One widely accepted explanation revolves around stellar mergers. Globular clusters, which are dense collections of stars, can cause stars to come into close proximity to one another, setting the stage for interactions that may lead to collisions. When two stars merge, the result is often a more massive star, one that burns through its fuel much faster than its neighbors. This accelerated burning process not only makes the star shine brighter and hotter, but it also explains why blue straggler stars appear blue. Larger stars tend to emit more light in the blue and ultraviolet spectra, thus giving them their distinctive color. Another factor that contributes to the blue straggler phenomenon is the complex dynamics of binary star systems. Many stars and globular clusters exist in binary pairs, and in such configurations, mass transfer can occur between the two stars. In a binary system, a more massive star can siphon hydrogen-rich material from its less massive companion. As the receiving star gains additional mass, it may reignite nuclear fusion within its core, effectively rejuvenating it. This process allows the star to shine brightly, appearing younger than its true age. The dynamics of stellar interactions within globular clusters are crucial to understanding the formation and survival of blue straggler stars. These densely packed environments foster conditions that allow for unusual evolutionary pathways, diverging from the more typical processes observed in isolated regions of space. Consequently, blue straggler stars not only provide important insights into stellar evolution, but they also highlight the intricate and often surprising interactions between stars in crowded cosmic environments. As astronomers continue to study these fascinating objects, they uncover more about the forces that shape the life cycles of stars and the evolutionary pathways that lead to the creation of such extraordinary celestial bodies. Meanwhile, Cepheid variable stars present yet another captivating feature of the cosmos, especially in terms of their ability to aid in measuring cosmic distances and helping to map the scale of the universe. Known for their intense pulsations, Cepheid variables undergo regular cycles of expansion and contraction, driven primarily by changes in pressure and temperature within their cores, which are influenced by nuclear fusion. The pulsations of these stars result in periodic variations in their brightness, and these variations have proven to be invaluable tools for astronomers. At the heart of the pulsations seen in Cepheid variable stars is a delicate balance between opposing forces. On one hand, the force of gravity pulls the star's outer layers inward, while on the other, the outward pressure generated by nuclear fusion in the star's core resists this contraction. As the core of the star heats up and energy is released through fusion, the outer layers of the star begin to expand. As they expand, the temperature and pressure in the star's outer regions drop, causing a decrease in the outward pressure. This loss of pressure can no longer support the weight of the outer layers, and gravity forces them to contract. As the star contracts, the temperature within the core increases once more, reigniting nuclear reactions, and the cycle begins again. The detailed mechanics behind these pulsations are best understood through the theory of stellar dynamics, particularly the opacity mechanism. This theory explains how energy is transported through the different layers of a star. As the temperature in the outer layers changes, so does the opacity, a measure of how easily energy can escape. When the outer layers expand, the opacity decreases, which allows more energy to escape. When the star contracts, the opacity increases, trapping energy within the star and causing the temperature to rise again. These intricate processes drive the pulsations that make Cepheid variables so unique, and they play a critical role in helping astronomers gauge distances across the cosmos, ultimately helping us better understand the vast scale of our universe. In summary, the exploration of these diverse stellar phenomena, from the neutron-rich environments of Thorn-Zitkow objects to the dynamic processes at work in blue straggler stars and Cepheid variables, offers us an ever-deepening understanding of the complexities of our universe. Each of these objects challenges and enriches our knowledge of how stars evolve, interact, and illuminate the path forward for our studies of the cosmos. Through these enigmatic stars, we can glimpse the intricate, interconnected web of forces that govern the behavior of celestial bodies, revealing the stunning diversity and complexity of the universe itself. Conversely, during the process of stellar contraction, energy becomes trapped within the core, resulting in a buildup of pressure. This pressure continues to increase until it reaches a critical point where it forces the outer layers of the star to expand once again. The duration it takes for a Cepheid variable star to complete one full cycle of pulsation is directly tied to its luminosity. This relationship between the pulsation period and the brightness of these stars became a pivotal discovery, famously utilized by the astronomer Henrietta Leavitt in the early 20th century. Her groundbreaking work formed the cornerstone of modern astronomical distance measurement, providing a method to calculate distances across the universe with remarkable accuracy. Observations of the pulsation period luminosity relationship have since played a key role in helping astronomers determine the distances to far-off galaxies. These observations not only illuminate the vast expanses of space, but they also offer critical insights into the expansion of the universe itself, a revelation that has reshaped our understanding of cosmology. The remarkable pulsation cycle of Cepheid variables serves as more than just a clock to measure time. It acts as a cosmic beacon, guiding our exploration of the universe's vast mysteries. One such fascinating example of this cosmic phenomenon is Mira, a red giant star located in the constellation Cetus. Mira presents an unusual and captivating sight, a comet-like tail, a result of its unique stellar characteristics and behavior, as it nears the final stages of its evolution. As Mira exhausts its nuclear fuel and transitions into a later stage of stellar life, it begins to lose mass at an accelerating rate. This mass loss is primarily driven by a powerful stellar wind, a steady stream of particles being expelled from the outer layers of the star. As Mira sheds its outer atmosphere, this ejected material interacts with the surrounding interstellar environment, forming a long, glowing trail of gas and dust. The composition of this material is rich in gases and dust particles, and as Mira progresses through its life cycle, this material is carried away, creating an extended tail that stretches across the cosmic void. The appearance of this tail is influenced by several factors: the velocity of the stellar wind and the density of the surrounding interstellar medium play a major role in determining how the tail forms and extends. Mira's motion through space also contributes to the development of its comet-like tail. As the star moves, it carries with it the material that has been expelled by the stellar wind. When the stellar wind collides with the interstellar medium, the stream of gas and dust is shaped into a tail that extends away from the star's direction of motion. This is similar to how a comet's tail forms as it approaches the sun and is swept backward by the solar wind and radiation. The presence of this tail not only signifies the ongoing mass loss experienced by aging stars, but also offers a deeper insight into the fundamental processes of stellar evolution. Studying stars like Mira provides astronomers with a valuable understanding of the final stages of stellar life. It helps us unravel the transformation processes that lead to the creation of planetary nebula, an intermediate phase in the life cycle of stars, where ejected material contributes to the formation of new stars and planets. This intricate dance of life and death among the stars highlights the dynamic and interconnected nature of stellar evolution, which in turn plays a crucial role in the broader processes of cosmic creation and destruction. In a similarly remarkable realm of stellar phenomena, hypervelocity stars represent one of the most extreme and awe-inspiring phenomena in the universe. These stars travel through space at velocities so high that they are capable of escaping the gravitational pull of our Milky Way galaxy. Their speeds can exceed 1 million miles per hour, placing them among the fastest moving objects in the universe. The origins of hypervelocity stars can be traced to various astrophysical processes, with interactions involving supermassive black holes being one of the most significant contributors. One of the leading theories behind the formation of hypervelocity stars involves gravitational encounters with supermassive black holes. At the heart of most galaxies lies a supermassive black hole, and in the case of our own galaxy, it resides in the center, where it exerts an immense gravitational influence. During certain interactions, a star in a binary system can be drawn into the black hole's vicinity, often entering a highly elliptical orbit around it. The gravitational pull of the black hole can dramatically alter the fates of both stars in the system. If one star is bound to the black hole, the other can be flung outward at an incredibly high velocity, escaping the galaxy entirely and becoming a hypervelocity star. Another mechanism for the creation of hypervelocity stars is the merging of binary star systems. When two stars in a binary system come close enough to one another, the gravitational forces between them can become so intense that one star is ejected from the system at tremendous speed, while the other is pulled into the black hole. This violent process not only offers insight into the dynamics of binary star systems, but it also provides valuable information about the behavior of stars in densely packed environments, such as globular clusters. Additionally, research has shown that hypervelocity stars can also be formed through dynamic interactions within star clusters. In these dense environments, close encounters between stars can lead to one or more stars being ejected into space at high velocities. These fast-moving stars leave behind a trail of stellar debris, providing a fascinating glimpse into the dramatic interactions that occur in the crowded regions of the universe. The study of hypervelocity stars not only enhances our understanding of stellar dynamics and the behaviors of stars under the influence of powerful gravitational forces, but also raises intriguing questions about the structure of our galaxy and the future of these cosmic travelers. As we observe these extraordinary stars, we begin to piece together the complexities of the universe's most extreme and dynamic phenomena. Hypervelocity stars stand as a testament to the incredible forces at work in the universe and the ways in which these forces shape the stars, galaxies, and the very fabric of space itself. As they venture through the vast expanse of intergalactic space, hypervelocity stars continue to unveil the intricate and ever-changing processes that shape our cosmos. Among the many celestial phenomena, binary star systems stand out due to their fascinating and complex nature. A binary star system consists of two stars bound by mutual gravity, orbiting each other in a delicate and intricate dance. These systems are not only intriguing in their own right, but also serve as cosmic laboratories, offering a unique window into the deeper workings of stellar evolution, mass transfer, and gravitational interactions. Binary stars engage in a variety of interactions, but one of the most captivating processes involves the transfer of mass between the two stars. This mass exchange is particularly prominent when one of the stars in the system evolves into a red giant, a phase in which it expands dramatically. If the stars are close enough, the gravitational forces at play can pull material from one star and deposit it onto the other. This transfer of mass is facilitated by the formation of an accretion disk, where gas, dust, and stellar material from the expanding star spiral around the companion slowly being absorbed. The details of how mass is transferred from one star to another are governed by the characteristics of the stars themselves. Factors such as temperature, mass, and the distance between the stars play crucial roles in determining the efficiency of this process. As one star approaches the later stages of its life cycle, its outer layers become increasingly tenuous, and if it is in close proximity to its companion, the gravitational forces between the two stars can cause the larger star to lose material. This loss often takes place in the form of gas and dust that flows toward the smaller star, forming an accretion disk that spirals inward, gradually consuming the material. This process of mass transfer can have profound and far-reaching effects on the stars involved. One of the most fascinating outcomes of mass transfer is the rejuvenation of the receiving star. The material it gains, often hydrogen-rich gas, reignites nuclear fusion within the star's core, effectively resetting its stellar clock and giving it a second life. This phenomenon is most notable in the creation of blue straggler stars, which appear hotter and younger than their neighbors, despite having formed at an earlier stage. These stars, born from the mass transfer process, are often more massive than typical stars of their age and radiate with an intensity that belies their true age. However, mass transfer is not without its dangers. In some cases, it can destabilize the binary system. If one star accumulates too much mass, it can alter the gravitational balance between the two stars, leading to dramatic changes in their orbital dynamics. In the most extreme cases, one star may be stripped of its outer layers entirely, leaving behind a stripped-down remnant. When mass transfer occurs rapidly, it can lead to explosive events such as novae or even supernovae. For example, when a white dwarf accumulates enough mass from its companion star to reach a critical threshold, it can trigger a catastrophic explosion, releasing an immense amount of energy. The study of mass transfer in binary systems is essential for understanding the broader picture of stellar evolution. These interactions not only shed light on the life cycles of individual stars, but also reveal how stars in binary systems influence each other, often altering the fate of both. Through the lens of mass transfer, we gain insights into the dynamic processes that drive the evolution of galaxies themselves. Another captivating aspect of stellar life is the study of B stars, massive stars known for their rapid rotation rates and the presence of equatorial gas disks. These stars, which are often among the most luminous and massive in the galaxy, are subject to a variety of fascinating dynamics that influence their rotation and overall evolution. The rapid rotation of B stars can be traced back to their formation processes. As a molecular cloud collapses under its own gravity to form a star, the material within the cloud conserves angular momentum. Much like a figure skater pulling in their arms to spin faster, this conservation of angular momentum causes the nascent star to spin at increasingly higher speeds. Throughout their life cycle, B stars maintain these high rotation rates, largely due to their relatively low mass loss compared to other massive stars. While many stars expel large amounts of material over their lifetimes, B stars do not lose mass at the same rate. This is partly because of their high rotational speeds, which allow them to hold on to their outer layers more effectively. Additionally, the presence of an equatorial disk, formed from material shed from the star's outer layers, plays a significant role in influencing the star's rotation. This disk of gas can interact with the star's angular momentum, allowing it to sustain its rapid spin. The dynamics of B stars are further complicated by their interactions with the surrounding environment. For example, when B stars are part of a binary system or experience close encounters with other stars, angular momentum can be exchanged, potentially increasing the speed of rotation even further. This exchange of momentum, combined with the accretion of gas and the dynamics of circumstellar disks, creates a complex environment that allows B stars to maintain their high rotational velocities throughout their lives. The study of B stars offers valuable insights into the broader processes of stellar dynamics and evolution. The rapid rotation of these stars, combined with their interactions with companion stars and the presence of circumstellar material, provides important clues about the forces that shape massive stars. By understanding the evolution of B stars, we gain a deeper understanding of the processes that govern the formation and evolution of stars, not only in our galaxy, but in galaxies across the universe. Massive stars, those with initial masses greater than approximately 8 times that of the Sun, are some of the most energetic and fascinating objects in the universe. These stars generate vast amounts of energy through the process of nuclear fusion in their cores. This fusion process creates an immense outward pressure, radiation pressure, generated by the energy emitted as light and other forms of radiation. Radiation pressure acts outward, counteracting the inward pull of gravity that would otherwise cause the star to collapse. Despite the immense outward pressure exerted by the radiation produced in their cores, massive stars must maintain a delicate balance between this radiation pressure and the gravitational pull of their own mass. This balance is known as hydrostatic equilibrium. In the early stages of a massive star's life, hydrogen is fused into helium in the core, and the radiation pressure generated by these fusion reactions is sufficient to counteract gravity, keeping the star stable. However, as the star consumes its hydrogen fuel, it begins to fuse heavier elements such as helium into carbon and oxygen, and eventually heavier elements such as neon, magnesium, and silicon. With each successive fusion process, the temperatures and pressures within the star's core increase, enabling it to sustain the radiation pressure necessary to maintain hydrostatic equilibrium. These complex processes allow massive stars to maintain their stability over the course of millions to billions of years. Ultimately, however, when a massive star runs out of fuel, it will undergo dramatic transformations, potentially leading to explosive end stages like supernovae, further enriching the surrounding interstellar medium with heavy elements that are crucial for the formation of new stars, planets, and even life itself. The study of these massive stars from their formation to their explosive deaths provides invaluable insights into the forces that drive stellar evolution. It also highlights the interconnectedness of all elements in the universe, as the death of one star often leads to the creation of the conditions necessary for new life, continuing the cosmic cycle of birth and rebirth in the ever-expanding universe. As massive stars approach the later stages of their life cycles, they undergo profound transformations that shape their very structure. These stars, in their evolutionary dance, often develop a complex, multi-layered interior. At the heart of the star lies a core rich in elements like iron, where fusion reactions, responsible for generating the star's energy, slow and eventually cease altogether. This shift marks a critical point in the star's evolution as it begins to lose the ability to sustain itself through fusion in its core. However, the outer layers of the star are a different story. These layers, composed primarily of lighter elements, continue to undergo fusion, producing vast amounts of energy. The fusion occurring at varying depths within the star works as a kind of internal regulator, balancing the opposing forces of radiation pressure pushing outward and gravity pulling inward. This delicate equilibrium is crucial, as it allows the star to maintain stability despite the ongoing changes in its structure as it nears the end of its life. A key player in this dynamic balance is the mass loss that occurs through intense stellar winds. These powerful outflows of gas not only strip away the star's mass over time, but also play a pivotal role in stabilizing the star. As a massive star loses mass, its overall gravitational pull weakens, reducing the tension between gravity and radiation pressure. In effect, the reduction in mass helps ease the competition between these two forces, further contributing to the star's stability. Stellar winds also carry away vast amounts of energy, helping to modulate the radiation pressure that would otherwise grow uncontrollably. Although mass loss carries its own risks, it is this very process that allows massive stars to avoid the catastrophic collapse that could otherwise occur. These finely tuned mechanisms of mass loss and internal fusion processes help massive stars avoid immediate destruction, ensuring they shine brightly for millions of years. Ultimately, their incredible life cycles culminate in awe-inspiring events such as supernova explosions. These spectacular endings mark the conclusion of the star's evolution, leaving behind a lasting imprint in the universe. The processes governing the life and death of these stellar giants demonstrate the intricate interplay between gravity, temperature, and fusion. Together, they illustrate the dynamic, ever-changing nature of stellar evolution and the forces that shape it. Turning to another intriguing celestial phenomenon, we encounter the enigmatic class of exoplanets known as hot Jupiters. These gas giants are remarkable not only for their immense size, but also for their extraordinarily close orbits around their parent stars, often far closer than Mercury's orbit around the Sun. The presence of these planets in such tight orbits presents a challenge to traditional models of planet formation, prompting astronomers to reconsider how such massive planets could have formed in the first place. Initially, the formation of hot Jupiters was thought to follow the same basic process as other gas giants, relying primarily on the core accretion model. In this process, a protoplanetary disk of gas and dust surrounds a young star. Through a series of collisions and coalescences, solid particles gradually come together to form larger and larger bodies, eventually creating a substantial core. Once the core becomes sufficiently massive, it begins to attract surrounding gas, growing into a full-fledged gas giant. However, traditional models expected gas giants like Jupiter to form farther from their stars, in the cooler regions of the protoplanetary disk, not so close as to become hot Jupiters. To explain the presence of these close-orbiting giants, astronomers have proposed the idea of planetary migration after formation. This migration could occur through several mechanisms, with the most widely discussed involving interactions between the newly formed planet and the gas in the surrounding protoplanetary disk. As the planet moves through the disk, it generates waves within the gas, transferring angular momentum and causing the planet to spiral inward toward its star. This process can be remarkably swift, allowing the planet to settle into a tight orbit in a relatively short time frame. Another potential explanation for the existence of hot Jupiters lies in gravitational interactions with other bodies in the protoplanetary disk. In systems where multiple planets are forming simultaneously, close encounters or mutual gravitational interactions can lead to what is known as planet-planet scattering. In this scenario, the orbits of the planets can be drastically altered, with the hot Jupiter being nudged into a closer orbit, while the other planets may be sent outward into more distant paths. This chaotic interaction provides a plausible route for these massive planets to end up in orbits much closer to their stars than originally expected. Together, these discoveries and theories offer a fascinating glimpse into the complexity of planetary formation and migration. They challenge our understanding of the processes that govern the birth of planetary systems, providing new insights into the dynamic nature of the cosmos. Through the study of hot Jupiters and the stellar giants from which they may have originated, astronomers continue to unravel the mysteries of the universe, one cosmic phenomenon at a time. In the intricate dance of stellar systems, the presence of a binary star system can significantly enhance the migration of planets, particularly when a hot Jupiter resides within it. These binary systems, with their dual gravitational pull, can shepherd such gas giants inward, nudging them closer to their host stars. This gravitational influence can result in the planet's orbit shrinking over time, bringing it into a dangerously close proximity to its stellar companion. The study of hot Jupiters, which are gas giants orbiting extremely close to their stars, offers profound insights into the processes of planetary formation and migration. These planets, which defy traditional expectations of planetary positioning, continue to raise questions about the very forces that drive the development of planetary systems. Their unusual orbits suggest that migration can occur in unexpected ways, fundamentally reshaping our understanding of planetary evolution. The existence of these gas giants challenges conventional models of planetary formation, indicating that other factors might be at play during the early stages of planetary development. Investigating hot Jupiters is not just about understanding these extreme planets themselves, but also about unveiling the mechanisms that drive planetary migration and the forces shaping entire star systems. Hot Jupiters provide a natural laboratory for studying these phenomena, continuing to be a key focus in the search for exoplanets beyond our solar system. Among the myriad of exoplanets discovered, some exhibit an even more fascinating phenomenon: retrograde orbits. These planets orbit their stars in the opposite direction to their star's rotation, an intriguing anomaly that has led to intense scrutiny among astronomers. The reasons behind retrograde orbits are varied, often stemming from complex gravitational interactions and chaotic dynamics that occur during the formation and evolution of planetary systems. One common explanation involves interactions with other massive bodies in multi-planet systems. During the early stages of planetary formation, a disk of gas and dust surrounds a young star. In such an environment, the gravitational influence of neighboring planets can be significant enough to alter a newly formed planet's orbit. These interactions can result in energy being transferred between planets, flipping the direction of a planet's orbit, sometimes even causing it to rotate in the opposite direction of its star. Another possible cause of retrograde motion is a close encounter with a neighboring star or a binary star system. When another star passes close enough, the gravitational forces involved can drastically alter the orbits of the planets in the system. In some cases, this results in the ejection of a planet from its system, or, more dramatically, forces it into a retrograde orbit. Such perturbations are more common in dense stellar environments, like globular clusters, where close stellar encounters are frequent. In addition, some retrograde exoplanets may have formed in these unusual orbits from the very beginning. This could be due to the asymmetric distribution of material in the protoplanetary disk, or the turbulence within it, causing planets to form on orbits that are not aligned with the rotation of the star. The existence of retrograde exoplanets, though rare, gives astronomers critical insights into the complex and chaotic nature of planetary dynamics. By studying these planets, we can refine our models of planetary formation and migration, ultimately enhancing our understanding of how planetary systems evolve under different conditions. Super-Earths, another fascinating category of exoplanets, are worlds that are larger than Earth but significantly smaller than Neptune or Uranus. These planets typically have masses ranging from 1 to 10 times that of Earth. The formation of super-Earths provides an intriguing window into the processes that govern planetary development, offering a stark contrast to the conditions seen in our own solar system. Like other terrestrial planets, super-Earths are believed to form through a process known as core accretion. In the early stages, a cloud of gas and dust known as a protoplanetary disk surrounds a young star. Solid particles in the disk collide and clump together, forming planetesimals. These planetesimals in turn collide and merge to create larger bodies, eventually forming the cores of new planets. The formation of super-Earths likely takes place in regions of the protoplanetary disk that have the right conditions, sufficient material in the right temperature and pressure regimes, allowing for the accretion of large, rocky planets. Once a solid core forms, it may begin to attract gas from the surrounding disk. A planet's ability to accumulate gas depends largely on its mass. The more massive a planet, the more gas it can capture, which is why super-Earths often have substantial atmospheres. This process can create planets with a variety of compositions, ranging from rocky worlds to those with thick gaseous envelopes. Yet, despite the numerous super-Earths discovered in other star systems, none exist in our solar system. This absence can be explained by the unique conditions that prevailed during the formation of our own solar system. The solar nebula, the cloud of gas and dust that birthed our solar system, was relatively small compared to the environments where many super-Earths have been found. In the early stages of solar system formation, most of the material that could form rocky planets was concentrated in the inner part of the solar system, giving rise to planets like Earth, Venus, Mars, and Mercury, all of which are much smaller than super-Earths. In some ways, the formation of super-Earths can be seen as a natural outcome of the processes that dominate planet formation in more massive protoplanetary disks, environments where the material distribution and conditions allow for the creation of larger, more massive worlds. Their absence in our solar system doesn't imply that they cannot exist, but rather that our solar system's formation conditions were simply not conducive to their creation. As astronomers continue to study these various classes of exoplanets, hot Jupiters, retrograde planets, and super-Earths, they are piecing together a more complex and nuanced picture of planetary system formation. Each discovery adds another layer of understanding, revealing the diverse and often chaotic nature of planetary dynamics across the universe. These exoplanets serve as both puzzles to solve and windows into the broader mechanisms that govern the birth and evolution of planets beyond our solar system. During the early stages of the solar system's formation, the immense gravitational forces and dynamic migrations of massive planets like Jupiter and Saturn played a crucial role in shaping the destiny of smaller rocky planets. These colossal giants, in their journey through the protoplanetary disk, likely disrupted the delicate balance required for the stable formation of planets similar to Earth. By scattering material either inward or outward, they effectively cleared vast regions, preventing the accumulation of mass that could have given rise to larger terrestrial planets. In essence, the gravitational interactions between these giant planets may have thwarted the formation of super-Earths, a category of planets that are significantly larger than Earth, but smaller than ice giants like Uranus and Neptune. The discovery of numerous super-Earths orbiting other stars presents compelling evidence of diverse planetary formation processes at work. These distant planets reveal environments and conditions far removed from the ones that shaped our own solar system. By studying these exoplanets, astronomers are gaining a deeper understanding of planetary formation, offering a glimpse into the vast array of evolutionary paths that planets can take throughout the cosmos. Each exoplanet represents a unique case study, highlighting the remarkable variety of planetary systems that exist beyond our solar neighborhood. One of the more intriguing phenomena that has captured the attention of astronomers is the Neptunian desert. This term refers to a conspicuous gap in the distribution of exoplanets, a void characterized by a distinct lack of planets with sizes or masses similar to that of Neptune, roughly 4 times the size of Earth. This gap stands as a puzzle, one that is still being explored in depth by researchers striving to understand the underlying reasons behind such an absence. The Neptunian desert is especially notable for its lack of exoplanets in the size range of approximately 2 to 4 times the Earth's radius. This clear desert of Neptune-like planets has become a central focus in the study of exoplanet diversity, raising questions about the processes that drive planetary formation and evolution. A key explanation for the existence of the Neptunian desert lies in the complex ways planets form and evolve after their initial creation. When a planet forms in a protoplanetary disk, its mass and the surrounding environment dictate its subsequent evolution. If a planet accumulates enough mass, it may retain a thick gaseous envelope, evolving into a gas giant like Jupiter or Saturn. On the other hand, smaller planets can lose their gaseous envelopes over time, eventually transforming into rocky worlds like Earth. The Neptunian desert can be understood within this context of planetary mass and atmospheric retention. Planets that form with intermediate masses, those around the size of Neptune, may either shed their atmospheres due to intense stellar irradiation or grow into gas giants by accumulating more gas before the protoplanetary disk dissipates. In either case, the result is a sharp decline in the number of planets in the intermediate size range, contributing to the formation of the observed gap in the exoplanet population. Another critical factor influencing the formation of the Neptunian desert is the role of stellar irradiation and atmospheric loss. For planets within the habitable zone of their stars, those regions where conditions might allow liquid water to exist, stellar radiation can significantly impact a planet's ability to retain its atmosphere. High levels of radiation can strip away lighter gases like hydrogen and helium, leading to the gradual loss of a planet's gaseous envelope. Consequently, super-Earths, which are often found in the same regions as exoplanets that might otherwise be classified as Neptune-like, are more likely to survive this process. This interplay between stellar radiation, atmospheric retention, and planetary migration leads to a reconfiguration of the planetary population, resulting in fewer planets with Neptune-like characteristics. Understanding the Neptunian desert is crucial for more than just explaining the current state of exoplanetary systems. It provides insights into the fundamental processes of planetary formation and the profound role that stellar and environmental conditions play in shaping planetary systems. Ongoing surveys of exoplanets continue to challenge our existing models of planetary formation, prompting astronomers to refine their theories and assumptions. As more exoplanets are discovered and studied, our comprehension of the vast diversity of worlds beyond our solar system will grow ever more profound. Exoplanets that orbit close to their stars face another fascinating set of challenges. These planets are forced to contend with the intense conditions found within the outer atmosphere of their host star, known as the corona. The corona, which can reach temperatures of millions of degrees, creates a hostile environment filled with high levels of radiation and energetic particle streams. Despite these extreme conditions, some exoplanets manage to survive and even thrive. Their survival is often due to a combination of unique factors, chief among them being the strength of their magnetic fields. Magnetic fields play a crucial role in protecting a planet's atmosphere from being stripped away by the stellar wind, the stream of charged particles constantly ejected from the star. Planets with strong magnetic fields can act as shields, deflecting the harmful particles and radiation that would otherwise erode their atmospheres. This protective barrier is essential for maintaining the conditions needed to support life, as it prevents the loss of key atmospheric components, such as water vapor. Additionally, these magnetic fields serve as a defense against harmful stellar radiation, further mitigating the adverse effects of the star's energetic emissions. Beyond the magnetic field, the composition and thickness of a planet's atmosphere also play a pivotal role in its ability to withstand the harsh conditions near its star. Some exoplanets have developed thick atmospheres composed of gases that are particularly effective at absorbing and deflecting incoming radiation and heat. These thick layers of gases provide insulation, helping to regulate the planet's surface temperature. As a result, these planets can maintain conditions that are conducive to the presence of liquid water, a crucial element for life as we know it. In essence, these planets exhibit the potential for habitability, despite their proximity to their stars, through a combination of magnetic shielding and atmospheric protection. In sum, the study of exoplanets provides a wealth of insights into the complex processes that govern planetary formation, migration, and survival. By examining these distant worlds, astronomers are uncovering the intricate relationships between a planet's size, composition, atmosphere, and its ability to withstand the harsh conditions of its environment. As technology continues to advance, our ability to detect and study exoplanets will only improve, bringing us closer to understanding the full extent of planetary diversity across the cosmos. The orbital dynamics of exoplanets, particularly those located within a star's corona, play a crucial role in shaping their environments. Many of these planets are tidally locked, meaning one hemisphere is always facing the star, while the opposite side is perpetually in darkness. This unique rotational characteristic has profound implications, particularly in how temperature gradients are distributed across the planet's surface. On the star-facing side, the relentless exposure to stellar radiation results in intense heating, while the opposite side remains a frigid, frozen wasteland. The contrast between these two hemispheres leads to a diverse range of environments, and it is within this stark thermal divide that the possibility for oceans or ice arises. In the extreme conditions presented by tidally locked planets, the interplay between magnetic fields, atmospheric conditions, and orbital mechanics becomes a testament to the resilience of these distant worlds. Extreme temperature variations are one of the most striking features of tidally locked exoplanets. Due to their unique rotational mechanics, these planets always show the same face to their star. As a result, one side of the planet is subjected to continuous sunlight, while the other remains cloaked in eternal darkness. The constant illumination of the day side causes temperatures to soar to scorching levels, potentially reaching extremes that might evaporate surface water or trigger the formation of heat-trapping clouds, further amplifying the planet's already harsh conditions. On the opposite side, the absence of solar radiation results in a chilling environment. With no direct sunlight for prolonged periods, temperatures on the night side can plummet, potentially dipping into the freezing range. If the planet has a sufficiently thick atmosphere capable of retaining heat, frost or ice may begin to accumulate. This dramatic thermal contrast not only defines the planetary experience, but also influences atmospheric circulation patterns, which can lead to the development of powerful winds. These winds act as natural redistributors of heat, striving to mitigate the extreme temperature disparities between the two hemispheres. Some tidally locked exoplanets are endowed with thick atmospheres, which can help moderate these temperature fluctuations to some extent. A robust atmosphere has the potential to transport heat from the star-facing side to the shadowed night side, creating a more balanced temperature distribution across the planet. However, the efficiency of this process is highly dependent on factors such as the planet's atmospheric composition and the nature of its climate system. The fascinating complexity of these interactions highlights how exoplanets can evolve in response to the extreme stellar conditions they inhabit, showcasing the resilience and adaptability of these worlds in the face of powerful forces. In addition to the challenges posed by tidal locking, exoplanets residing in binary star systems face their own set of unique conditions. A binary star system, where two stars orbit around a shared center of mass, creates a gravitational environment that significantly alters planetary formation and stability. Unlike in single star systems, where planets form from a single protoplanetary disk, binary star systems introduce a second gravitational influence. This interaction can either enhance or disrupt the formation of planets, depending on the distance between the two stars. In wider binary systems, the protoplanetary disk remains relatively stable, allowing particles to clump together and form planetary bodies. However, in closer binary systems, the gravitational perturbations of the two stars can lead to a more chaotic environment, scattering particles or even ejecting them from the disk entirely. This altered environment makes the formation of planets in binary star systems more complex and less predictable than in single star systems. Even when planets manage to form, their orbits can be influenced by the gravitational pull of both stars. These gravitational interactions can lead to unstable orbits, making the planet more vulnerable to disruptions, such as potential collisions with other bodies or ejection from the system altogether. As a result, planets in binary star systems must navigate a much more dynamic and unpredictable gravitational landscape compared to those orbiting solitary stars. However, not all is chaotic in binary systems. Some planets manage to find stable zones within the binary setup, particularly if they are situated at the right distance from both stars. In these regions, gravitational forces from both stars can balance each other out, allowing the planet to maintain a stable orbit. These so-called circumbinary planets can reside in areas of the protoplanetary disk that are influenced by both stars, creating a delicate equilibrium that enables the planet to persist in its orbit without being significantly disturbed. This stability within the gravitational interplay of the two stars opens up possibilities for a wide range of planetary environments, offering the potential for diverse worlds formed under the influence of dual stellar systems. Moreover, some of the most intriguing exoplanets to be discovered in recent years are those described as cotton candy worlds. These planets are characterized by their remarkably low densities, suggesting they are composed of lighter materials that differ significantly from the dense, rocky worlds like Earth. The term cotton candy world refers to their fluffy, gaseous nature, which gives them a unique and ethereal appearance. These planets are typically thought to possess thick atmospheres, primarily composed of hydrogen and helium, elements that are also found in the gas giants of our solar system. Despite their low density, these exoplanets are not to be underestimated. They may have vast gaseous envelopes that encase the planet, providing them with the ability to retain heat and exert significant atmospheric pressure. These atmospheres can contribute to a highly dynamic weather system with strong winds and potential for cloud formation, further complicating the planetary environment. Although the precise composition of cotton candy exoplanets remains a subject of ongoing research, it is clear that these distant worlds offer a fascinating glimpse into the diversity of planetary bodies beyond our solar system, challenging our understanding of what is possible in the vast and ever-expanding universe. The complexity of planetary environments in binary star systems, the extreme conditions found on tidally locked planets, and the intriguing nature of low-density cotton candy worlds all point to the remarkable diversity that exists in the cosmos. Each planet, shaped by the forces of gravity, stellar radiation, and atmospheric conditions, offers a unique and fascinating story, underscoring the incredible variety of exoplanets scattered across the galaxy. As we continue to explore these distant worlds, we uncover the many ways in which planets can evolve in response to their cosmic environments, revealing the stunning complexity of the universe we inhabit. However, what truly sets these planets apart is their remarkably low mass, coupled with their rapid formation processes. This combination often leads to a unique, bloated, and puffed-up state as the planets evolve. As they develop, these planets possess the ability to trap vast amounts of lighter gases, contributing to a soft, cotton candy-like exterior that is strikingly less dense compared to their mass. Their low density is visually akin to the fluffy, airy texture of cotton candy, an outer shell that seems delicate but can hold surprisingly substantial volumes of gas. As these exoplanets continue to form, the presence of water vapor and other volatile compounds becomes increasingly significant. Water, alongside other molecules that easily vaporize, plays a pivotal role in the observed low densities. The combination of hydrogen-rich atmospheres and substantial water content can create a dynamic range of cloud formations and weather patterns that are vastly different from those found on denser, rocky planets. These weather systems, while still under investigation, offer clues into the extraordinary conditions these planets can generate. Their atmospheres may host complex cloud formations and potentially unknown meteorological phenomena, which are still being researched to understand their behavior over long periods. The formation history of these planets, sometimes referred to as cotton candy worlds, provides tantalizing clues about planetary evolution. Some scientists theorize that they may have formed in more massive protoplanetary disks or once resided closer to their host stars before migrating outward. This migration could have allowed them to gather lighter gases without the intense heat that would otherwise strip away these elements. Such a process challenges our conventional understanding of planet formation, suggesting that the universe holds a far wider array of possibilities than we had once imagined. These cotton candy planets may offer us a glimpse into the surprising diversity of planetary types that could exist in distant star systems. In another corner of the cosmos, there exist exoplanets orbiting pulsars, ultra-dense, highly magnetized remnants of stars that have exploded in supernovae. The conditions required for a planet to maintain a stable orbit around a pulsar are unique and dictated by the extraordinary properties of these cosmic objects. Pulsars, which rotate rapidly and emit beams of electromagnetic radiation, exert immense gravitational forces due to their compact size and powerful magnetic fields. These forces can dramatically affect the orbits of nearby planets, making their stability a subject of intense study. For an exoplanet to remain in a stable orbit around a pulsar, it must find itself at the right distance, often referred to as the habitable zone, or the gravitational sweet spot. This distance ensures that the gravitational pull of the pulsar and the orbital speed of the planet are balanced, so the planet isn't pulled in too close or flung too far away into space. However, the intense radiation emitted by pulsars can pose a significant threat to any nearby planet. Despite these hazards, some exoplanets have demonstrated remarkable resilience. They may have developed strong magnetic fields or protective atmospheres that shield them from the pulsar's harmful emissions. Moreover, the formation of planets around pulsars often takes place after a star has gone supernova, leaving behind the dense remnant known as a pulsar. The surrounding debris from the explosion can serve as a reservoir of material from which planets can form. As planets coalesce from this debris, they can establish stable orbits early on, securing their place around the pulsar. The remaining debris field, although chaotic at first, eventually settles into an environment where the frequency of collisions between bodies becomes lower, thus facilitating more stable orbital paths. Observations have shown that many pulsars host planets, and these planets often exhibit carefully measured orbital configurations. These orbital arrangements are influenced not only by the pulsar's gravitational forces, but also by its rotational characteristics, such as its spin rate and magnetic field orientation. The planets that find themselves in the right orbital positions can thrive within the pulsar's environment, adapting to its extreme conditions and demonstrating the incredible diversity of planetary systems in our universe. Elsewhere, many exoplanets have been found to exhibit wildly elliptical orbits, an intriguing feature that is often the result of gravitational interactions, chaotic dynamics, and the evolutionary history of the planetary system. Initially, when planets form in protoplanetary disks, their orbits are typically circular. However, over time, these orbits can evolve into more elongated paths, taking planets far from their host stars at certain points in their orbits. One significant factor influencing these changes is the gravitational pull exerted by other celestial bodies in the system. When multiple planets are located near each other, their gravitational interactions can lead to orbital changes. If one planet approaches another too closely during its orbit, the interaction can create a gravitational slingshot effect, altering both planets' orbits. These interactions can push planets into more eccentric orbits, creating the elongated elliptical trajectories we observe. Another important factor is planetary migration. Many exoplanets start their lives farther from their stars and gradually spiral inward over time, influenced by interactions with the protoplanetary disk or other nearby planets. As a result, some exoplanets develop highly elliptical orbits, especially if they encounter orbital resonances that amplify their orbital eccentricity. These resonances occur when two orbiting bodies exert a regular, periodic gravitational influence on one another, leading to an enhancement of the eccentricity of their paths. In all these cases, the dynamic interplay between gravitational forces, planetary migration, and orbital resonance highlights the complexity of exoplanetary systems. As scientists continue to observe and study these phenomena, they are uncovering the vast and varied ways in which planets can evolve and adapt to their environments. The study of exoplanetary orbits, whether elliptical or stable, is not only crucial for understanding individual planetary systems, but also for expanding our knowledge of how planets form, migrate, and interact in the broader cosmos. The universe is teeming with possibilities, each one offering a new opportunity to explore the diversity of planetary life. Stellar influences play a crucial and often underestimated role in shaping the orbits of exoplanets. As exoplanets travel through the cosmos, their paths are not solely dictated by the gravity of their host stars. Close encounters with neighboring stars, or even the gravitational pull of distant celestial bodies, can significantly perturb a planet's orbit, resulting in profound changes to its trajectory. When a planet comes close enough to another star, the gravitational forces between the two objects can stretch the planet's orbit, transforming it from a near-circular shape to one that is highly elliptical. This kind of encounter can dramatically alter the planet's distance from its star, affecting everything from its climate to the possibility of sustaining life. These stellar interactions are part of a grand, dynamic, astronomical ballet where forces beyond our control choreograph the movements of planets, sometimes in ways we have yet to fully understand. This constant interplay of cosmic forces paints a picture of a universe in flux, where even the most stable of planetary systems can be disrupted by the movements of nearby stars. Over the lifespans of these exoplanets, such interactions are not rare. Rather, they highlight the ever-changing nature of our universe, where stars and planets are in a constant dance, evolving and adjusting in response to each other's gravitational pull. To understand these celestial phenomena, we must trace the universe back to its very beginning. In the first fraction of a second after the Big Bang, the universe underwent a series of rapid and transformative events. These early moments set the stage for everything that would follow. This period, known as the Planck epoch, was an era when the universe was incredibly hot and dense, with temperatures exceeding 10 to the power of 27 Kelvin. It was a time when the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single force, a state that existed for only a fleeting moment. As the universe began to cool, it quickly transitioned beyond the Planck epoch, entering what is called the Grand Unification epoch. During this period, the once unified forces began to separate, with gravity becoming distinct from the other three. The rapid expansion of the universe, known as cosmic inflation, further reshaped the landscape of space-time. This inflationary phase, which lasted for mere fractions of a second, stretched space exponentially, smoothing out any irregularities that had existed before. The rapid expansion of space allowed regions of the universe to drift far apart, even though they had originally shared the same initial conditions. As inflation came to an end, the universe continued to cool, setting the stage for the formation of matter. In the next stage, known as reheating, energy from inflation was converted into particle-antiparticle pairs, giving rise to the creation of fundamental particles, including quarks, electrons, and neutrinos. Despite these particles beginning to form, conditions were still too energetic for them to combine into stable atoms. The universe remained in a soup-like state, with free particles floating in a chaotic dance. By roughly 1 second after the Big Bang, the universe had expanded and cooled sufficiently for quarks to combine, forming protons and neutrons. This marked the beginning of the baryogenesis phase, a period where the matter that would eventually form stars, galaxies, and the very structure of the cosmos began its journey. From this explosive origin, the universe began to take shape, leading to the formation of everything we know today. Understanding these early moments of cosmic history is key, not only to explaining how the universe formed, but also to unraveling the mysteries of why it took the shape we observe now. Approximately 380,000 years after the Big Bang, the universe underwent a transformative change. The cooling of the cosmos reached a point where electrons could combine with protons to form neutral hydrogen atoms, a phase known as recombination. This led to what is referred to as the cosmic dark ages, where the universe became mostly transparent to radiation. The once chaotic soup of particles began to cool into a more stable state, allowing light to travel freely across the vast stretches of space. But even during this seemingly quiet phase, the universe was not entirely dormant. Small fluctuations in the density of matter, remnants from the quantum fluctuations that occurred during inflation, played a crucial role in the birth of the first stars and galaxies. These fluctuations, though minuscule, led to regions of slightly higher density which began to gravitationally attract surrounding gas, primarily composed of hydrogen and helium. Over millions of years, these denser regions collapsed under their own gravity, forming the first cosmic structures. As the density reached a critical threshold, the collapsing gas formed protostars, clusters of gas and dust that heated up as the gravitational pressure intensified. Eventually, the temperature in these protostars became high enough for nuclear fusion to occur. This was the spark that ignited the first stars, often referred to as population 3 stars. These early stars were vastly different from those we observe today. They were massive, burning through their fuel at a tremendous rate, and were short-lived compared to the stars that came after them. But their rapid consumption of fuel and subsequent death played a critical role in shaping the universe, as these stars produced vast amounts of energy, which helped to re-ionize the universe. The intense radiation and stellar winds from these first stars had a profound impact on their surroundings, clearing out large amounts of gas and dust. This process facilitated the formation of galaxies, as the remnants of the first stars and the energy they released helped to shape the large-scale structures we see in the universe today. These star clusters merged, evolved, and formed the galaxies that became the building blocks of the cosmic web. In the grand scheme of the universe, these early moments, brief as they were, laid the foundation for the complex structures that followed. The formation of the first stars and galaxies marks the dawn of a new era in cosmic history, where the very building blocks of the universe began to take their familiar shapes. The universe, once a hot and dense cloud of particles, slowly matured into the vast, intricate cosmos that we continue to study and explore today. Through understanding these pivotal moments, we not only gain insight into how our universe began, but also into the forces that continue to shape its evolution, from the birth of stars to the intricate orbits of exoplanets. The complex interplay between gravitational radiation and cosmic evolution has shaped the universe we observe today. From the first whisper of the Big Bang, this intricate process seeded the formation of the galaxies, the very building blocks of the cosmos. These seeds, now grown into the vast network of galaxies, stretch across the observable universe. They gave birth to everything from our own Milky Way to the countless galaxies scattered across the vast expanse of space. At the heart of this grand cosmic drama is an enigmatic force, dark matter. Believed to constitute approximately 25% of the total mass energy content of the universe, dark matter remains one of the most profound mysteries in modern science. Unlike the ordinary matter that makes up everything we can see, stars, planets, and living organisms, dark matter neither emits, absorbs, nor reflects electromagnetic radiation, such as light. This lack of interaction with light makes dark matter invisible, detectable only through its gravitational effects on the visible matter and radiation around it. The evidence for dark matter comes from various astrophysical observations that highlight its mysterious presence. For example, the way galaxies rotate offers strong clues. According to Newtonian physics, the outer regions of galaxies should rotate more slowly than the inner regions, given the way visible mass is distributed. Yet, astronomers have found that the outer parts of galaxies rotate at unexpectedly high speeds. This anomaly suggests that an unseen, invisible mass, now understood as dark matter, is exerting a gravitational pull on the galaxy, holding it together in a way that visible matter alone cannot. Another key observation that points to the existence of dark matter comes from gravitational lensing. This phenomenon occurs when the light from distant objects is bent by the gravitational influence of massive galaxy clusters. The degree of bending observed is stronger than what would be expected based solely on the visible matter in these clusters. This indicates that the amount of mass present in these clusters far exceeds what we can directly observe, further supporting the idea that dark matter is at play. Dark matter primarily interacts with regular matter through gravity. However, its true nature remains elusive. Numerous theoretical candidates have been proposed to have it, with one of the leading possibilities being weakly interacting massive particles, one apiece. These hypothetical particles would interact with normal matter via the weak nuclear force, in addition to gravity. Other potential candidates include axions or sterile neutrinos, but despite extensive efforts, none of these particles have been definitively detected. Because dark matter does not interact with electromagnetic radiation, it does not form atoms or molecules, making it fundamentally different from the ordinary matter that makes up the stars and planets. To probe dark matter's properties further, researchers are conducting experiments designed to detect dark matter particles directly or indirectly. These experiments are carried out in specially shielded environments, such as deep underground laboratories, or even in the vacuum of space. Yet, despite these efforts, no conclusive results have emerged so far. Understanding the nature of dark matter is crucial for piecing together the history of the universe, as it plays a pivotal role in the formation and evolution of cosmic structures. Dark matter influences the way galaxies and galaxy clusters evolve over cosmic time, affecting the very shape and structure of the universe. The search for dark matter represents one of the most significant challenges in modern astrophysics and cosmology. As scientists delve deeper into the nature of this invisible substance, they face one of the most profound questions in science. What exactly is dark matter, and how does it influence the fabric of the universe? Parallel to the mystery of dark matter, another enigma has puzzled physicists and cosmologists: the apparent predominance of matter over antimatter in the universe. According to the fundamental laws of physics, for every particle of matter, there should be a corresponding antiparticle. When matter and antimatter meet, they annihilate each other, producing energy in the form of photons. During the early moments of the Big Bang, both matter and antimatter should have emerged in roughly equal amounts. However, our observable universe is overwhelmingly made up of matter, with very little antimatter detected. This imbalance is known as baryon asymmetry, and it is one of the great mysteries of modern physics. Theories to explain this imbalance propose that certain processes in the extremely hot and dense conditions of the early universe favored the production of matter over antimatter. One of the leading explanations involves a phenomenon known as CP violation, which refers to violations of the combined symmetry of charge conjugation and parity during certain particle decays. Experiments have shown that particles decay differently from their corresponding antiparticles, suggesting that the laws of physics behave asymmetrically under specific conditions. Several theoretical models have been proposed to explain how this asymmetry could have emerged. One of the most prominent is the electroweak baryogenesis model, which suggests that at high energies, interactions involving the electroweak force, one of the four fundamental forces of nature, may have contributed to a preferential generation of matter over antimatter. Another possibility involves the Higgs boson, a fundamental particle that might have played a role in generating this imbalance. Despite the progress in understanding these processes, the precise mechanism behind the matter-antimatter imbalance remains unresolved. Researchers continue to investigate this question through particle collisions, studies of cosmic background radiation, and other cosmological phenomena. Understanding how the universe came to favor matter over antimatter not only deepens our knowledge of particle physics, but also provides vital insights into the origins of the universe and the conditions that allowed it to evolve into the vast and complex structure we see today. In the end, the quest to understand dark matter and baryon asymmetry is not just a search for answers to isolated questions, but a journey into the very heart of the cosmos. These mysteries are intertwined with the fabric of the universe itself, and solving them will bring us one step closer to unraveling the secrets of the cosmos, from the birth of the universe to the complex web of galaxies, stars, and planets that it contains. Cosmic inflation, the rapid exponential expansion of the universe in its earliest moments, may hold the answers to some of the most profound questions about the fundamental structure of reality itself. This brief but incredibly intense phase of expansion occurred roughly between 10 to the power of negative 36 and 10 to the power of negative 32 seconds after the Big Bang. It has since become a cornerstone of modern cosmology, providing key insights into the formation and current state of the universe. During this incredibly brief period, the universe expanded at an astonishing rate, growing by a factor greater than 1 trillion times in less than a fraction of a second. This rapid expansion has helped to explain several critical features of the universe, including its overall uniformity and the seemingly random distribution of cosmic structures we see today, from galaxies to clusters of galaxies. While scientists are still actively investigating the exact causes behind cosmic inflation, multiple theories have emerged, offering possible mechanisms for this cosmic growth spurt. One of the leading hypotheses suggests that inflation was driven by a hypothetical scalar field known as the inflaton field. This invisible field is believed to have permeated the early universe, exerting an immense negative pressure that caused space itself to expand rapidly. As the inflaton field decayed, its energy was converted into particles and radiation, ultimately leading to the cooling of the universe. This cooling in turn facilitated the formation of the first subatomic particles, atoms, stars, galaxies, and all the cosmic structures we observe today. Imagine, if you will, a tightly packed spring under immense pressure. When released, it causes the universe to explode into a period of accelerated growth, setting the stage for everything we know. Cosmic inflation also provides elegant solutions to several perplexing puzzles in cosmology. One of the most challenging questions it addresses is the flatness problem, which concerns the precise balance of density in the universe. Despite the immense differences in the distribution of matter across space, the universe appears to have an almost perfectly flat geometry. Inflation solves this by stretching the fabric of the universe to such an extent that even minor fluctuations are stretched out, smoothing out the initial irregularities and creating the uniform cosmos we observe today. Another mystery solved by inflation is the horizon problem, which concerns the homogeneous temperature of the cosmic microwave background radiation across vast stretches of space. In a universe that had no initial connection between distant regions, how could these regions have the same temperature? According to inflationary theory, the answer lies in the fact that these distant regions were once in close proximity, but the rapid expansion quickly separated them, leaving behind a uniform temperature across the observable universe. In addition to these theoretical frameworks, researchers are actively testing the predictions made by inflationary models through observational data. Measurements of the cosmic microwave background radiation, as well as surveys of large-scale cosmic structures, are providing valuable evidence to either confirm or refine our understanding of the inflationary period. While the exact mechanics of inflation are still under investigation, the theory has already provided a profound leap forward in our understanding of the universe's early days and the forces that shaped its evolution. This period of inflation not only rewrote the early history of the cosmos, but also set the stage for the creation of galaxies, stars, and the very conditions necessary for life itself. Looking beyond the origins of the universe, the fate of the cosmos is another question that has captivated cosmologists for decades. As we continue to study the universe's expansion, three primary scenarios have emerged regarding how the universe might ultimately end: the Big Freeze, the Big Rip, and the Big Crunch. Each of these potential outcomes hinges on the behavior of cosmic expansion, the density of matter, and the mysterious force known as dark energy, which is believed to be driving the accelerated expansion of the universe. The most widely accepted scenario at present is the Big Freeze. This model suggests that the universe will continue to expand indefinitely, with galaxies drifting further apart over unimaginably long timescales, trillions of years. As this process continues, the available gas and dust needed for new star formation will be depleted, and the universe will become increasingly cold and empty. Eventually, all stars will burn out, leaving behind remnants like white dwarfs, neutron stars, and black holes. The universe will eventually reach a state of thermodynamic equilibrium, where only low-energy radiation and dark matter remain. This heat death will mark the slow, inevitable decline of a universe that becomes dark and frigid, slowly fading into an unchanging void. In stark contrast, the Big Rip offers a much more dramatic and chaotic ending. In this scenario, dark energy, instead of remaining constant, would grow stronger over time. As it becomes increasingly powerful, it could overpower the gravitational forces that bind galaxies, stars, and even planets together. The accelerated expansion of the universe would reach a tipping point, tearing apart galaxies, stars, and even atomic structures. The universe would end not with a whimper, but with a catastrophic disintegration of everything, from large-scale cosmic structures to the very building blocks of matter. The result would be a universe that ceases to exist as we know it, dissolving into an infinitesimally small and incomprehensible state. The Big Crunch, on the other hand, presents a more cyclical view of the universe's fate. In this scenario, the expansion of the universe slows over time due to the gravitational pull of matter within it. Eventually, this leads to a reversal of cosmic expansion, pulling galaxies and all matter back toward a central point. As the universe contracts, the temperature rises dramatically, and galaxies collide, merging into a dense, hot state. The end result would be a singularity, a state of infinite density and temperature, akin to the conditions of the Big Bang. The Big Crunch suggests the possibility of a cyclic universe, one that could potentially reboot, entering a new expansion phase after contracting to a singularity. Current observations, especially the measurement of cosmic acceleration and the influence of dark energy, seem to point toward the Big Freeze as the most likely scenario. However, the true fate of the universe remains one of the greatest mysteries in cosmology, as we continue to explore the depths of space and time to understand the forces that shape not only our past but also our future. The journey of cosmic expansion, from its explosive beginning to its ultimate end, is a story still unfolding, filled with astonishing discoveries that continue to challenge our understanding of the universe and our place within it. As research continues and new cosmic phenomena are uncovered, our understanding of the universe's fate evolves, offering deeper insights into the ultimate destiny of all existence. The more we discover, the more we come to realize that the universe's future is not a fixed path, but a landscape filled with mystery, uncertainty, and untapped possibilities. These revelations, still unfolding, help us not only grasp the distant future of the universe, but also offer profound insights into the nature of space-time itself and the fundamental forces that govern reality. As the theories grow and expand, they lead us down new avenues of thought, pushing the limits of our understanding. At the heart of this exploration lies the intriguing concept of the multiverse, the idea that our universe may not be the only one, but instead just one of many distinct coexisting universes, each potentially governed by its own set of physical laws and constants. This hypothesis has become an important subject of discussion in both theoretical physics and cosmology, gaining considerable traction in some circles. Yet, despite its allure, the multiverse remains speculative. No definitive experimental evidence has been found to confirm its existence, leaving it an unresolved and tantalizing question in modern science. Its very nature challenges the conventional boundaries of what we consider to be reality. Several theoretical frameworks propose different models of the multiverse, each offering a unique perspective on how such a vast collection of universes might come into being. One of the most discussed concepts is the inflationary multiverse, which stems from the theory of cosmic inflation. In the early moments of the universe, during the process of rapid expansion, different regions could have stopped inflating at different times, leading to the creation of what are known as bubble universes. Each bubble within this grand multiversal structure could have its own distinct set of physical properties. The idea suggests that there could be an infinite number of universes, each with potentially differing physical laws, constants, and even entirely unique realities. In such a scenario, the laws of physics that govern our universe might not apply universally, and every universe could represent a different realization of possibilities. Alongside this, another fascinating hypothesis arises from the many worlds interpretation of quantum mechanics, which offers a radically different view. According to this interpretation, every time a quantum event occurs, such as the measurement of a particle's position or spin, the universe branches. Each possible outcome of that event occurs in a separate, parallel universe. Thus, the universe we experience is just one among countless others, each representing a different version of reality based on the outcomes of quantum interactions. In this context, every conceivable possibility could manifest in its own universe, creating a sprawling, interconnected landscape of realities. The number of universes within such a multiverse scenario is an open question. It could range from a countably infinite set to an unbounded, unfathomable quantity beyond human comprehension. Some models even suggest that universes may continuously form and dissolve, further complicating the task of quantifying or even conceptualizing them in any traditional sense. The deeper we explore these ideas, the more we realize that for multiversists, our understanding of what is real and what constitutes reality might be severely limited. This realization challenges us to reconsider our place in the cosmos. While the multiverse theory elegantly explains certain phenomena within its theoretical framework, it also raises profound philosophical and scientific questions. For example, testing the existence of other universes directly remains an insurmountable challenge. Given the physical constraints of our current understanding, other universes would likely be inaccessible to us. Without any way to gather empirical evidence from beyond our universe, we are left in the realm of speculation. Despite this, the concept of the multiverse continues to inspire debates and fuel imagination, as it offers a way to explain anomalies in physics that remain puzzling in a single universe context. Parallel to these cosmic speculations is the equally enigmatic phenomenon of quantum entanglement, a cornerstone of quantum mechanics. Quantum entanglement refers to the way in which two or more particles can become linked, such that the state of one particle instantaneously influences the state of the other, no matter how far apart they are. This strange behavior shatters the classical understanding that information cannot travel faster than light, leading to questions about the fundamental nature of reality itself. Entangled particles exhibit what Albert Einstein famously described as spooky action at a distance. Einstein, along with his contemporaries, initially saw this phenomenon as a challenge to the principles of locality, which state that objects are only directly influenced by their immediate surroundings. However, subsequent experiments, starting with Alain Aspect's work in the 1980s, have confirmed that particles do indeed display this instantaneous correlation, even when separated by vast distances. The implications of this result are profound and puzzling. They suggest that space, time, and causality might not be as clear-cut and rigid as we once thought. The nature of quantum entanglement raises deep questions about the structure of space-time. It points to a kind of non-locality, suggesting that particles could be more interconnected than we previously imagined, challenging the classical view that space-time is made up of separate, independent points. Some interpretations of quantum theory propose that this entanglement could be evidence of a deeper, more profound interconnectedness of the universe, one in which the separation between objects is less absolute than it appears. Rather than being discrete entities that interact only locally, particles, and perhaps even entire systems, could be part of a larger, non-local web of relationships that spans the cosmos. Ultimately, quantum entanglement challenges us to rethink the nature of space, time, and reality itself. It raises the possibility that the universe is much more interconnected and non-local than we have ever imagined. As our understanding of quantum mechanics continues to evolve, so too will our understanding of the universe's fundamental fabric, its very space-time. Every new discovery, whether in the realm of quantum mechanics or cosmology, seems to bring us closer to unveiling the vast, hidden complexities of the universe and the true nature of reality. In the grand scheme of things, these ideas, be they about the multiverse or quantum entanglement, remind us that the universe is far from being a static, predictable entity. Rather, it is a dynamic, ever-evolving system that continues to challenge our perceptions and ignite our imagination. The more we learn, the more we realize how little we actually know, and how vast the horizon is when it comes to uncovering the secrets of existence itself. In the world of modern physics, few concepts are as captivating and perplexing as quantum entanglement. This phenomenon, in which two or more particles become inextricably linked, regardless of the distance between them, plays a crucial role in the ongoing efforts to unify the two dominant theories that govern our understanding of the universe: general relativity and quantum mechanics. As physicists venture further into the intricacies of quantum entanglement, some have speculated that the very fabric of space-time itself could be a product of entanglement relationships among fundamental quantum particles. This radically different view suggests that what we perceive as the smooth, continuous structure of space-time may not be an inherent property of the universe. Instead, it could emerge from the entangled connections between the most basic building blocks of reality. The idea proposes that space-time, along with the laws of physics as we know them, could be a consequence of deeper, underlying quantum states that we have yet to fully comprehend. The entanglement between particles might form a network so fundamental that it shapes the very essence of how we experience space and time. As researchers push forward with experiments and theoretical advancements, the ramifications of quantum entanglement become ever more profound. It challenges not only our understanding of quantum mechanics, but also our conception of reality itself. The connections it reveals might ultimately reshape our worldview, suggesting that everything we experience, from the motion of planets to the passage of time, could be the result of entangled quantum states on a scale we can hardly imagine. Physicists are diving into a deeper, more complicated web of ideas. Could quantum entanglement be the key to understanding phenomena like quantum gravity? As we search for a theory that successfully merges the microscopic world of quantum particles with the macroscopic reality governed by gravity, entanglement seems to hold some of the answers. In this emerging framework, the connections between particles could potentially provide insight into how general relativity and quantum mechanics can coexist in a unified theory of everything. Primordial black holes represent another fascinating enigma in the study of the universe's origins. These black holes, distinct from their stellar counterparts, are hypothesized to have formed not from the death of massive stars, but from the very conditions present in the early moments of the Big Bang. Unlike stellar black holes, which are created by the gravitational collapse of massive stars, primordial black holes could have formed from density fluctuations in the ultra-hot, dense environment of the nascent universe. As the universe expanded and cooled, regions with higher than average density might have collapsed under their own gravity, leading to the formation of black holes long before the first stars or galaxies began to take shape. This process could have occurred during the inflationary era, a brief yet explosive period when the universe expanded at an incredibly rapid rate. During this time, quantum fluctuations were magnified to macroscopic scales, creating substantial variations in the density of matter. If some of these fluctuations reach a critical density, they could have caused gravitational collapse, resulting in the creation of black holes. These primordial black holes could span an extraordinary range of sizes. Some might have masses only a few times greater than that of a small asteroid, while others could be much more massive, perhaps equivalent to those formed from stellar collapses. However, these early black holes might have played an even more important role in the development of the cosmos. Their gravitational influence could have shaped the structure of the universe by acting as seeds for the formation of galaxies and large-scale structures. As they drew in surrounding matter, these black holes could have facilitated the formation of the first galaxies, making them key players in the evolution of the universe. Moreover, these enigmatic objects might offer a clue to the mystery of dark matter, which, despite its pervasive presence in the universe, remains elusive to scientists. Some researchers propose that primordial black holes could be a significant component, or perhaps the entirety, of dark matter. If this hypothesis is correct, it would not only explain the gravitational effects attributed to dark matter, but could also offer groundbreaking insights into one of the most profound mysteries in astrophysics. The search for primordial black holes is ongoing, with researchers utilizing advanced techniques like gravitational wave detection and other observational tools to uncover traces of these early cosmic objects. By examining cosmic structures and studying the faint signatures left behind by these black holes, scientists hope to gain a clearer understanding of how black holes formed in the early universe and what role they played in shaping the cosmic landscape we observe today. One of the most intriguing and puzzling features of the cosmic microwave background radiation, the faint glow left over from the Big Bang, is the cold spot. This particular region, cooler than its surrounding areas, presents a fascinating riddle for cosmologists. The cold spot has baffled scientists because it suggests something unusual is taking place in this part of the universe. The temperature here is just slightly below average, but the implications of this anomaly are far-reaching. One of the leading theories to explain the cold spot is the existence of a supervoid. A supervoid is an enormous region of space that contains significantly fewer galaxies than the typical density found elsewhere in the universe. Such a supervoid could span millions of light years and, due to its lack of matter, would exert less gravitational influence, which could account for the cooler temperatures observed in the cold spot. The presence of this supervoid would also have significant consequences for the structure of the universe, as these vast, empty regions can stretch the fabric of space-time itself. Another intriguing hypothesis involves primordial fluctuations in the density of matter in the early universe. These fluctuations, which arose during the inflationary period, may have created variations in the temperature across the universe, potentially leaving an imprint on the cosmic microwave background. Some researchers speculate that the cold spot could be the result of a more exotic phenomenon, an ancient supercluster's gravitational influence. This long-forgotten structure, once a massive collection of galaxies, could have left a subtle but profound mark on the fabric of spacetime itself, creating the cold spot that we observe today. In this way, the cold spot becomes more than just an anomaly in the cosmic microwave background. It is a window into the deep past, a glimpse of the early universe that might reveal hidden forces, ancient structures, or cosmic events that shape the universe into what we see today. Whether the explanation lies in the existence of a supervoid, primordial fluctuations, or some other cosmic mystery, the cold spot invites scientists to look deeper into the origins of our universe and the forces that continue to shape it. The notion that we might not be alone in the universe is not just a topic of speculation. It's one that has sparked profound interest and debate, particularly with the ongoing exploration of the multiverse. According to theories surrounding this concept, our universe may be just one of many, part of an intricate and vast cosmic ensemble. Imagine for a moment that an entirely separate universe might have collided with ours. The implications of such an event could be far-reaching, affecting the very fabric of space-time. It might manifest in disturbances in the cosmic microwave background, those faint, ancient remnants of the Big Bang. These disturbances could appear as either cold or hot spots, anomalies that challenge our understanding of the universe's creation and evolution. As scientists explore these mysterious cold spots, they venture deeper into the cosmic unknown. Their research brings us closer to uncovering the origins of our universe, yet with every discovery, we are confronted with even more questions. What does it mean for our understanding of reality if other universes exist beyond the bounds of what we perceive? The concept of the multiverse pushes the boundaries of science itself, offering a tantalizing glimpse into the untapped potential of knowledge. But as we venture further into this speculative realm, we are reminded that each new piece of information only adds to the complexity of the cosmos. The journey to understand it may be long, but every step brings us closer to understanding the vastness of our existence. Among the many mysteries that continue to capture our collective imagination, few are as captivating as the discovery of the wow signal, which has become one of the most enduring enigmas in the search for extraterrestrial intelligence. It was on August 15, 1977, when a strong and highly unusual radio signal was detected by a radio telescope at Ohio State University. The signal, which lasted for a mere 72 seconds, was so striking in its intensity that astronomer Jerry R. Eman, upon reviewing the data, wrote the word "wow" in red ink on the printout. Little did he know that this simple exclamation would become synonymous with one of the greatest unsolved mysteries in the history of astronomy. The wow signal, originating from the direction of the constellation Sagittarius, has intrigued scientists ever since. What makes it especially remarkable is that the signal appeared to match the expected signature of a transmission that could have been generated by an alien civilization. The frequency it emitted fell within the hydrogen line, a wavelength commonly associated with potential extraterrestrial communications. As scientists have long speculated, hydrogen is a key element in the universe, and it is precisely this frequency range that we monitor in the search for signals from other worlds. Despite numerous attempts to locate a repeat of the signal, it has never resurfaced, and its source remains elusive. This persistent mystery has prompted many theories. Some suggest it could have been a natural phenomenon, perhaps related to a comet or even a passing asteroid. Yet, these explanations fail to account for the signal's narrow bandwidth and highly specific properties, which align closely with what one might expect from an artificial source. Another possibility that has captured the imagination of many is that the wow signal could indeed be a transmission from an extraterrestrial civilization trying to make contact across the vastness of space. The fact that no definitive explanation for the wow signal has emerged only deepens its allure. It stands as a powerful symbol of our ongoing quest to understand the universe, urging us to explore even more audacious possibilities. As technology advances and our understanding of the cosmos expands, the WOW signal continues to challenge researchers to reimagine what we know about life beyond our planet. What if the signal was a beacon, a faint cry from a distant civilization waiting to be heard? The mystery it represents continues to fuel discussions within the scientific community and keeps the dream of finding extraterrestrial life very much alive. As we turn our attention to the red planet, Mars has long been a focal point in the search for life beyond Earth, especially in the form of ancient microbial life. The discovery of organic molecules on Mars is one of the most exciting avenues of research in this regard. Organic molecules, complex structures composed mainly of carbon, along with hydrogen, oxygen, nitrogen, and other elements, are considered the building blocks of life as we know it. The presence of these molecules on Mars suggests that the planet may have once hosted the conditions necessary for life. Over the past several years, missions like NASA's Curiosity rover have provided compelling evidence of organic molecules on Mars, detected in ancient sedimentary rocks. These molecules are thought to have formed through a combination of geological and potentially biological processes. Mars, we now know, was once a very different world. Billions of years ago, it boasted a warmer, wetter climate, one that could have supported chemical reactions leading to the formation of simple organic compounds. Interestingly, laboratory experiments on Earth have shown that organic molecules can form under certain conditions, particularly in environments like hydrothermal vents, which exist on Earth's ocean floors. Such conditions may have once existed on Mars as well, deep beneath its surface or within isolated pockets of water, providing a fertile ground for life to potentially take root. What's even more exciting is that these findings might only be the tip of the iceberg. The discovery of these complex organic compounds in Mars's ancient rocks suggests that if life ever existed on the red planet, remnants of it might still be preserved within these molecules, waiting to be uncovered. The implications of such a discovery could be profound, not only because it would answer key questions about the planet's past, but also because it could alter our understanding of life in the universe. If Mars once supported life, it could indicate that life in some form is far more common in the universe than we once believed. The investigation of Mars's organic molecules is an ongoing journey, one that reminds us of the vast mysteries still awaiting us on the red planet. As we continue to peel back the layers of Martian history, we find ourselves inching closer to answers that could have far-reaching implications for the future of space exploration and the search for life beyond Earth. Each discovery on Mars adds to the growing body of knowledge that the universe is not only older and more complex than we ever imagined, it might also be far more connected to life than we once dared to dream. However, these organic compounds can also emerge from non-biological processes, a fascinating aspect of their formation. For instance, when carbon-rich materials in space interact with ultraviolet UV radiation, cosmic rays, or even thermal events, they can trigger the synthesis of these molecules. While the mere presence of such organic compounds suggests the potential for life on a planet, it does not provide definitive proof. This introduces an exciting yet profound question. Are these molecules the remnants of ancient biological activity, or are they simply byproducts of natural chemical reactions? In pursuit of answers, future space missions, such as the Mars Sample Return mission, hold great promise. These missions aim to collect Martian samples and return them to Earth for more detailed analysis. This effort would be pivotal in furthering our understanding of Mars' past, potentially shedding light on whether life ever thrived there. Such discoveries could not only rewrite the history of the red planet, but also contribute to the broader search for life beyond Earth. By examining the molecular traces found on Mars, scientists could deepen our comprehension of the planet's geological history and its capacity to harbor life. Astronauts, too, have experienced their own mysterious encounters during missions in space, an intriguing phenomenon that has both puzzled scientists and captivated the public's imagination. The so-called flashes of light are often reported during spacewalks or while passing through the Earth's shadow. While these flashes may seem alarming, scientists have determined that they are the result of cosmic rays interacting with the astronaut's eyes. Cosmic rays, which are high-energy particles, mostly protons, constantly travel through space. These particles, which originate from various sources like supernovae and the sun itself, are a natural part of the cosmic environment. When these high-energy particles make their way into the spacecraft or spacesuit, they collide with the atoms in the astronaut's eyes. This collision creates a cascade of secondary particles, which then interact with the retina. This process can trigger a visual response, leading to the perception of a flash or streak of light. Interestingly, this phenomenon is similar to the experience some people have during a retinal scan, where a direct impact on the retina generates flashes, even in the absence of actual light. Furthermore, the lack of atmosphere in space plays a crucial role in amplifying the visibility of these flashes. On Earth, air particles scatter light in all directions, which helps diffuse light sources. In space, however, the absence of air means that there are no particles to scatter the light. As a result, these flashes appear more vivid and noticeable to astronauts. Research into these space flashes has been instrumental in deepening our understanding of the risks associated with long-duration space travel. Prolonged exposure to cosmic rays is a significant health concern for astronauts, with studies showing a potential link to an increased risk of cancer and damage to the nervous system. As human exploration ventures further into space, particularly on missions to Mars and beyond, it will be vital to monitor the effects of these high-energy particles and protect astronauts' health. Understanding the causes of these flashes is critical not only for the safety of astronauts, but also for the efficiency of their performance during extended missions. As space exploration continues to evolve, so too does the need to protect the well-being of astronauts, especially on ambitious missions to distant planets. The flashes of light caused by cosmic rays offer a glimpse into the challenges faced by astronauts beyond Earth, reminding us that space exploration is as much about understanding the human experience as it is about discovering new frontiers. Another captivating area of research in space exploration is the presence of water on the Moon, a discovery that has intrigued scientists for decades. New findings are helping to unravel the complex processes behind how water may have formed or arrived on our lunar neighbor. One of the leading theories is that water was delivered to the Moon by comets and asteroids, which collided with the lunar surface over billions of years. These icy celestial bodies, rich in water, released their contents upon impact, potentially seeding the Moon with water. Alternatively, some scientists propose that water may have been present during the Moon's very formation. The Moon, which formed approximately 4.5 billion years ago, is believed to have originated from debris ejected by a colossal impact between the early Earth and a Mars-sized object. During this chaotic period, water in the form of vapor could have been trapped within the Moon's molten material. As the Moon cooled, this trapped water might have been released, forming pockets of ice in permanently shadowed regions. Recent missions, including NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1, have confirmed the presence of water ice in substantial quantities at the Moon's poles, regions that never receive sunlight. Some estimates suggest that these permanently shadowed craters could contain millions of tons of water ice. This discovery holds enormous potential, as water is a vital resource for sustaining future lunar exploration. Not only can water be split into hydrogen and oxygen to provide breathable air, but it can also be converted into propellant for spacecraft. The significance of understanding the origins and quantity of water on the Moon extends beyond scientific curiosity. It has profound implications for human exploration. As NASA's Artemis program aims to establish a sustainable human presence on the Moon, tapping into lunar resources such as water will be crucial for long-term habitation. Moreover, harnessing water from the Moon could serve as a vital stepping stone for further missions to Mars and beyond. The Moon's water could thus become not just a fascinating scientific discovery, but a key component of humanity's future in space. Lastly, the Trojan asteroid designated 2010 TK7 provides another exciting object of study. This asteroid shares an orbit with Earth, positioned at a stable point known as a Lagrange point. In the case of 2010 TK7, it resides at Earth's first Lagrange point, located about 150,000 kilometers ahead of Earth in its orbit. Trojan asteroids like 2010 TK7 are believed to be remnants of the early solar system, their origins tracing back to a chaotic time when the planets were still forming. During this period, small bodies were scattered across space, some of which became trapped in stable orbits by gravitational forces. These bodies could have been nudged into their current positions by the gravitational influence of the early Earth or other neighboring planets. While identifying the precise origin of individual Trojan asteroids remains challenging, the study of these objects provides valuable insights into the early solar system and the formation of our planetary neighbors. As space missions continue to explore these ancient remnants, they could unlock further mysteries about the solar system's history and its evolving dynamics. The fascinating nature of Trojan asteroids like 2010 TK7 underscores how much more there is to learn about the cosmos, offering endless possibilities for future exploration. However, many scientists believe that these objects could be remnants of the primordial material that originally formed the planets. Some studies suggest that they may consist of the same materials as the outer planets, while others propose that they could be fragments from larger bodies shattered during cosmic collisions. This connection to the early solar system makes objects like 2010 TK7 invaluable for understanding the conditions that existed during its formation. They offer a rare glimpse into the building blocks of our celestial neighborhood during its infancy. The Trojan asteroids, particularly, represent a fascinating opportunity for future space exploration. As our understanding of planetary science continues to advance, missions to these stable points in space, such as the Lagrange points, could reveal essential information about the processes that shaped the planets. This could potentially unravel secrets about the very origins of Earth itself. As we probe deeper into the mysteries of the solar system, the study of such asteroids enriches our comprehension of its dynamic nature, offering a closer look at the intricate forces that govern the movement and evolution of celestial bodies. By examining these ancient remnants, we may learn more about how Earth, along with the other planets, came into being. One of the most intriguing objects in our solar system, Enceladus, a moon of Saturn, continues to captivate scientists with its extraordinary geysers, which shoot spectacular plumes from its south pole. This geological activity is closely tied to the moon's unique internal structure. Beneath its frozen surface lies a vast subsurface ocean kept in a liquid state due to the tidal forces generated by Saturn's gravitational pull, as well as the influence of its other moons. The phenomenon of geyser eruptions is a direct result of the complex interplay between heat and pressure within Enceladus. Saturn's immense gravity stretches and flexes the moon, generating frictional heat that prevents the water beneath the icy shell from freezing, despite the extreme cold of its outer layers. This combination of liquid water, along with dissolved salts and organic compounds, creates an environment that fosters geyser activity. The eruptions themselves occur within a region known as the Tiger Stripes, a set of fractures in Enceladus's icy crust. These fissures allow the pressurized ocean beneath to escape when internal pressure builds to a critical point. As the water vapor and ice particles are expelled into space, the plumes can reach several hundred kilometers above the surface, offering a stunning visual display. These geysers provide more than just an awe-inspiring spectacle. They are crucial for understanding the geological and hydrological activity of Enceladus. More importantly, they hold significant implications for the potential of life beyond Earth. The presence of liquid water, along with organic materials, raises the tantalizing possibility that microbial life could exist within Enceladus's hidden ocean. As we continue to explore the mysteries of this fascinating moon, future missions are being planned to analyze the composition of the geyser plumes more thoroughly. This research could further position Enceladus as one of the leading candidates in the search for extraterrestrial life within our solar system. Each new discovery continues to add depth to the story of this captivating moon, revealing the hidden wonders that lie beneath its icy exterior. Meanwhile, on Mars, mysterious fluctuations in the levels of oxygen in the atmosphere have sparked intrigue and raised important questions about the planet's environmental dynamics. Scientists have observed that the concentration of oxygen in Mars's atmosphere can vary significantly, fluctuating by as much as 30% over the course of a seasonal cycle. Understanding these changes is critical for gaining a deeper understanding of the Martian environment, including the potential for past or present life on the red planet. One of the leading hypotheses behind these oxygen fluctuations relates to the seasonal temperature shifts and changes in atmospheric pressure on Mars. During the harsh Martian winter, carbon dioxide freezes at the polar ice caps, leading to a significant decrease in atmospheric pressure. When the warmer months arrive, the carbon dioxide sublimates back into gas, which can cause the distribution of other gases, including oxygen, to fluctuate as well. These cyclical processes of sublimation and deposition of carbon dioxide appear to influence the behavior of oxygen in Mars's atmosphere, potentially offering insights into how the Martian environment has evolved. Unraveling the mystery of Mars's oxygen fluctuations is essential for both understanding the planet's climatic history and evaluating its potential to support life. As scientists continue to monitor these atmospheric shifts, they may uncover more about the processes that shape the Martian environment and the possibility of life in the past or future. Each new piece of data brings us closer to answering fundamental questions about the red planet's history and its role in the broader context of the solar system. The surface of Mars continues to be a source of deep fascination for scientists, especially when it comes to understanding the cyclical nature of oxygen fluctuations in its atmosphere. Over the years, researchers have delved into the role that chemical reactions, both on the Martian surface and within the atmosphere, might play in shaping the planet's atmospheric composition. A key factor in these processes is the interaction of solar radiation with various surface minerals, which can trigger photochemical reactions. These reactions have the potential to produce oxygen, a gas central to life as we know it on Earth. Moreover, the presence of catalyzing materials such as iron oxides in the Martian regolith, the loose soil and rock that covers the surface, could contribute significantly to the cycling of oxygen through a variety of chemical processes. While the majority of these fluctuations are likely driven by natural processes, some researchers are keen to explore the intriguing possibility of biological activity contributing to these changes. However, despite the growing body of evidence collected by various missions to Mars, no direct proof has been found to support the hypothesis of life on Mars, at least not yet. As missions to Mars continue, the focus remains on detailed analyses of the planet's atmosphere, surface minerals, and soil. These ongoing studies have the potential to provide crucial insights into how oxygen behaves on Mars, which could, in turn, illuminate the planet's climatic history and its potential for habitability. Each new discovery brings scientists closer to piecing together the mysteries of Mars, reaffirming the importance of continued exploration in the quest to understand this enigmatic world and its atmosphere. With each discovery, the question of whether life could once have existed or could still exist on Mars becomes ever more tantalizing. Just as Mars draws attention for its potential habitability, other celestial bodies in our solar system also intrigue scientists with their unique characteristics. Take, for example, the asteroid Bennu. Its peculiar shape, a combination of boulders and loose debris, serves as a reminder of the chaotic processes that shaped our solar system. Bennu, classified as a near-Earth asteroid, has a distinctive rubble pile structure, setting it apart from more solid celestial objects. This unusual configuration can be traced back to the formation processes that took place billions of years ago when the early solar system was a violent place of collision and chaos. It is believed that Bennu and similar asteroids originated from larger parent bodies, which were shattered during catastrophic collisions. When these larger asteroids collided, they broke apart into smaller fragments. Over time, the gravitational pull between these fragments led to their eventual reassembly. However, the smaller size and low gravity of the resulting objects prevented them from fully coalescing into solid bodies like planets. Instead, they formed what scientists call rubble piles, aggregates of loosely bound rocks and debris held together by weak gravitational forces. This lack of strong gravitational attraction is why asteroids like Bennu tend to have irregular, uneven shapes. The weak gravitational pull also means that other forces, such as the asteroid's rotation, play a significant role in shaping its appearance. Bennu, for instance, completes one full rotation roughly every 4 hours. This rapid rotation causes its equatorial region to bulge slightly, giving it a shape that has been likened to a spinning top. But it's not just rotation that affects Bennu's form. Impacts from smaller bodies, collisions with meteoroids and space debris, have also contributed to its current appearance. The craters and grooves on Bennu's surface are the remnants of these impacts, adding further complexity to its shape and composition. Studying asteroids like Bennu not only provides valuable insights into the building blocks of our solar system, but also helps scientists understand the early conditions that led to the formation of planets and other celestial bodies. These asteroids are essentially relics from a time when the solar system was still in its infancy, and they may hold clues about organic material or water, two essential ingredients for life that could potentially exist within their ancient remains. Beyond asteroids, some of the most promising locations in our search for extraterrestrial life lie beneath the icy crusts of moons within our own solar system. These moons harbor vast subsurface oceans, hidden from view beneath thick layers of ice or rock. The forces responsible for maintaining the liquid state of these oceans are as diverse as the moons themselves. Tidal heating, which results from the gravitational influence of nearby celestial bodies, plays a crucial role in keeping these oceans warm despite the frigid conditions on the moon's surfaces. Europa, one of Jupiter's many moons, stands out as one of the most exciting candidates in the search for life beyond Earth. Beneath its icy exterior lies an ocean that could be as much as 150 kilometers deep. This ocean remains in liquid form thanks to tidal heating, which is driven by the gravitational pull of Jupiter and its surrounding moons. This heat, combined with the potential for chemical interactions between the ocean and Europa's rocky mantle, raises the tantalizing possibility that Europa could harbor the conditions necessary for life, even if that life is microbial. Enceladus, another of Saturn's moons, presents similar possibilities. It too contains a subsurface ocean, which remains liquid thanks to tidal heating. In fact, this heating is so intense that geysers erupt from Enceladus's south pole, venting water vapor and ice particles into space. These plumes have been found to contain organic compounds and salts, providing further evidence that the ocean beneath Enceladus's icy surface is chemically rich. Like Europa, Enceladus presents a compelling case for the potential habitability of its hidden ocean, where microbial life could be thriving. Not to be overlooked, Ganymede, one of Jupiter's largest moons, also possesses a subsurface ocean. Recent studies suggest that Ganymede's ocean may be sandwiched between layers of ice, and some scientists believe it could be even deeper than Europa's ocean. What sets Ganymede apart from other moons is its unique magnetic field, which hints at active geological processes beneath its surface. This magnetic field suggests that Ganymede may have a dynamic and complex internal structure, one that could influence the dynamics of its subsurface ocean and, potentially, its ability to support life. As scientists continue to explore these moons and their subsurface oceans, each discovery brings us closer to understanding the conditions that might allow life to exist elsewhere in the solar system. Whether on Mars, Europa, Enceladus, or Ganymede, the search for extraterrestrial life is a journey that promises to reshape our understanding of the universe and our place within it. Titan, Saturn's largest moon, stands as a fascinating world that offers an array of intriguing contrasts to both the familiar environments of Earth and the harsh alien landscapes of distant celestial bodies. It may not resemble Earth in the obvious ways we're accustomed to, but upon closer examination, Titan reveals an ecosystem governed by its own rules that might in some ways echo the processes of our own planet. One of Titan's most compelling features is its extensive liquid lakes, which are not made of water but methane and ethane. These lakes, some as large as Earth's Great Lakes, dot Titan's surface, forming intricate networks of rivers and deltas. Yet, beneath the icy shell of Titan, a profoundly stirs. Scientists hypothesize that a subsurface ocean of water mixed with ammonia could exist. This ocean is believed to remain liquid despite Titan's frigid surface temperatures due to the unique properties of ammonia, which acts as antifreeze. This potential subsurface ocean offers tantalizing possibilities for life. life forms possibly adapted to survive in such extreme and radically different conditions compared to anything we know on Earth. The study of these hidden oceans is an area of intense interest for future missions, as they might hold the key to understanding not just Titan, but the broader question of life beyond Earth. The conditions on Titan, however, offer a stunning degree of familiarity despite their differences. Titan's atmosphere is a thick blanket of nitrogen, similar to Earth's, though it also harbors large quantities of methane, a substance that plays a crucial role in the Moon's geological and climatic processes. This methane interacts with Titan's frigid surface, forming clouds and precipitation in a manner similar to Earth's water cycle, but on an entirely different scale. Titan's cold temperatures, averaging around -180 degrees Celsius, allow methane to exist as a liquid. It then evaporates, condenses, and precipitates, sculpting the landscape much like Earth's own water cycle shapes its terrain. Indeed, Titan's landscape is an eerie reflection of Earth's. The presence of methane lakes and rivers creates coastlines and deltas that evoke our own planet's geographical features. But it is the geological processes at work on Titan that truly make it stand out. Unlike Earth, where erosion is driven by water, on Titan, erosion is driven by methane. This, combined with other processes such as sediment transport and chemical weathering, has led to the formation of extraordinary terrain, including vast sand dunes, some of which resemble the dunes of Earth's desert regions. What makes Titan even more unusual are its cryovolcanoes. These are ice volcanoes that erupt not molten rock, but a slushy mix of water and ammonia. This kind of eruption is unlike anything found on Earth and provides a glimpse into how geological processes can unfold in an entirely alien environment, driven by very different materials and forces than those we see on our own planet. Together, these processes contribute to a continually evolving surface, much like Earth's ever-changing landscape. Titan, with its thick atmosphere and dynamic surface, is a living, breathing world in its own right. The study of Titan, with its mix of geological and atmospheric conditions, opens up exciting possibilities for understanding the broader universe. By studying this moon, scientists hope to uncover not just the secrets of Titan itself, but to gain a deeper understanding of how planets and moons form and evolve, and what conditions might foster life, whether it be microbial or something more complex, in environments that seem so alien to us. Titan challenges our assumptions about habitability and the potential for life in extreme conditions, offering a glimpse into the diverse and unpredictable ways life might emerge and thrive across the cosmos. Further afield, in the distant reaches of the Crab Nebula, another celestial mystery unfolds. Here, the source of periodic dimming observed by astronomers lies in the pulsating rhythms of the Crab pulsar. This neutron star at the heart of the nebula emits beams of electromagnetic radiation from its magnetic poles, sweeping them across space like the beam of a lighthouse. As the pulsar spins, these beams of radiation sweep in and out of view from Earth, creating the mesmerizing effect of periodic dimming. This pulsation occurs with astounding precision, with the Crab pulsar completing one full rotation approximately every 33 milliseconds. The Crab pulsar is a remnant of a supernova that exploded in 1054 AD, and its beams of radiation are not the only source of energy in the Crab Nebula. The interaction between the pulsar's powerful magnetic field and the expanding debris from the supernova creates a complex environment filled with shockwaves, radiation, and ever-changing electromagnetic emissions. As the pulsar's radiation sweeps past Earth, the star's brightness fluctuates, and this process provides invaluable insights into the physics of neutron stars, the behavior of magnetic fields in extreme environments, and the life cycle of stellar remnants. The study of the Crab pulsar and its surrounding nebula not only helps us understand the birth and death of stars, but also provides a unique laboratory for exploring the most extreme conditions known in the universe. Pulsars, like the Crab, serve as natural beacons for astrophysicists, providing crucial data on the fundamental processes that govern the behavior of matter and energy in some of the most extreme environments in the cosmos. Meanwhile, in the realm of stellar evolution, astronomers face a delightful conundrum. Some stars appear to be older than the universe itself. This puzzle stems from the complexities inherent in estimating the age of stars. The universe is estimated to be about 13.8 billion years old, but certain stars seem to be older than this based on traditional methods of age determination. This discrepancy points to the intricate nature of stellar formation and evolution. Astronomers typically estimate a star's age based on its position on the Hertzsprung-Russell diagram, which plots stars according to their temperature and brightness. However, this method relies on certain assumptions that may not always account for the full complexity of a star's history. These apparent age discrepancies prompt scientists to rethink how they measure stellar age and to refine our understanding of the life cycle of stars in the vast expanse of the cosmos. As we peer deeper into the stars through the lens of Titan and the pulsar rhythms of the Crab Nebula, the universe reveals its astonishing diversity and complexity. Each discovery, from the icy lakes of Titan to the pulsing heart of a neutron star, challenges our understanding of the cosmos and inspires new questions about life, evolution, and the nature of the universe itself. The ongoing exploration of these celestial wonders holds the promise of uncovering not just the secrets of the distant past, but also the keys to the future of space exploration and the search for life beyond our home planet. However, this method can often introduce significant uncertainties, especially when it comes to stars in the later stages of their evolution. When a star is located in a region of the Hertzsprung-Russell diagram that suggests it has a much older age, it doesn't necessarily mean that its true age matches this estimate. The apparent age may not be a true reflection if the assumptions underlying the evolutionary models are flawed or incomplete. The process of determining stellar ages is complicated by many factors, and these models, while sophisticated, are still subject to revision. One major contributor to this paradox is the nature of a star's composition. Stars that have higher concentrations of heavy elements, referred to as metals in astronomical terms, are typically formed after previous generations of stars have evolved and died. These earlier stars enriched the interstellar medium with heavier elements, which are then incorporated into new generations of stars. Thus, a star that exhibits a low metallicity, meaning it contains fewer of these heavy elements, could be indicative of one born from primordial materials. This suggests it could have existed since the early universe. Yet, despite its low metallicity, such stars might appear older than they actually are due to the complexities of stellar dynamics and life cycles. Adding another layer of complexity, some stars reside in globular clusters, dense collections of ancient stars that have remained largely unchanged for billions of years. Determining the exact age of these clusters presents significant challenges. Many of the oldest globular clusters are believed to be around 14 billion years old, based on stellar models. This estimation sometimes brings them perilously close to the theoretical upper limits of the universe's age. This overlap between the ages of these ancient star clusters and the age of the universe itself raises important questions about the reliability of our models for estimating stellar ages. It also challenges our understanding of star formation history in the cosmos. In light of these uncertainties, it's clear that the apparent ages of certain stars challenge our understanding of stellar evolution. These anomalies underscore the need for refinements in our modeling techniques. As researchers continue to develop more advanced telescopes and improved observational methods, we can expect to gain a deeper understanding of the intricate history of the universe and the stars that populate it. Shifting focus to a different celestial phenomenon, let's explore the extraordinary and enigmatic world of ultraluminous X-ray sources, ULXs. These are some of the most powerful astrophysical phenomena detected in galaxies far beyond our own. ULXs are distinguished by their remarkably high X-ray luminosities, often exceeding 1 million times that of our Sun. Such intense radiation is much more powerful than that emitted by typical stellar sources, making them a topic of great interest for astronomers. Despite the substantial attention they've garnered, the precise nature of ULXs remains an area of active research. ULXs are generally believed to be associated with binary systems, where a compact object, such as a black hole or neutron star, accretes material from a companion star. The accretion process generates vast amounts of energy as the material spirals toward the compact object, heating up and emitting X-rays. Many of these ULXs are thought to harbor black holes with masses ranging from a few to several tens of solar masses. This distinguishes them from stellar mass black holes, which are more commonly found in our own galaxy. What makes ULXs even more intriguing is the possibility that some of them might contain intermediate mass black holes, an elusive class of black holes whose masses range from 100 to 1,000 times that of the Sun. These intermediate mass black holes are thought to fill in a gap between stellar mass black holes and the supermassive black holes found at the centers of galaxies, which can have masses that are millions or even billions of times that of the Sun. If ULXs are indeed homes to these intermediate mass black holes, they could provide crucial insights into the formation mechanisms of the supermassive black holes that dominate galactic centers. The discovery of such objects would significantly advance our understanding of how these behemoths come into existence. The exploration of these phenomena, both in terms of stellar age determination and the study of ULXs, reveals the vast and complex nature of our universe. As our technology advances, the potential for new discoveries grows exponentially, allowing us to delve deeper into the mysteries of the cosmos. With each breakthrough, our understanding of the universe's history, from the birth of stars to the formation of black holes, continues to evolve. Ultraluminous X-ray sources, ULXs, are among the most captivating phenomena in modern astrophysics. These enigmatic celestial objects often exhibit remarkable variability in their brightness, signaling shifts in their accretion rates. At times, these fluctuations can manifest as sudden flares, offering scientists a rare glimpse into the complex interactions between the accreting material and the compact object at the center. Such variability makes ULXs an exceptional field for investigating the fundamental physics of black holes, accretion flows, and the intricate environments in which they reside. The study of ULXs is not static. It evolves with each advancement in observational technology and new observational campaigns across both optical and X-ray wavelengths. As our understanding deepens, ULXs provide a unique window into some of the most extreme astrophysical processes known to science. They offer invaluable insights into the interplay between massive stars and their compact remnants, enriching our understanding of the broader cosmic landscape. Each discovery in this field adds another layer to the complex, evolving tapestry of the universe and fuels our quest to understand the fundamental nature of matter and energy under extreme conditions. In the vast expanse of the universe, one intriguing mystery lies in the observation of certain galaxies exhibiting little to no star formation, despite having an abundance of gas, the essential ingredient for stellar birth. At first glance, this seems counterintuitive. If a galaxy has copious amounts of gas, why isn't it producing stars? However, researchers have uncovered that multiple factors can impede this process, leading to what is known as star formation quenching. A key factor in this quenching phenomenon is related to the internal dynamics of the galaxy. In some cases, the gas may not possess the necessary density or temperature to collapse into new stars. For example, turbulence within the gas or heating from existing stars can prevent the gas from cooling down and condensing. This creates a barrier to star formation. In massive elliptical galaxies, the presence of supermassive black holes at the galactic centers can be especially influential. These black holes can generate powerful winds or jets that heat the surrounding interstellar medium, effectively halting the cooling processes necessary for star formation. Galaxy mergers and interactions also have a profound impact on star formation. When galaxies collide, the gravitational forces at play can drive gas toward the galactic centers, triggering bursts of stellar activity. However, these interactions don't always lead to star formation. In some cases, they can expel gas from the galaxy or redistribute it in ways that make it harder for new stars to form. The gas may be stripped away, or its distribution may be altered to prevent it from collapsing into stars. Dark matter also plays a crucial role in galaxies that are not actively forming stars. The binding energy of the dark matter halo, which surrounds many galaxies, may not provide the necessary conditions to retain gas. In some cases, gas can be stripped from a galaxy due to interactions with its environment or through the gravitational influence of a larger structure, such as a galaxy cluster. Additionally, the cosmic web, the large-scale structure of the universe has a significant impact on gas flow and distribution. In certain regions, the inflow of gas from the intergalactic medium is suppressed, further limiting the available gas for star formation. Understanding why some galaxies maintain large reservoirs of gas without converting it into stars provides critical insights into the evolution of galaxies. By using advanced observational techniques and sophisticated simulations, scientists aim to uncover the intricate gravitational, hydrodynamic, and chemical processes that shape galaxies throughout cosmic history. Each new discovery sheds light on the complex nature of galaxy formation, deepening our understanding of the universe. Equally captivating are the ripples observed in the Milky Way's disk. These intriguing features provide valuable insights into the dynamic forces shaping our galaxy. Primarily, these ripples are the result of gravitational interactions among stars within the galactic disk, as well as the influence of nearby celestial structures. One significant contributor is the passage of spiral arms. As stars and gas clouds move through these arms, they experience gravitational forces that cause disturbances, creating wave-like patterns in the distribution of stars and gas. The Milky Way is far from an isolated system. It is orbited by several small galaxies, including the Large and Small Magellanic Clouds. The gravitational influence of these satellite galaxies can induce tidal forces that disturb the star distribution within the Milky Way's disk. Over vast timescales, these interactions can accumulate, creating observable ripples or waves in the galaxy's structure. Another intriguing possibility is the role of dark matter. Although it remains invisible to current instruments, dark matter is believed to constitute a significant portion of a galaxy's mass. Its gravitational influence can affect the motion of stars within the galaxy, contributing to the formation of these ripples. By studying the motion of visible stars, scientists can indirectly probe the properties of dark matter. As new data from telescopes and other instruments continues to come in, researchers are uncovering the intricate details of the Milky Way's structure, revealing a dynamic and ever-evolving system. Understanding these ripples not only enhances our knowledge of the Milky Way, but also provides insights into the interactions occurring in other galaxies across the universe. Meanwhile, the captivating shapes of planetary nebulae arise from a delicate interplay of processes during the final stages of a star's life. When a medium-sized star, like our Sun, runs out of nuclear fuel, it begins a transformation that culminates in the expulsion of its outer layers. The core contracts while the outer layers are ejected into space, forming a glowing shell of gas and dust known as a planetary nebula. The symmetry often observed in these nebulae results from the dynamics of this ejection process, influenced by various factors. Magnetic fields play a crucial role in shaping the structure of these nebulae. As the star sheds its outer layers, the magnetic fields can guide the flow of gas, creating more organized and intricate shapes. In many instances, these magnetic fields interact with the stellar wind, the stream of charged particles expelled by the star, further enhancing the ordered structure of the nebula. This complex interaction between magnetic fields, stellar winds, and the gas ejected from the star leads to the beautiful and symmetrical shapes that characterize planetary nebulae. As scientists continue to explore these fascinating phenomena, they are gaining deeper insights into the life cycles of stars and the physical processes that govern the cosmos. From the variability of ultraluminous X-ray sources to the mysterious quenching of star formation in certain galaxies, the universe continually offers new avenues for discovery. And through these discoveries, we are gradually piecing together the grand story of cosmic evolution, one discovery at a time. Binary star systems are more than just a pairing of two stars. They play a crucial role in shaping the cosmos around them. These dynamic systems are instrumental in the creation of some of the most symmetrical and striking formations observed in the universe. When stars in a binary system interact, the gravitational tug between the two can lead to fascinating processes, one of the most significant being mass exchange. This exchange happens when one star sheds its outer layers, which are then captured and redirected by the gravity of its companion. In doing so, the material isn't just scattered aimlessly. It is sculpted, often into highly structured shapes, creating what we recognize as distinct cosmic patterns. The interplay of these gravitational forces can also give rise to jets and lobes, which contribute to the intricate and sometimes otherworldly shapes we see in nebulae. These structures vary widely, from smooth and spherical to more complex formations like tangled knots and delicate filaments. The process is not just a fascinating spectacle. It offers a profound glimpse into stellar evolution, revealing the dramatic transformations stars undergo in their final stages. Each planetary nebula that we observe is, in essence, a snapshot, a moment in time frozen in space, showcasing nature's artistry at its finest. Equally captivating is the enigmatic interstellar object, Oumuamua, which has captivated the scientific community since its unexpected discovery in 2017. This peculiar visitor, hailing from beyond our solar system, presents a unique opportunity for researchers to study an object that has traversed vast interstellar distances before entering our cosmic neighborhood. Based on its composition and appearance, Oumuamua is thought to be either rocky or metallic in nature. What makes it stand out, however, is its elongated, cigar-like shape, an anomaly compared to the spherical or irregular forms typically observed in asteroids and comets within our own solar system. The name Oumuamua, derived from Hawaiian, means scout or messenger, an apt moniker for the first interstellar object ever detected passing through our solar system. Scientists speculate that this object originated from a distant star system, possibly ejected from its original galaxy. This ejection could have been the result of complex gravitational interactions with other stars, flinging it into the vast expanse of space at incredibly high velocities. Having been released from its home system, Oumuamua embarked on a journey that lasted millions of years, eventually arriving in the inner solar system where it was first detected by astronomers. One of the most intriguing aspects of Oumuamua's passage was the unusual acceleration it displayed as it moved through the solar system. Initially, scientists considered the possibility of outgassing, a phenomenon commonly seen in comets, where the heat of the sun causes volatile materials within the object to vaporize, propelling it forward. However, the lack of any visible tail or comet-like features forced researchers to reconsider this hypothesis. Instead, alternative theories emerged, including the possibility that Oumuamua might be a fragment of a much larger celestial body, or perhaps it is involved in the intricate gravitational dynamics of interstellar space. Whatever the case, Oumuamua remains a fascinating mystery, pushing scientists to ask fundamental questions about the distribution of interstellar objects and the forces that govern their paths across the universe. As research continues, it offers an unprecedented opportunity to uncover the secrets of objects traveling through space far beyond the confines of our solar system. Meanwhile, the star clusters that orbit galaxies present another layer of cosmic complexity. Within these clusters, scientists have observed a fascinating phenomenon: the existence of multiple populations of stars, each with its own distinct composition. This is particularly evident in globular clusters, which are ancient groupings of stars that have orbited galaxies for billions of years. The presence of such diverse populations within a single cluster reveals much about its history and the environmental conditions in which it was born. The origins of these multiple populations lie in the cluster's formative years. Many star clusters were born in dense regions of gas and dust, where the first generation of stars began their lives. These stars, through nuclear fusion, created heavy elements, enriching the surrounding material. When these stars eventually reached the end of their life cycles and exploded as supernova, they spread these heavier elements throughout the surrounding gas, raising its metallicity. This enriched material then served as the foundation for the next generation of stars. The result was a second population with a higher metallicity compared to the first. These distinct populations offer a glimpse into the evolutionary processes that shape star clusters, revealing the intricate dance of stellar life cycles and the way in which the universe constantly evolves. Together, these phenomena, the shaping of planetary nebulae by binary star systems, the cosmic mystery of Oumuamua, and the rich history embedded within star clusters, demonstrate the dynamic and ever-evolving nature of the cosmos. They remind us that the universe is not static, but rather a constantly changing tapestry, woven from the interactions of stars, gravity, and time. With each discovery, we move a step closer to understanding the forces that shape our universe and perhaps our place within it. Within star clusters, interactions among stars play a pivotal role in shaping the diversity of stellar populations. As stars evolve, some can shed material, which may then be accreted by younger stars, altering their chemical compositions in profound ways. These processes contribute to the dynamic and often complex makeup of the cluster. Additionally, it is believed that many star clusters underwent intermittent periods of star formation, spread out over millions of years. During these intervals, new generations of stars emerged, each with unique compositions reflecting the changing stellar environment. The passage of time allowed for the gradual transformation of the cluster, leading to varying chemical signatures across different populations of stars. Moreover, recent discoveries have challenged our previous understanding of how star clusters evolve. One particularly intriguing theory suggests that globular clusters may have originated from the merging of smaller individual clusters. If this hypothesis holds, it implies that what we observe today is a fusion of multiple star-forming events, all coexisting within the gravitational confines of the cluster. This idea introduces a fascinating complexity to the way we interpret the history of star formation. Each star cluster, therefore, may be seen as a mosaic of diverse stellar birth events, each contributing to the intricate web of stellar evolution. This interplay between formation history and stellar evolution is what makes the study of star clusters so captivating. These cosmic objects serve as natural laboratories, offering a wealth of information about the life cycles of stars and the chemical evolution of galaxies. Through their observation, astronomers can unravel the broader processes that shape the universe on a grand scale, tracing the footprints of star formation and chemical enrichment across cosmic time. In a different corner of the universe, a celestial phenomenon has long captured the attention of astronomers: the periodic brightening of the blazar OJ-287. Blazars are a distinctive class of active galactic nuclei, AGN, known for their powerful, relativistic jets of particles that point nearly directly at Earth. These jets emit radiation across the entire electromagnetic spectrum, and OJ-287 is particularly notable for its recurring brightness variations. Every 12 years, the blazar undergoes a dramatic surge in brightness, a cycle that has intrigued researchers for decades. The periodic activity observed in OJ-287 is thought to be the result of the interaction between two supermassive black holes at the center of the galaxy. The system consists of a primary black hole that is actively accreting material, surrounded by a secondary black hole in a binary configuration. As the companion black hole orbits the larger one, its gravitational influence affects the material in the accretion disk surrounding the primary black hole. These gravitational forces can enhance the accretion process, leading to an increased release of radiation. When the companion black hole draws closer to the primary one, the energy released as material spirals into the central black hole increases significantly. This surge of energy causes the blazar to brighten dramatically, producing observable outbursts of radiation. The mechanics behind these outbursts are further amplified by the interactions of shock waves traveling along the jet. As the material in the jet approaches the speed of light, these shock waves intensify, creating a Doppler effect that boosts the brightness of the blazar from our perspective. The cyclical nature of OJ-287 reinforces our understanding of black hole interactions within active galactic nuclei. Observing these brightening events not only sheds light on the behavior of matter under extreme gravitational and energetic conditions, but also deepens our knowledge of the dynamics that govern such massive systems. OJ-287 serves as a critical cosmic laboratory, offering valuable insights into the workings of the universe at its most energetic and fundamental levels. By studying this extraordinary object, astronomers can improve their comprehension of black hole physics, the behavior of supermassive black hole pairs, and the broader processes that shape active galaxies. In another corner of the cosmos, binary star systems undergo a fascinating phase of evolution known as common envelope evolution. This dramatic process occurs when one of the stars in a binary system expands into a red giant, enveloping its companion in a shared outer layer of gas. The gravitational interaction between the two stars during this phase can significantly alter their orbits. potentially ejecting the outer envelope of gas. However, in some cases, the system may survive this tumultuous phase, setting the stage for further evolution. Several factors can contribute to the resilience of a binary system during the common envelope phase. One key factor is the mass relationship between the two stars. If the secondary star is sufficiently massive, it may help stabilize the common envelope by retaining some of the material ejected from the primary star. This retention can allow the two stars to continue interacting, facilitating mass transfer between them and ensuring that they remain gravitationally bound. Additionally, the dynamics of the common envelope itself play a crucial role in determining the fate of the binary system. As the material from the primary star's outer layers falls onto the companion star, the gravitational energy released may cause a rapid decrease in orbital separation. If the energy is sufficient, the envelope can be ejected entirely, leading to a tighter orbit for the two stars. This tighter orbit allows for more intense interactions between the stars, which can significantly alter their subsequent evolution. The spins and magnetic fields of the stars involved also influence the common envelope process. In some cases, the orientation of the star's spins and the dynamics of their magnetic fields may help dissipate energy, preventing the envelope from becoming too diffuse. These factors can help the system maintain its integrity and avoid total disruption. When the stars are aligned in favorable ways, this interplay can facilitate the survival of the system, allowing it to undergo further evolution in a more stable configuration. Understanding the intricacies of common envelope evolution provides valuable insights into the diverse pathways that binary systems can take. Even in the face of such intense transformation, some systems manage to adapt and survive, offering a unique perspective on stellar evolution and the complex relationships that can form between massive objects in space. Each binary system is a dynamic story of cosmic survival, with outcomes that depend on a multitude of factors including mass, spin, and the interactions between stars. Finally, the James Webb Space Telescope, JWST, marks a groundbreaking advancement in our quest to understand the early universe. Equipped with a suite of cutting-edge instruments and a large, segmented mirror, the JWST is designed to observe infrared light. This allows it to peer deeper into space and time than any previous telescope, making it ideally suited to study the first galaxies that formed after the Big Bang. By observing these ancient galaxies, the JWST can uncover the conditions that gave rise to the universe as we know it today. Its observations will provide crucial insights into the earliest stages of cosmic history, offering a window into the formation of galaxies, stars, and planetary systems during the universe's infancy. In short, the advancements brought by the James Webb Space Telescope represent a leap forward in our understanding of the cosmos. By unlocking the mysteries of the distant past, JWST promises to reshape our comprehension of the universe and the fundamental processes that have shaped its evolution over the past 13.8 billion years. One of the most transformative capabilities of the James Webb Space Telescope, JWST, lies in its remarkable ability to observe distant celestial objects emitting light at wavelengths longer than the visible spectrum. As galaxies move away from us, due to the ongoing expansion of the universe, their light undergoes a shift toward the red end of the electromagnetic spectrum. This phenomenon, known as redshift, is a fundamental key to unlocking the mysteries of the universe's past. By focusing on these longer wavelengths, Webb can detect the faint light from the earliest galaxies that formed just 400 to 800 million years after the Big Bang. These galaxies are located at such great distances that their light has been traveling through space for billions of years, offering a glimpse into a time when the universe was still in its infancy. This unprecedented capability will allow astronomers to examine the formation and evolution of these ancient cosmic structures in ways that were once thought impossible. Beyond its work with early galaxies, Webb is also set to provide groundbreaking insights into the processes that govern the formation of stars and planetary systems. Its extraordinary sensitivity to infrared radiation enables the telescope to peer into dense regions of gas and dust, places where new stars are born. These areas were previously obscured from view, hidden behind thick clouds of material. Now, with Webb's ability to observe in infrared wavelengths, scientists will be able to study stellar nurseries with unparalleled precision. By analyzing these stellar birthplaces, Webb will also allow scientists to investigate the chemical composition of the materials involved in star formation. This will shed light on how the elements necessary for life, such as carbon, oxygen, and nitrogen, first formed in the early universe. Understanding the origins of these elements is crucial to understanding how stars and planets evolve over time, and how life, as we know it, might have emerged on Earth. Moreover, Webb's powerful capabilities extend to the study of exoplanets and their atmospheres, allowing astronomers to explore these distant worlds in unprecedented detail. The telescope will be able to analyze the chemical signatures of exoplanet atmospheres, looking for the presence of key molecules like water vapor, carbon dioxide, and even ozone. These molecules are essential markers in the search for life beyond Earth. By identifying which exoplanets could potentially harbor life, Webb will contribute significantly to humanity's understanding of the universe's potential to support life, broadening our perspective on where life might exist beyond our home planet. The James Webb Space Telescope is not merely a scientific tool. It represents a monumental leap forward in our ability to explore the cosmos. It is designed to peer into the distant past, shedding light on the early epochs of the universe, and revealing the intricate processes that shape galaxies, stars, and potentially life itself. With the telescope's advanced capabilities, we are poised to make discoveries that could challenge existing theories and inspire entirely new questions, expanding the boundaries of our knowledge and fundamentally enhancing our grasp of the universe. In parallel, gravitational wave astronomy has emerged as an exciting new frontier that is already revolutionizing our understanding of the cosmos. Since the first detection of gravitational waves in 2015, this emerging field has provided unprecedented insights into the most extreme and dynamic events in the universe. As technology continues to improve and more advanced gravitational wave detectors come online, we can expect a series of breakthroughs in the coming decades that will deepen our understanding of astrophysical phenomena and open new doors in fundamental physics. One of the most promising areas of discovery in gravitational wave astronomy is the study of black hole mergers. As more and more gravitational wave events are detected, astronomers will gain invaluable data about the properties and populations of black holes scattered across the universe. This includes critical information on their masses, spins, and the frequency of their collisions. Understanding these dynamics could reveal much about the formation mechanisms of black holes, their role in the evolution of galaxies, and even provide clues about the nature of the extreme gravity fields they generate. In addition, these studies may offer insights into the fundamental laws governing black hole physics, expanding our knowledge of the universe's most enigmatic objects. Another exciting potential breakthrough lies in the observation of neutron-star mergers. The gravitational waves produced by these violent collisions carry critical information about the ultra-dense matter that composes neutron stars. By combining these gravitational wave signals with electromagnetic observations, scientists can explore phenomena such as the formation of heavy elements in the universe, like gold and platinum, through processes such as kilonovae explosions. This multi-messenger approach, combining gravitational waves and electromagnetic signals, promises to enhance our understanding of cosmic events and how elements are synthesized in the universe. Gravitational wave astronomy also holds immense potential for exploring fundamental physics beyond our current theories. For example, by studying the behavior of gravitational waves, researchers hope to address long-standing questions about the nature of dark matter and dark energy, two of the greatest mysteries in modern physics. Additionally, some researchers are investigating whether gravitational waves can be used to test the linearity of general relativity itself, potentially providing new insights into how gravity works on the most extreme scales. These groundbreaking explorations could ultimately pave the way for the development of advanced theories that seek to unify general relativity, which governs large-scale phenomena like black holes and galaxies, with quantum mechanics, the theory that describes the behavior of particles at the smallest scales. Such a unification would address long-standing questions in physics and potentially lead to a deeper understanding of the fundamental forces that govern the universe. Together, the James Webb Space Telescope and the rapidly evolving field of gravitational wave astronomy represent two of the most powerful tools humanity has ever developed to explore the cosmos. By observing the universe through both light and gravitational waves, we are poised to make discoveries that will not only revolutionize our understanding of the universe's history, but also redefine the very laws of physics that govern the natural world. As we stand on the precipice of an exciting era in astrophysical research, the advent of future gravitational wave observatories, such as the European Space Agency's LISA, Laser Interferometer Space Antenna, along with other proposed projects, promises to open an entirely new chapter in our understanding of the cosmos. These upcoming facilities are set to detect lower frequency gravitational waves, a breakthrough that will allow scientists to observe previously elusive astrophysical phenomena. The ability to detect these waves could lead to the discovery of entirely new types of cosmic events, such as the mergers of supermassive black holes residing at the centers of galaxies, which up until now have remained largely hidden from view. Furthermore, it may offer us a window into the primordial gravitational waves that were generated during the earliest moments of the universe, potentially shedding light on the mysteries of the universe's birth and evolution. Over the coming decades, the field of gravitational wave astronomy is poised to revolutionize our understanding of the universe. These observations will unravel some of the most enigmatic and extreme phenomena in existence, phenomena that have long been inaccessible to traditional methods of observation. As we continue to push the boundaries of detection, the gravitational waves that reach us carry information from the very heart of cosmic events, opening doors to deeper insights into the fundamental workings of nature. Neutrino astronomy, too, holds the potential to fundamentally transform our understanding of the cosmos. Neutrinos are subatomic particles that interact with matter in a remarkably weak manner, enabling them to traverse vast expanses of space without being absorbed or deflected by intervening material. This extraordinary property makes neutrinos an invaluable tool for studying cosmic phenomena that would otherwise remain hidden, from supernova to active galactic nuclei to gamma-ray bursts. These high-energy events produce copious amounts of neutrinos, which carry crucial information about the extreme processes at play. For instance, when a massive star collapses in a supernova explosion, it releases an immense flux of neutrinos that can provide insights into the conditions and physical processes during such catastrophic events. Detecting these neutrinos allows scientists to probe the mechanisms driving stellar evolution, offering a unique perspective on the life cycles of stars. Neutrinos also provide a crucial link to understanding the origins and behavior of cosmic rays. High-energy particles that come from astrophysical sources like supernova remnants, active galaxies, or even the collision of neutron stars. As cosmic rays interact with matter, they produce neutrinos, and by studying these particles, researchers can trace the cosmic rays back to their sources, unveiling the mysteries of these high-energy environments. Beyond their role in understanding high-energy astrophysical phenomena, neutrinos are also key to unlocking the secrets of the early universe. Shortly after the Big Bang, neutrinos played an essential role in shaping the dynamics of the cosmos. By studying the relic neutrinos from this epoch, often referred to as the cosmic neutrino background radiation, scientists can gain valuable clues about the universe's evolution, the formation of its structures, and even the mechanisms that led to cosmic inflation, the rapid expansion of the universe in its first moments. As neutrino detection technology continues to advance, the field of neutrino astronomy is set to expand, offering new insights into some of the most elusive and energetic processes in the universe. By complementing the electromagnetic observations made by telescopes, which capture light across a range of wavelengths, neutrino astronomy provides a fuller, more nuanced picture of the cosmos. This synergy between different types of observational data will allow researchers to build a more comprehensive understanding of the fundamental processes governing both celestial objects and the universe as a whole. In addition to the expanding horizons of gravitational wave and neutrino astronomy, Our own solar system still holds a wealth of scientific mysteries waiting to be unraveled. Among the most intriguing targets for future exploration are the ice giants, Uranus and Neptune. Despite being relatively close to Earth in astronomical terms, both of these planets remain underexplored, and there are many questions about their nature that remain unanswered. A dedicated mission to these enigmatic worlds could reveal critical information about their composition, their atmospheres, and the broader dynamics that shape our solar system. One of the key areas of interest for such missions would be the atmospheric composition and weather patterns of Uranus and Neptune. Both planets boast dynamic atmospheres with dramatic features such as powerful storms, intense winds, and possibly even seasonal changes. By closely examining these features, future missions could offer crucial data about the processes that drive such atmospheric phenomena. Moreover, understanding the composition of their atmospheres, particularly the presence of gases such as methane, ammonia, and water, could provide insights into the formation and evolution of ice giants. These findings would help scientists better understand how these planets came to be and the role they played in the early stages of our solar system. Another major goal of these missions would be to investigate the internal structures of Uranus and Neptune. What lies beneath the thick layers of their atmospheres? Do these planets have layered atmospheres, rocky cores, or even oceanic interiors? By exploring these questions, scientists develop a more complete model of how ice giants form and evolve. This research could also offer a fascinating comparison to gas giants like Jupiter and Saturn, revealing the diversity of planetary types in our solar system and providing important context for the study of exoplanets orbiting distant stars. In the coming years, the exploration of both the ice giants and the phenomena observed through gravitational wave and neutrino astronomy will not only deepen our understanding of the universe, but also reveal the intricate connections between the largest cosmic events and the smallest particles that populate space. As we continue to explore, both in our own solar system and beyond, we are sure to uncover answers to some of the most profound questions about the nature of existence itself. Exploring the magnetic fields and magnetospheres of Uranus and Neptune offers a remarkable opportunity to uncover the hidden dynamics of these enigmatic ice giants. Unlike other planets in our solar system, these two worlds possess magnetic fields that are unlike any we've seen before. The magnetic axes of Uranus and Neptune are both tilted and offset, creating a distinct magnetic environment that does not align with their rotational axes. This peculiar characteristic sets them apart from other planets and opens up intriguing possibilities for understanding their internal structures. By studying the unusual properties of these magnetic fields, scientists can unlock critical insights into the deep, complex processes occurring within the planet's cores, processes that have been largely hidden from our view. Future missions to Uranus and Neptune can not only shed light on the internal workings of these planets, but also offer invaluable clues about the broader history and evolution of our solar system. By carefully investigating the conditions under which these ice giants formed, scientists hope to uncover how they might have evolved and migrated across the solar system in its infancy. Such discoveries could dramatically reshape our understanding of the formation and behavior of giant planets, offering a fresh perspective on the dynamics of the solar system's early years. Moreover, as astronomers continue to identify exoplanets that share similar characteristics with Uranus and Neptune, the data gathered from these future missions will prove essential for comparison. The insights gleaned from our ice giants will serve as a critical reference point for studying distant worlds. As scientists probe the atmospheres, interiors, and magnetospheres of these exoplanets, the knowledge we gather from our own solar system could provide crucial context, allowing us to make informed comparisons between distant exoplanets and the giants of our own cosmic neighborhood. In this context, missions to Uranus and Neptune are poised to transform our understanding of planetary diversity, dynamics, and the processes of planetary formation. These ice giants are more than just fascinating objects of study. They are key to unlocking some of the most profound questions in planetary science. Each new discovery made during future explorations could drastically alter our perceptions of the cosmos and inspire a deeper, more nuanced exploration of the universe. These missions are not merely scientific endeavors. They are stepping stones to a broader understanding of the complexities and mysteries of our solar system and beyond. At the same time, the rapidly advancing fields of artificial intelligence, AI, and machine learning are set to revolutionize how we process astronomical data, making it possible to explore the cosmos in ways previously unimaginable. The enormous volumes of data generated by modern telescopes and observatories can be overwhelming, often reaching petabytes from massive surveys of the night sky. Traditional methods of analysis, while effective to an extent, struggle to keep pace with this data deluge. AI, however, offers the powerful tools needed to efficiently analyze, interpret, and extract meaningful insights from this vast ocean of information. One of the most exciting advancements driven by AI lies in the automation of celestial object classification. With so many different phenomena detectable in the universe, from distant stars and galaxies to transient events like supernovae and gamma-ray bursts, AI can significantly improve the speed and accuracy with which scientists can identify and categorize these objects. By training machine learning algorithms on vast labeled datasets, researchers can create sophisticated classifiers capable of recognizing patterns in data that would otherwise be missed by human eyes or traditional techniques. This ability to quickly and reliably categorize astronomical phenomena allows astronomers to zero in on the most promising leads for further investigation, enhancing the efficiency of research and accelerating scientific progress. AI's impact doesn't stop at classification. It also plays a crucial role in addressing one of the most challenging aspects of astronomical data, distinguishing real signals from noise. In endeavors like the search for gravitational waves or the detection of exoplanets, the ability to separate genuine signals from background interference is paramount. Machine learning algorithms can be trained to detect subtle anomalies in the data, whether it's a faint gravitational wave or the signature of a distant exoplanet, making it far more likely that important discoveries will be made. These algorithms can sift through massive data sets, flagging interesting anomalies that might otherwise go unnoticed. Another promising application of AI lies in the realm of astrophysical simulations. The modeling of complex processes like galaxy formation or stellar evolution requires the analysis of vast amounts of data. AI can help process these enormous data sets, making it possible to simulate the intricate dynamics of the universe with far greater precision than ever before. Furthermore, AI-driven models can improve over time, evolving through iterative learning. With each new dataset, these models become more accurate, allowing researchers to make more precise predictions about the behavior of celestial objects and events. By integrating AI and machine learning into the fabric of modern astrophysics, scientists are poised to accelerate their ability to explore the mysteries of the cosmos. The future of astronomical research lies not only in the continued exploration of distant planets like Uranus and Neptune, but also in the powerful tools of artificial intelligence that will help unravel the complex processes that govern our universe. The fusion of these two fronts promises a new era of discovery, one where the boundaries of human knowledge are pushed farther than ever before, and where the most profound mysteries of the cosmos are within our grasp. Moreover, as multi-wavelength observations continue to gain prominence in modern astronomy, the challenge of integrating data from diverse sources becomes increasingly complex. Machine learning, however, offers transformative tools for data fusion, enabling the synthesis of information gathered from optical, infrared, radio, and other wavelengths. This powerful capability allows astronomers to form a much more holistic and nuanced understanding of celestial phenomena. Such a comprehensive approach is particularly valuable when studying intricate systems like active galactic nuclei or examining the intricate interactions of different components within galaxies. The potential of artificial intelligence, AI, and machine learning in the field of astronomy is vast, with new possibilities unfolding as these technologies evolve. As they continue to advance, they will provide researchers with the ability to process, analyze, and interpret vast quantities of astronomical data with an unprecedented level of precision and efficiency. This ongoing transformation holds the promise not only of uncovering new celestial phenomena, but also of refining our understanding of the fundamental principles that govern the universe. In the near future, this technological progress will open new frontiers in cosmic exploration, shedding light on some of the universe's most profound mysteries. In particular, large-scale galaxy surveys, which are set to become a cornerstone of modern astronomy, promise to provide groundbreaking insights into the cosmos. These expansive observational campaigns aim to map billions of galaxies across vast swaths of space, collecting an immense array of data about their properties, distributions, and interactions. The wealth of information gathered will allow researchers to tackle some of the universe's most fundamental questions while refining our existing theories about galaxy formation and evolution. One of the most exciting areas of exploration will be the large-scale structure of the universe. By studying how galaxies are distributed throughout space, astronomers can begin to unravel the intricate cosmic web, the vast network of filaments and voids that shapes the universe on the largest scales. Understanding the patterns in which galaxies are clustered and spread out across space provides crucial insights into the evolution of cosmic structures since the Big Bang. These studies may also shed light on dark matter and dark energy, two of the universe's most enigmatic components. By observing how these unseen forces influence the motion and clustering of galaxies, researchers hope to uncover more about their role in the evolution of the cosmos. Another key area of investigation will be the properties and characteristics of different types of galaxies. Large-scale surveys will allow scientists to classify galaxies based on various criteria, including their shape, star formation rates, and chemical composition. By cross-referencing these properties with environmental factors, such as whether galaxies reside in isolated regions or dense clusters, astronomers can gain deeper insights into how galaxies evolve in different cosmic environments. This research will help scientists piece together the complex processes that drive galaxy formation, particularly during crucial periods of their life cycles. The dynamics of galaxy interactions will also be a major focus. Many galaxies are found in close proximity to one another, and their gravitational interactions can cause significant changes in their structure and star formation activity. By observing galaxy mergers and collisions, researchers can learn more about the processes that drive the growth of supermassive black holes at the centers of galaxies, and how these cosmic giants impact their host galaxies. These findings will provide valuable clues about the fundamental physics that govern galaxy evolution. Additionally, large-scale surveys will play a pivotal role in the search for exoplanets and habitable environments beyond our solar system. By investigating the stellar populations within galaxies and tracking their distribution across cosmic time, astronomers can identify which types of stars and planetary systems are most likely to support life. The data gathered from these surveys will be critical to addressing one of the most profound questions humanity has ever asked: is there life elsewhere in the universe? The insights gleaned from these upcoming large-scale galaxy surveys will have far-reaching implications for our understanding of the universe's structure, the forces driving galaxy evolution, and the search for life beyond Earth. As these surveys unfold, they will undoubtedly benefit from continuous advancements in technology and data analysis. These innovations will not only enable a more thorough exploration of the cosmos, but will also refine our place within it. At the same time, detecting and studying primordial gravitational waves presents an exciting new frontier in cosmology. These waves, which carry information from the universe's earliest moments, particularly from the period of cosmic inflation just after the Big Bang, hold the potential to reveal profound insights into the very origins of the universe. To detect these elusive waves, researchers are developing advanced techniques and technologies aimed at isolating their faint signals from the overwhelming background noise of the universe. One of the most promising methods for detection is the use of highly sensitive cosmic microwave background, CMB, observations. Primordial gravitational waves are expected to leave a distinct imprint on the CMB, the afterglow radiation from the Big Bang. As gravitational waves ripple through the fabric of space-time, they can influence the polarization of the CMB. By precisely measuring these polarization patterns, scientists can search for unique signatures that would indicate the presence of primordial gravitational waves. Ongoing and future missions, such as those involving the Simons Observatory and advancements in compact interferometers, are focused on mapping these polarization patterns with greater sensitivity to improve detection capabilities. Another promising avenue for detection involves the use of advanced gravitational wave observatories such as the Laser Interferometer Space Antenna, LISA. LISA aims to detect gravitational waves in lower frequency ranges, which may include signals from the merging of supermassive black holes formed in the early universe. While these signals may differ from primordial gravitational waves produced during cosmic inflation, their detection would still provide a broader view of the gravitational landscape of the early cosmos. If LISA succeeds in detecting these waves, it would mark a significant advancement in our understanding of gravitational wave propagation and their origins. On the ground, upcoming terrestrial detectors, such as the Einstein Telescope, the next generation of the Laser Interferometer Gravitational Wave Observatory, LIGO, are being designed with enhanced sensitivity to higher frequencies. These advanced detectors will be capable of detecting gravitational waves potentially originating from cosmic events that are tied to the early universe. By comparing findings from various detectors operating across different frequency bands, scientists will be able to explore a much wider range of gravitational sources, offering an unprecedented view into the universe's most fundamental phenomena. Researchers are pushing the boundaries of our understanding by exploring new theoretical models and simulations designed to predict the elusive characteristics of primordial gravitational waves. These waves, which were born in the earliest moments of the universe, could be the key to unlocking a deeper comprehension of the cosmos. By refining these models, scientists are not only improving their predictions about how these gravitational waves interact with matter and energy, but also laying the groundwork for more effective observational strategies. In the search to detect these waves, scientists are blending innovative observational techniques with cutting-edge gravitational wave detector technology. This marriage of theory and practice could lead to breakthroughs that enhance the design of detection instruments and improve search algorithms. As this field continues to evolve, every new discovery has the potential to significantly alter our understanding of cosmic inflation, the conditions that shape the early universe, and the very fabric of space-time itself. The study of primordial gravitational waves promises to offer cosmic breadcrumbs, small yet profound pieces of information that could guide us toward a more complete understanding of the universe's origins and its ongoing evolution. Should we succeed in detecting these waves, it could mark a monumental shift in our comprehension of the forces and events that occurred at the very birth of the universe. However, the quest does not end with gravitational waves. Looking ahead, the development of an interstellar probe designed to explore nearby star systems could offer a groundbreaking opportunity to expand our knowledge of the universe, particularly regarding the formation of planetary systems, the potential for extraterrestrial life, and the intricate dynamics of stellar environments. With advancements in propulsion methods and space travel technology, such a probe could go beyond the realm of theoretical speculation, providing us with direct data from beyond our solar system. This would offer insights into distant systems and phenomena that are currently known only through remote observation. One of the primary missions of an interstellar probe would be to study the planetary systems surrounding neighboring stars, such as Proxima Centauri, Alpha Centauri A, and Alpha Centauri B. By analyzing the chemical compositions, atmospheric conditions, and potential habitability of exoplanets in these systems, researchers could make significant strides in our understanding of planetary formation and evolution. The probe could investigate whether conditions similar to Earth's exist elsewhere in the galaxy, assessing the presence of water, organic molecules, and other essential elements needed to support life. This, in turn, would bring us closer to answering the age-old question, are we alone in the universe? In addition to searching for signs of life, the probe could delve into the complexities of stellar environments, studying solar activity, magnetic fields, and how these factors influence the planets that orbit these stars. Understanding how stellar winds and radiation impact the atmospheres of nearby exoplanets is crucial for assessing the habitability of those worlds. By learning how different types of stars interact with their planetary systems, we could gain valuable insights into the conditions required for life, as well as how these systems might differ from our own. Moreover, the probe could provide invaluable data on the interstellar medium, the vast, diffuse gas and dust that exists between the stars. As it travels through this region, the probe could analyze the composition of particles, magnetic fields, and radiation levels. This data would not only enhance our understanding of the conditions within interstellar space, but also help illuminate the processes that drive the evolution of galaxies and star systems. Such findings could eventually lead to a deeper comprehension of how galaxies form and evolve, shedding light on the grander cosmic narrative. But the importance of an interstellar probe extends beyond scientific exploration. It could serve as a critical stepping stone for future missions, providing data on the challenges of navigating interstellar space. By studying radiation exposure, navigation difficulties, and the power requirements of such long-duration missions, scientists and engineers could refine the technologies needed for human space travel beyond our solar system. This is not just about exploring distant stars, it's about preparing humanity for future spacefaring endeavors that could one day take us to the farthest reaches of the galaxy. Beyond its scientific and technological contributions, an interstellar probe would also captivate the public imagination. The very notion of sending a spacecraft to explore distant stars has the power to inspire future generations of scientists, engineers, and space enthusiasts. It would renew global interest in space exploration and reignite the search for extraterrestrial life. The excitement generated by such a mission would undoubtedly fuel further advancements in space exploration, laying the groundwork for humanity's continued journey into the cosmos. Each discovery made by the probe would bring us closer to answering some of the most profound questions of our existence. Are we truly alone in the universe? How did life emerge, and how might it evolve elsewhere in the galaxy? And perhaps most intriguingly, what is our place in this vast, ever-expanding universe? Another bold frontier in astrophysics is the study of the cosmic neutrino background, an elusive and challenging domain. These primordial neutrinos, which were produced during the first moments of the universe, hold the potential to revolutionize our understanding of the conditions that existed just after the Big Bang. By studying these relic neutrinos, we can gain invaluable insights into the universe's early temperature, density fluctuations, and the formation of large-scale structures. Though the task is difficult and requires advanced technology, the potential rewards of studying cosmic neutrinos are immense. These particles could serve as a window into a time long before stars, galaxies, and even atoms as we know them existed. By detecting and analyzing the cosmic neutrino background, scientists hope to piece together a more complete picture of the universe's infancy, ultimately refining our models of cosmic evolution and our understanding of the forces that shape the universe from the very beginning. In both cases, the search for primordial gravitational waves and the study of cosmic neutrinos, scientific advancements will continue to build upon one another, offering more precise tools and theories to explore the universe's deepest mysteries. Whether we are looking outward toward distant star systems or inward to the quantum realms of the early universe, every discovery helps us understand the cosmic puzzle piece by piece, moving us closer to answering the greatest questions of existence. The detection of cosmic neutrinos, a fundamental and elusive aspect of the universe's early history, presents an ongoing challenge for scientists. Their identification is particularly difficult due to the weak interaction they have with matter. These nearly ghostly particles pass through most substances undetected, making their presence almost invisible. However, scientists are undeterred. One promising approach to detect the cosmic neutrino background, CNB, is the use of large-scale neutrino detectors, expansive facilities designed to capture the rare moments when neutrinos interact with matter. These detectors, such as the Ice Cube Neutrino Observatory at the South Pole, are built in locations that provide a shield from background noise and cosmic rays. Ice Cube, for instance, consists of a massive array of detectors buried deep beneath the Antarctic ice, hoping to catch the faint signals of high-energy neutrinos. Another major initiative is the Short Baseline Neutrino Program, SBN, a next-generation detection facility designed to be even more sensitive to low-energy neutrino interactions. These detectors aim to identify interactions that would otherwise go unnoticed by previous generations of technology. In the coming years, we may see the development of even more advanced technologies, liquid argon or water-based detectors, which hold the promise of boosting sensitivity to these low-energy neutrino signals, allowing scientists to inch closer to detecting the cosmic neutrino background. Yet, detecting these faint neutrinos is not limited to particle physics alone. Another method involves studying the cosmic microwave background, CMB, the afterglow of the Big Bang. The primordial neutrinos that flooded the universe in its early stages have left an indelible mark on the CMB's temperature fluctuations. These neutrinos influenced the universe's dynamics in its infancy, imprinting their presence on the radiation that permeates the cosmos today. By analyzing the intricate maps of the CMB, scientists can look for subtle clues, signatures that point to the existence of these primordial neutrinos. Currently, a number of ongoing and upcoming missions are dedicated to exploring the CMB. For instance, the Atacama Cosmology Telescope, ACT in Chile, is already contributing to detailed observations of the CMB, and future satellite missions will extend this research further. Such data will be invaluable in refining theoretical models that incorporate the effects of cosmic neutrinos. This is where astrophysical simulations also play a crucial role. These simulations are essential in predicting the behavior of cosmic neutrinos, allowing researchers to better understand their interactions with other particles and the fields that dominated the early universe. By simulating the cosmos's earliest moments, scientists can pinpoint regions of interest, guiding future experiments and providing insights into where the clearest signals might be found. These models also help predict the energy spectrum of relic neutrinos, which is key to developing detection strategies and designing new instruments. Collaborative efforts across various scientific disciplines are indispensable for tackling the challenge of detecting and studying the cosmic neutrino background. Integrating data from neutrino detectors, CMB observations, and cosmological surveys offers a more holistic understanding of the early universe's conditions. These multidisciplinary approaches are crucial for advancing our knowledge of fundamental physics and the processes that shape the universe as we know it today. The collaboration of different research areas will not only provide answers, but may also open new avenues of inquiry into the universe's most mysterious components. In conclusion, while the cosmic neutrino background remains a formidable puzzle, breakthroughs seem to be on the horizon. Innovative detection technologies, along with increased collaboration between research groups, are gradually bringing us closer to solving this cosmic mystery. Success in this endeavor could provide invaluable insights into the origins of the universe, deepening our understanding of the fundamental forces that shaped the cosmos. These discoveries could also shed light on how these forces continue to influence the fabric of the universe, offering a deeper appreciation of the cosmic landscape. Beyond the study of neutrinos, the future of space exploration also looks promising, particularly with the development of space-based telescopes. These state-of-the-art instruments, expected to launch in the coming decades, are set to provide unprecedented views of our solar system, pushing the boundaries of our knowledge and understanding. Equipped with cutting-edge technology, these telescopes will allow astronomers to explore distant, elusive objects within our solar system, including those in the Kuiper Belt and Oort cloud. These regions are populated by remnants from the solar system's infancy, icy bodies such as Pluto and its dwarf planet companions. Space-based telescopes offer the ability to study these objects in greater detail, revealing their compositions, surface features, and even their atmospheric properties. By analyzing the chemical and physical properties of these bodies, scientists hope to uncover clues about the solar system's formation and the processes that led to the creation of the planets. For example, the discovery of organic molecules or signs of past geological activity could reshape our understanding of the early solar system, offering new perspectives on the conditions that existed in its nascent years. These telescopes will also provide a more detailed view of comets and asteroids, key building blocks of the solar system. Understanding these bodies will give us insights into their internal structure, surface processes, and the roles they played in the formation of the planets. Studying their orbits and other properties will also help assess potential threats, enabling scientists to better understand and perhaps mitigate the risk posed by hazardous asteroids, a critical aspect of planetary defense. Another exciting frontier for space-based telescopes will be the search for signs of life on the moons of gas giants such as Jupiter's Europa, Saturn's Enceladus, and Saturn's moon Titan. These moons have long been considered prime candidates for hosting life due to their subsurface oceans, which may harbor conditions suitable for life. Telescopes in the future may be able to analyze the plumes of water vapor that erupt from these moons, searching for biosignatures or other markers of biological activity. This research will not only deepen our understanding of whether life exists beyond Earth, but also help us learn more about the potential for habitable environments elsewhere in the cosmos. As technology advances and as space exploration progresses, the potential for breakthroughs in both neutrino research and solar system exploration is immense. With every new discovery, we move closer to understanding the intricate workings of our universe and perhaps the fundamental mysteries of life itself. Space-based telescopes are set to revolutionize our understanding of the universe, offering unparalleled opportunities to study solar phenomena and their interactions with planetary atmospheres. By investigating solar activity and its effects on planets, these observatories will provide essential data sets that unravel the intricate dynamics of our cosmic neighborhood. Through a focused study of solar wind and its impact on planetary magnetospheres and atmospheres, researchers will gain critical insights into the forces that shape these environments. This knowledge will extend far beyond theoretical speculation. On planets like Mars, where solar wind has played a key role in atmospheric loss, it could illuminate the reasons behind significant planetary changes. Similarly, understanding the interaction between solar wind and Earth's magnetic field will help scientists decipher climate processes here, offering potential implications for climate science on Earth, and other distant worlds. Moreover, the synergy of advanced imaging technologies, precise spectroscopy, and the ability to observe across a multitude of wavelengths will empower these space-based telescopes to delve deeper into the mysteries of our solar system. These innovations will not only reveal hidden facets of our planetary neighbors, but also pave the way for groundbreaking discoveries, each building on the last. With each revelation, our comprehension of the processes that govern planetary formation and evolution will expand, shedding light on the intricate forces that shape planetary systems. As we continue to explore the far reaches of our solar system, we are poised to unlock secrets that will reshape our understanding of the universe. This exploration promises to foster a deeper appreciation for the vastness and complexity of the cosmos we are just beginning to understand. Through these efforts, humanity will move closer to answering some of the most profound questions about our place in the universe.